Fund in North Carolina State University, so these are all great. Finally, I want to thank you all for coming here and participating in the program. A lot of the students and faculty and their mentors that we had for the scholars, and all of you who are here to listen to this effort. And now what I'd like to do is finally to introduce to you Professor Roy or Ruing Hong He, the Goodnight Innovation Distinguished Professor in Marine, Earth, and Atmospheric Sciences here at NC State. And he's the Keynote Institute Senior Faculty Fellow on Climate Change. And Roy played a tremendous role in organizing this meeting, and it's in your hands now. Thank you.
Good morning, everyone. And thank you, Professor Carbonell, and thanks Chancellor Woodson, and also thank you, Amanda, for all your tremendous effort putting this symposium together. And also thanks to everyone in the audience for coming to join us this morning. So if we can move to the next slide. All right, so our climate is changing rapidly. And this slide shows the time series of atmospheric carbon dioxide. And as we can see, before 1950, for more than 800,000 years, the atmospheric CO2 concentration has never been above 300 parts per million. Now, in the last 17 years, we have this alarming rate of CO2 increase. And today we are having 410 ppm parts per million. So the global warming caused by such large increase in greenhouse gases is already have many dire consequences, such as sea level rise and the strong and slow moving storms, as we all have seen about 10 days ago. So the global climate change is the most challenging environmental problem we are facing today. So this Climate Leaders Symposium highlights the contribution in the State University Climate Leaders Program, scholars and also mentors, and also outside experts are making on climate science, climate solutions, social economics and policies. And we are really, thank you again for joining this exciting inaugural symposium. So please allow me to introduce our two distinguished speakers for our plenary session. First, we welcome Ms. Barrett. Ms. Barrett is the NOAA Senior Advisor for Climate. In this role, she is responsible for providing strategic advice and direction within NOAA to enable the agency to best provide climate service needed to address the climate change. Ms. Barrett represents NOAA's effort to achieve US climate goals to reduce emission and stabilize global temperature by mid-century. In 2015, Ms. Barrett was one of the first women elected to serve as the vice chair of the Intergovernmental Panel on Climate Change, also known as IPCC, a position she still holds. Prior to joining NOAA in 2005, she was a director of the Global Climate Change Program at the US Agency for International Development and oversaw climate activities in more than 40 countries. She has won many awards for contributions both to NOAA and to the nation, including a Nobel Peace Prize. Shared with members of the IPCC in 2007. In 2021, Ms. Barrett was awarded a Distinguished Presidential Rank Award, one of the most prestigious awards in the Federal Career Civil Service. So thank you, Ms. Barrett, for joining us this morning, and thank you for your leadership and the contribution to address our climate challenges. Next, we'll also welcome our second plenary speaker, Ms. Elizabeth Beiser. Governor Roy Cooper named Ms. Beiser as Secretary of the North Carolina Department of environment quality, also known as DEQ, in June 2021. She is the first woman confirmed as a DEQ secretary. As the DEQ secretary, Ms. Beiser oversees the state agency whose mission is to protect North Carolina's environment and the natural resources. This agency has offices from the mountains to the coast and administers regulatory and public assistance programs aimed at protecting the quality of North Carolina's air, water, land, its coastal fishery, and the public health. So Ms. Beiser previously served as a director of legislature and intergovernmental affairs when the agency was known as the North Carolina Department of Environment and Natural Resources. And during her tenure in that position, she played a major role in securing $134 million in funding the design and the construction of the Green Square complex in downtown Raleigh. So thank you, Secretary Beiser, for joining us this morning, and thank you for your leadership and contribution in protecting the environment and the natural resource for North Carolinians. So Ms. Barrett and Secretary Beiser will speak one after the other, followed by a Q&A session. So we'll be inviting both of you to the stage. But first, let's welcome Ms. Barrett first to give a keynote presentation.
Just get myself set up here a little bit. Well, hello everybody. It's so nice to be here with you today in North Carolina. Many thanks to NC State University and the Keynote Institute Climate Leaders Program, and to you, Amanda and Roy, for having me, Secretary Beiser. So honored to share this session with you. As a representative of both NOAA and IPCC, I always also start my presentations with science to make sure that we're all on the same page about the climate challenges, so we have a common basis from which to discuss solutions. So I think this will kind of nicely complement what Roy put up, but also dovetail very nicely with the session to follow. So, no slides. I'll just talk with you a little bit about what do we know. In brief, it's indisputable that human activities are causing climate change, and human influence is making extreme climate events, including heat waves, heavy rainfall and droughts, more frequent and severe. Human activities have warmed the planet at a rate not seen in at least the past 2,000 years, an alarming and undeniable warming trend, where the planet has already warmed by 1.1 degrees C since pre-industrial times and shows no signs of slowing down. The level of warming is a threat to human well-being and the health of the planet. Each day, we see the impacts of extreme weather and climate play out across the globe in the ways that scientists predicted would happen. It has become commonplace to wake up wondering where we will see a new record temperature or a devastating flood, so often completely outside of the range of normal. And every increment of additional warming increases the risks of severe impacts, some of which will be irreversible, like Arctic sea ice retreat, increases in heavy rainfall and flooding, and loss of glaciers and snowpack. These changes are driven by the rise in greenhouse gas emissions, as Roy pointed out. Average annual greenhouse gas emissions during the last decade were higher than in any previous decade in human history. And greenhouse gas emissions have increased since 2010 across all major sectors globally, with an increasing share attributed to urban areas, which is interesting, and I'll talk more about that. In the scenarios that the IPCC assessed, limiting warming to 1.5 degrees requires global greenhouse gas emissions to peak by 2025 and to be reduced significantly by the end of this decade. So let me say that again. global emissions would need to peak in the next 3 years if we are to keep warming to the level that many countries have set as their target. Climate change is already affecting every region on Earth, from the tops of the highest mountains to the deepest seas. Places that have not seen a human footprint are feeling the effects of humanity's carbon footprint. This point makes me particularly sad for the wild places we're losing before most of us even know what is lost. Solving the problem requires immediate action, deep into every segment of society and widespread across the globe. And the next decades are critical. The truth is, we've never purposely undertaken anything as transformational as we need to solve the climate problem. We need something like a Marshall Plan for the entire planet, with the aims of decarbonizing energy, transport, industry, and manufacturing, building resilient homes and roads and power distribution systems, and protecting and restoring the natural areas that protect and sustain us. Oh, and we need to figure out how to remove large amounts of carbon dioxide from the air and the oceans so that we can eventually reverse the warming trend and address ocean acidification. Depressing stuff, right? Well, it is, and I know it is because I get a chance to talk about climate change with lots of folks in my various roles. And across the board, this conversation makes people feel like the problem is too big and too hard, and it makes them feel hopeless. This is particularly true for people the age of my children. Some of you are the same age as my children, who I find are heartbroken and so angry that they question whether it's ethical to bring children into this world. But before I convince you too to lose hope, let's turn our attention to a few things that make me think that the tides are starting to turn, bringing us in the direction of solutions to the problem. We can and are taking action at the national and international levels to address the problem. The Paris Agreement, I'm sure many of you have heard of it, and subsequent climate negotiations have increased ambition to address the problem. Coalitions of governments, academia, NGOs, and the private sector, like the Chancellor spoke of, are making commitments that can change our emissions trajectory, reduce deforestation, and spur innovation. And if we look at the US, we've just put into effect the largest climate action bill we have ever enacted as a country. The Inflation Reduction Act provides $369 billion for energy and climate solutions. Credible estimates say that the bill will reduce our emissions by 40% by the end of this decade. The incentives in the bill make it attractive for each of us as individuals to upgrade our appliances, our windows, our insulation, and shift to electric vehicles, but also for society to advance renewable energy production, battery storage, carbon sequestration, and hazard mitigation. And it delivers on two important fronts. It creates new jobs at competitive wages, including for apprenticeships in clean energy industries. And it brings underserved communities into the solution space with bonus incentives that encourage investment in EV infrastructure, efficiency improvements, and renewable energy production in low-income areas. Together with the previously passed bipartisan infrastructure law, which focuses on building and renovating our eroding infrastructure in climate-smart ways, we can turn the corner on this problem and set a model for others to follow. That transformation that I talked about, it can truly start to happen with the enactment of these bills. But let's be clear, the real action, the front lines of climate action are at the state and local level. This is where the impacts are being felt, and this is where we can sustain action over time. So take cities, for example. In the last round of IPCC reports, we found that cities and other urban areas are responsible for more than 2/3 of global greenhouse gas emissions through the production and consumption of goods and services. And even those not living in cities are impacted by urban systems through interconnecting infrastructure, trade, family ties, and the influence of water, food, energy, and waste. In cities, we can focus on sustainable production and consumption electrification with low emissions energy, and as places where we improve carbon uptake and storage and reduce urban heat with expanded green and blue spaces like permeable surfaces, green roofs, urban forests, green spaces, rivers, ponds, and lakes. And this makes the cities more livable and more enjoyable. In cities, we can focus on improving or retrofitting buildings to make them more efficient and upgrade existing public transport. And in new communities, we can do things right from the start and avoid future emissions by co-locating jobs and housing, transitioning to low emissions technologies, or avoiding fossil fuels entirely and providing energy efficient infrastructure and services. You may have heard recently about a place called Babcock Ranch in Florida. It was in the news following Hurricane Ian. Babcock Ranch is a primarily solar-powered community built to weather severe storms, and is one of the few places that did not lose power when Ian devastated many nearby communities. Their mix of adaptation and mitigation solutions is a powerful and just one example of how local communities can act on climate change. And I want to hit on one more important aspect of kind of state and local action that I think has huge potential. And this is touched on a little bit in IPCC reports, but is more informed by the conversations I spoke of earlier and the work we have going on at NOAA to create a climate-ready nation. This is the importance of city, state, and community level action as a magnifier of individual ambition. So what am I talking about? It's becoming clear that city, state, and community level action provides just the right level of engagement to magnify individual ambition and motivate community action. You have probably seen there is a groundswell of interest in doing something about this problem, but many people feel overwhelmed by the magnitude of the challenge, and just making personal dietary changes or addressing my energy needs or taking a different take on fashion and transport feels too disconnected from the huge transformation we need to make a difference. But changes in our community, working in places that we care about, this is an opportunity to make a tangible difference. And oh, by the way, to disconnect from the fits and starts that happen at the national policy level, which pendulums wildly with changing geopolitics. Subnational action can have real and lasting positive effects, which is why I'm so honored to speak with you, Secretary. I guess my message as I close would be, don't underestimate the effectiveness of community groups, university-based groups like the Climate Leaders Program, and civil society groups like Science Moms. These exist in every state and are very successful in engaging their communities to make a difference and motivate sustained change. Thinking, speaking, and doing at these levels is where the real action is, and it's time to devote more attention and resources in this direction. Keep an eye out for a Climate Smarts community initiative that we'll be rolling out at NOAA. But I just want to close by saying we can all work to make places we care about, like the beautiful state of North Carolina, resilient to our changing future. Thank you.
Thanks so much, Ms. Barrett. And now let's welcome our Secretary Advisor to give a follow-up presentation.
You're welcome to be out here until Secretary Biden. Okay. Don't feel like you're
Sounds great. Well, good morning, and thank you so much for having me here today. I can't think of a better way to start off a Monday than to be here with experts like Co and climate leaders like all of you who are working to make a difference on such an important topic. So this morning I'm looking forward to sharing with you a little bit about what we're doing at the Department of Environmental Quality on climate. So at DEQ, I'll start out by telling you our mission is to provide science-based environmental stewardship for the health and prosperity of all North Carolinians. And we do that in a number of ways. Most people know us for our regulatory programs that protect air, water, and land quality. But we also have non-regulatory programs that includes business assistance and technical assistance, grants for water and wastewater infrastructure, electric school buses, charging infrastructure, environmental education, and much, much more. And of course, the topic we're here today, we do a lot on climate, both in trying to mitigate the worst effects of climate change and also in how we make our communities throughout North Carolina more resilient. North Carolina has been a leader on these issues for years. We are no stranger to these intense flooding and storm events. In fact, we've had yet another example of this just about a week and a half ago with Ian coming through. But under Governor Cooper's leadership, we have set ambitious goals as a state for combating climate change with a reduction of 50% goal of reduction in carbon emissions by 2030 and net neutrality by 2050. A few weeks ago, I had somebody ask me, do you think we're actually going to meet these goals? And my answer to them was, we have no choice, which is why I'm glad all of you are focused on this. We have to use literally every tool at our disposal because we have to get creative. We've got to look at innovative solutions. We've got to look at both what's worked in the past, but we've got to look at a whole new future of what tools have we not yet thought about that we're going to have to employ in order to make a difference. And we need folks like you who can help decision makers make those educated decisions about how do we move forward as a state or as a country. And so over the last few years, I mentioned North Carolina has taken some bold actions. We've developed a clean energy plan that came out of Executive Order 80 that laid a roadmap for the state to transition to a clean energy economy and a clean energy future that works for everybody. We also developed the state's first climate risk assessment and resilience plan to identify the greatest climate hazards that we face across the state and to begin tracking our actions to address them. We also have developed the statewide greenhouse gas inventory to better understand where we are and where we need to go. Those key efforts were driven both by stakeholder input and by the scientific expertise we have in our state to make clear what North Carolina needs to do to address climate change and where we need to focus our work. But it takes more than plans. We need action. So just last year, we passed bipartisan legislation. I just want to emphasize that. Bipartisan legislation to turn recommendations into reality. House Bill 951 is a sweeping energy reform law that codified the state's goals of reducing carbon emissions from the energy generation sector 70% by 2030 and carbon neutrality by 2050. It took months of difficult negotiations between the governor and the General Assembly and Duke Energy, but we were able to reach a compromise that makes North Carolina a national leader on the issue. To reach bipartisan consensus on something of this nature is no small feat. Of course, the bill and the idea for this has started years earlier. Many of the elements of that bill came directly from the Clean Energy Plan that the department helped develop, which called for several initiatives and reforms, such as fostering long-term energy affordability and price stability for North Carolina's residents and businesses by modernizing our regulatory and planning processes, accelerating clean energy innovation, development, and deployment to create economic opportunities for both rural and urban areas, and ensuring a just and equitable transition to a clean energy economy. DEQ was directed to lead the development of that plan in October of 2018. And for more than a year, stakeholders from across the state, representing everyone from ratepayers to environmental and consumer groups to co-ops and utilities, and the scientific community worked together to create a consensus vision for the state. So that was just the beginning of that long road that led to House Bill 951. And throughout all of this, we are driven by three core tenets: to ensure that energy is clean, reliable, and affordable. Achieving all three simultaneously is not an easy task, but it's necessary. We have to do this all in a way that doesn't leave anybody behind. We know that climate change tends to disproportionately affect overburdened communities. And so passing House Bill 951 was just one step. So there was another step that was taken. So Governor Cooper last January signed Executive Order 246 detailing the next steps that we need to take to further reduce greenhouse gas emissions, prioritize environmental justice, and develop a clean transportation plan. Because transportation, by the way, is the largest sector of greenhouse gas emissions in North Carolina, accounting for nearly 36% of our total emissions. So to truly address climate change or reduce emissions, we can't just look at the electricity generation sector. We have to also look at how we're addressing the transportation sector. So that clean transportation plan process is going to be similar, or is similar to what the clean energy plan development process is. So I have similar hopes that we're going to see other big things come from it. We're taking significant actions as a state, and I'm confident in our ability to meet those goals, but government cannot do it alone. What we can do is align the social and economic incentives with the outcomes that we're trying to achieve. And that's where what the federal government comes in with the Inflation Reduction Act is really, really exciting and helpful. And Co talked a little bit about the record investment that we're seeing through that. I'm so excited about it. I mean, the $369 billion, let's think about that. That is more money than we've ever had to address climate and environmental justice in U.S. history. It's a comprehensive package that addresses it from many angles, including electricity generation, transportation, environmental justice, and so much more. So using those tax credits, and Co, as you were mentioning, looking at where the rubber meets the road from a state level, we're really excited to plan to see how can we put those dollars to work in the best possible way to have the broadest impact and achieve that estimated 40% reduction in greenhouse gas emissions nationwide by 2030. It's going to reduce greenhouse gas emissions on a scale that's demanded by the science and alleviate those environmental impacts that disproportionately harm low-income and minority communities. So it will empower North Carolinians to lower energy costs by taking advantage of those cleaner and increasingly more affordable technologies. And Co, you listed a few of these, but making sure we have availability for things like electric vehicles and rooftop solar panels and our energy efficient appliances and better weatherization for our homes. It's going to increase American energy security and supercharge the growth of domestic energy, clean energy manufacturing, which will create millions of good-paying jobs and growing the economy. And North Carolina is already seeing an influx in manufacturing associated with the clean energy economy already. It's huge for the country. It's going to help North Carolina meet our goals in a big way. We're still waiting for guidance from the federal government to find out exactly what we're going to receive and what the rules are going to be about how we can spend it. But we are already preparing and already gearing up to be able to deploy those resources in a very efficient and effective manner. I mentioned earlier, North Carolina is taking a coordinated and whole-of-government approach to climate change. And while DEQ has a critical role to play in this, we are not the only ones. The only way that we're going to make meaningful progress is to take that whole-of-government approach and for all of the agencies to work together. I mentioned DOT is currently leading the development of the Clean Transportation Plan. The Office of Recovery and Resiliency, which was created in the aftermath of Hurricane Florence in 2018, has been working to update the Risk and Resilience Plan and help us plan for a stronger and more resilient future in the face of increasingly frequent and intense storms. The Department of Commerce is working to promote offshore wind and recruit more clean energy industry to the state. So those are just a few examples of working with our colleagues in state government. Because under Governor Cooper's leadership, he makes sure, he reinforces this to us regularly, that we are all working together for that common goal. But we're also working with our local communities to increase resiliency to storm impacts. So with increasing flooding, with increasing instances of electricity outages that are related to those flooding, we're looking at a number of programs to help make our communities more resilient. One of those is the Resilient Coastal Communities Program, which is led by DEQ in partnership with other agencies and nonprofits. It's funded through a combination of state and federal dollars, and it's designed to provide grants and technical assistance to governments in the 20 coastal counties to advance shovel-ready resilience projects. We know that there's not a one-size-fits-all solution to resiliency, which is why we're working with individual communities to help identify which projects are going to help them the most as they are facing the effects of climate change. We're also using infrastructure dollars to upgrade our water systems. moving pump stations and equipment above flooding levels, adding generator backups to systems to ensure reliability during power outages. We've funded community solar projects to give 94 so far low-income households access to clean energy for the first time. There's so much more that I could talk about. I want to make sure we've got time for Q&A, but there's so many different wonderful programs that we've got going on, and so much more that we're going to be able to do as a result of that Inflation Reduction Act. We can't regulate our way to a cleaner future, though, so it requires partnership with the local governments, with the private sector, with academia, really across the whole society. It takes a whole of society approach to address this problem. We've been fighting this battle for a long time, but I am energized and I'm hopeful. A lot has changed. The fact that we have better public discourse now happening, we've got folks, like I said, I'm just going to go back to it, a bipartisan energy legislation, that type of action gives me hope for the future, that we've got more consensus around the need to take action. And it's not just for today. It's not just about our children, it's about our children's children. Co, you said that so eloquently about the fear that we're seeing from so many folks. But you know, I'm so, again, filled with hope because, and so grateful to be part of an administration that's putting this really front and center in everything that we're doing. I know that all of you are passionate about this issue, and we're gonna all have to work together to be able to really make a difference. And I'm really looking forward to discussion. Thank you.
Well, thanks so much, Secretary Beiser. So now we are entering the QA session. And so we invite our two plenary speakers sitting on the stage. And we would encourage everyone who has questions come forward. We have a mic at the front to receive questions. We also have Katie Hollinger. So Katie is one of our Climate Leaders Program Fellow. So she's also helping monitoring the questions online. So any questions so far? And maybe I can start a question to begin with. So I am a marine scientist myself. I study ocean circulation, and I do predictions for storm surge, hurricanes, and also look into the interactions between land, ocean, and atmosphere. So my question is, for a long time, we've been doing study just within academic. So we publish paper, we talk to our colleagues, but in this day and age, when we fight for climate challenge that require very strong collaborations beyond academic. So I wonder, as a government officials, both of you, do you have advice to us and also our students on how we can better contribute to the development of actionable and effective climate mitigations and adaptation strategy? How we can do better in helping this societal effort in addressing these climate challenges?
Yeah,
yes.
You can use the mic so that our virtual attendees can hear. That would be great. Should it just pop out, or you should, yeah, you should.
Okay. Yeah, I don't know. I think it's going to be in here. Okay. Hey, everybody in internet land. First thing I'll say, Roy, before I get to a specific answer to your question, and you know, Secretary Beiser's presentation really makes this clear. What students can do is become that workforce of the future that we are going to need to solve this problem. I mean, we need an army of climate practitioners who are going to be working in every community in this nation to help people to prioritize their needs, to find the resources that they can use to address their challenges. I mean, there are 30,000 communities in the US. So think about the number of people that we really need who are trained up to do the work. We also know that folks who live in a specific community are often a trusted agent. So going to your communities is really helpful as well. Because, you know, as as you mentioned, Secretary Beiser, the issue is a bit challenging, so having trusted interlocutors who can be working is also very important. So I just wanted to get that point out there because it's so key. At NOAA, we recognize there's a fair amount we can do from a federal perspective, but the real work on the ground requires, outreach, extension beyond what we can possibly do. I was actually struck by the Chancellor's remarks because I think there is the seed for what students or academics can be doing, working within these coalitions with the private sector, with government, because innovation is so key to solving this problem. We have a lot of the tools that we need, but things like carbon dioxide removal at the scale that's required, we're still working on those technologies. There's things called direct air capture, but figuring out how we deal with carbon dioxide in the oceans, we're really not there. So we really do need kind of a diversity of thought from people who come at the issue from a business perspective, who come at it from the understanding of academic knowledge, who come at it from community and civil organizations to affect the best solutions.
And I will second your plug for working in this area. I know for the department, we've got a lot of open jobs right now. So I'll make a plug for anybody who's graduating soon or looking to make a job change. Please consider coming to work for DEQ. I know Amanda is a DEQ alum as well, so she can tell you that it's a great place to work. But it's critical that we have folks who have the scientific understanding and interdisciplinary knowledge that you're gaining through this program in these jobs, whether it's local government, state, NOAA, or other federal agencies. So I'd say that's one big thing. Another thing that we've really been working on is more formalized partnerships with academia. So we started with the North Carolina Policy Collaboratory this year, an applied research fellowship program. And so our first 4 fellows are focused on forever chemicals right now, but I know that that's planned. We're looking at how to expand that to other disciplines here soon. But actually, Dr. Detlef Kanapi from NC State is one of those fellows. But we are really looking at how to make those connections, because what we're finding is there's a disconnect between the research that's happening and the decisions that are being made, and understanding what information is needed for making those decisions. I'll give you an example from a regulatory standpoint. There's specific information and studies that are needed in order to set regulations. But as we talked with researchers, they didn't realize what the requirements of those studies were. And so they said, well, if we knew that that's what you needed, then we could certainly tailor our studies to help you, and we can have more conversation. And so I think it's easy for us to each stay in our silos. And I'm using, academia and government as an example, but you could say this about any 2 sectors, and not understand kind of where the other is coming from, or what kind of environment they're working in, or what the others are needing. And so I think having more direct conversations, collaborating more, getting around a table together, and just working through these tough issues and brainstorming together, that's where we're going to have the breakthroughs, is having those types of both formal and informal collaboration moving forward.
Well, thanks to both of you. I like to just echo the point that you two articulated so well. I think that's really the communication, right? Engagement, and that's really one of the major purpose of setting up the Climate Leaders Program. So we have the Climate Leaders Fellows who will do the intern in the government agencies, in the industry, and then using what they learn from university and just start developing the practical solutions. So I think this is a great message to our fellows, and we keep doing such communication and working closely as a community to address climate issues.
Thank you very much for your presentation. It's really encouraging to hear the progress. I wanted to talk about, or find out some more about, what you think are the barriers for innovation in this area. I work in the area of biopharmaceuticals, and of course regulatory issues come up, economic issues come up. And those same 2 issues are present in climate change approaches. Are there things that we need to do that we're not doing in order to encourage investments or encourage individuals to invest in their own homes and energy requirements and so on? Is there more to be done in the political realm as well as the educational realm, right? Because a lot of this has to be information given to the public. Thank you.
It's a great question. I'm trying to think of where to start. From a, you mentioned, housing, how do you encourage consumers to upgrade? And, I think about things like our state building codes. How are we making sure that those building codes are taking into account what we need, both to make our homes more resilient to storms, but also just to make them more energy efficient and making them part of the solution rather than part of the problem. And so that starts with a lot of regulatory action. That's regulatory action that's outside of my department, but it's very, very critical. We certainly interact with it a lot through our weatherization program. Yes, the political will is part of it. We're seeing some encouragement on that front. We still have a ways to go. And part of that is helping everybody see the benefit that it holds for them to create that more resilient and climate-ready future. So we've got some work to do there. From a regulatory standpoint, looking at, I think about the recent Supreme Court decision with West Virginia versus EPA. For states like North Carolina, it has less of an impact since we've taken our own action, but I worry about the collective action. And I know that there was an effort to fix some of that by giving EPA some specific authority through the Inflation Reduction Act. So we're going to need more action like that to make it clear that this is something that we all have to do together, because North Carolina can do its part, but we need the other states, the other countries, everybody needs to be working collectively together. So I'll start there. I'll see if you want to add any.
Just to add to those excellent comments, Secretary. I mean, one of the things we need to do is just to speak about what opportunities exist. We have to get that knowledge into people's hands so that they know what exists to support action that they may be inclined to take. And I don't want to underestimate that, because often those of us who work on climate don't even talk about climate change with our families or our communities. We're so absorbed in that as our day job that sometimes we just come home and, whatever, watch Netflix. But, we really do need to use our voices to spur action and to spur innovation. The other piece that I'll maybe hit on is, and this goes back to your comments about silos, Secretary Beiser. Real innovation has to cross silos. If we come to a complex problem like climate change from the perspective of our discipline or even our university's approach to that question, sometimes we are only seeing this from a narrow, potentially biased perspective. But if we bring an interdisciplinary approach, if we invite all people from all different perspectives to the table to look at the problem from various sides, then we really open up the space for innovation. And I think a lot of the solutions that we have yet to kind of hit on will come from processes like that. Someone told me a really interesting statistic that when we were looking to solve the acid rain problem, we made a list of what we thought were the 40 top solutions to address this problem early on, right, before we hit on the solution. The eventual solutions were not on that list of 40 ideas. The eventual solution was not on the top list of 400 ideas, because you had to keep looking at it. Okay, maybe we should just look at scrubbing this right there at the source. So I just don't want to underestimate the importance of thinking outside the box, especially on a complex problem like climate.
I'm going to add one thing to that. That reminds me of something I read recently, that most innovation happens from folks who are not in the field. So that also points to your point of, finding partners to work together, and also looking at non-traditional partners. I would say think about folks from all segments. I heard that you all have one fellow who's actually looking at sports and climate. I think those types of just non-traditional partners and non-traditional looks at the issue are really important.
Thank you so much for joining us today. You mentioned, these monumental funding initiatives that are in place right now. How do we actually get that money into the hands of local communities and our partners? I know that at the university we need to create different types of educational opportunities to help work with these communities, but that's going to also take a little bit of time. So I'm just curious about how much you've been talking about capacity current and the ability to implement these amazing opportunities that exist for us.
Great question. Because if you've ever tried to read the bill, it's just treacherous to try to get through. It's all kind of a crosswalk to IRS code, so it's like change paragraph 25 and this, and it's very hard to decipher even for a person like me in the federal government. So we actually need to put the effort into deciphering out exactly what this means for groups. So as an individual, does this mean for me? And groups are doing this. It's not like it all has to be, it all remains to be done. But the federal piece of this is only a part, right? So as an individual, we can, starting next year, buy high efficiency appliances and do all the things we talked about in our speeches. And that's kind of a direct federal tax credit. And then there are interesting pieces in the legislation that if you're a tax exempt organization or you don't actually pay taxes, there are some innovative ways to still be reimbursed through direct payment or transferable credits. But a key piece, as Secretary Beiser was mentioning, is kind of the grants that are coming through the states, and that requires pending guidance from the federal level in order to get a lot of the really important money moving. So that's key, and I'm sure you have some plans for that.
There's two parts I think about with this question. One is building capacity of our ability to actually grant this money out. If you followed the department over the years, and you mentioned I'd previously been there when we had been Department of Environment, Natural Resources, and then we faced a decade of substantial budget cuts. And so we're left in a very weakened state to deal with a lot of extra money. But luckily we've had a dress rehearsal for this. So with water and wastewater infrastructure, through the American Rescue Plan, we received $2.3 billion for water and wastewater infrastructure. So that's given the department some opportunity to look at how we build capacity to be able to handle grants and getting out grants quickly. And we have successfully gotten those grants out in a really, I would say, record fashion, and getting, because if the money sitting in the state doesn't do anybody any good, it's got to be mobilized at a local level. And so we, within 6 weeks of the budget bill passing, we actually had our draft plan out, and we in one day awarded almost $800 million. Some of the money was earmarked. That included an additional $200 million that the governor had signed in the budget in July on a Monday, and we awarded it on Thursday. So we have really refined processes for how we as a department build a capacity. I will put another plug in. We need people to help do that work. So always looking for more folks to help us on that front. But then on the programmatic side, we also have some programs in place. I mentioned the Resilient Coastal Communities program earlier. That's where we're working with coastal communities to see what types of projects they need in order to make their community more resilient, looking at the fact that each community is going to need something a little bit different, depending on what issues they're facing and what the geographical challenges and opportunities are in the community. So we are working with those communities right now to identify shovel-ready projects for the event when funding is available. So that means that we're going to be right ready to go with a lot of communities, and that program has been getting more funds and expanding, so we are in a great place there. Our state energy office is also gearing up. We've got current programs that got a little bit more money through the bipartisan infrastructure law that they've already been gearing up for programs like weatherization assistance and community solar and other programs that help bring especially help bring clean energy to our low-income communities and minority communities. And so we are already kind of building up some reps there to be able to be ready for when that money comes down. And we are in very intense planning at the moment so that we can let it out the door as quickly as we can.
If I can just come back in for a second, it's really important that we make this work. We're never going to get money like this again. And if we don't actually achieve what we say we're going to achieve, which is 40% of emissions reductions by the end of this decade, we're all going to be in hot water, literally.
Really urgent. Yeah, Professor Kai. Yeah.
I'm Wei Jun Cai from University of Delaware. Well, first, thank you for both your excellent talk and this very active discussion, which actually answered some of my questions. But I'm going to ask anyway because it's something I think a barrier, one of the serious barriers for us to move forward is, how as academia we move into this climate solution, and how the government, state, local government could help. So I gave one example early this year, myself and a group of others, including Roy, we were responding to this call for carbon dioxide removal by additional venture. So one idea we proposed is use sewage, wastewater, and etching water to lime at base to that to take out CO2 and let the current ocean, river plume and ocean current take out to the Gulf Stream to make a big action. However, the first barrier I got is when I approached the city of Miami's sewage treatment. I said, can we access to your sewage pipe and maybe city of Philadelphia? And they wouldn't be interested or not even talk to me. I have to admit, being academia, we get too comfortable use the just propose a hypothesis and doing experiment, right? But move to talk to them, that first no deterred me. I didn't even try very hard, I have to admit. So there is this thing, and in the next meeting when I meet with Delaware's, state people, they say, oh, there are ways we can talk about maybe some local, smaller, sewage treatment facility could help. But anyway, these are the issues really I feel are very, how academia and industry and a government can work together, and would like to hear your comments. Thank you.
That's a great question, and I think the first thing that comes to mind is, again, strengthening communication on the front end. Some of this deals with trust. People get a little nervous sometimes, especially the regulated community, when we talk about doing things differently and worried about if they're going to be out of compliance or what that's going to mean. Is it going to cost them more money? And so that's where I think the state and local government partners can also come into a good place, but that's where you need kind of that multi-pronged collaboration, as you were mentioning. Working with on the front end, maybe identifying what some of those barriers are, but then, coming to your state and local partners to see, are there ways that we can help? Because if we're looking at, the art of the possible within our regulatory structures, because of course we also have to keep a mind out for that, we can maybe help identify solutions as well. But again, your point is well taken that innovation can ask us to do things differently. One thing that, change is hard and people get a little nervous when you start doing things differently, but we're gonna have to. So that's where I think having more, again, formal and informal dialogues happening all the time and building those partnerships and those relationships where we're working on problems on the same side of the table together can help reduce some of those barriers down the line when you're looking to test things out. So I know this is yet another example this morning of inspiring me to look for additional ways to engage with the university community that we're so fortunate to have in our backyard, so that we can help on some of these issues, because it's critical that we look at doing things differently, and we're not always the best at doing things differently.
Yeah, I guess I'll just iterate the same point that, it's really important to have an iterative process where people in academia or in NOAA, where I work, who may be, deeply exploring certain aspects of the climate solution space, have a chance to interact with the folks who really are asking for these solutions or who are dealing with the problems on the front line. And you made this point wonderfully, Secretary, earlier. You have to understand their context and what they need, and then to bring those requirements back into the academic process so that there is this iteration. Okay, here's what we know we can provide, here's what they need, how do we work together to kind of solve that? But I would also say many of the best innovations are not taken up the first time that they're presented to a potential user. Like, it seems like it really takes a lot of fortitude to just keep going. If it is a solution that actually can help solve the problem, it takes a hard shell to just keep going and going and going. Who is it? Maybe Miami is a gigantic place to start. What community has kind of identified that sewage is a potential part of a solution and go there?
Questions?
Hi, my name is Jethro Sanganzi, and I'm actually a Climate Leaders Fellow. So I have a question. It seems like there are a lot of stakeholders involved with making these large climate decisions. So if we have like an end solution for our, problems, how do we decide what weight, certain groups can provide to solve these issues? Because it seems like there are a lot of stakeholders, but some things might have higher priority than another, and how can that be quantified objectively?
Well, thanks for that question. That's kind of why I was saying that kind of a local scale or community level intervention is helpful, because you're right. I mean, this is a big, complicated problem with lots of stakeholders, across the planet. And if you kind of are rooted in a specific place, then it's easy to kind of say, oh, what are like Madison, Wisconsin, what are your priorities? Oh, you're interested in your aging building stock. You've got a river flowing through the middle of your city, so you're trying to build resilience to the, if you work in places where people have already set priorities that aren't necessarily climate priorities, but are their kind of development or their, livable community priorities, that can be a nice grounding piece upon which we respond with, oh, here's how we can help you to make this more resilient, or here's how we can reduce your energy costs and actually reduce greenhouse gas emissions from your transportation system. So that's kind of why I'm focused a lot on that, even though I work for a federal agency, as I envision my retirement, which will be in Western North Carolina, by the way. I think about wanting to work at that level and in that space.
I'll just emphasize, I think, to just add on to what you're saying, listening is so important, and understanding where everybody's coming from, and then trying to build a solution that then can get that support to be prioritized. That it's one thing, as you're saying, that the fortitude from the last question, the fortitude it requires to keep going and trying to, even if you get a no the first time, of being persistent, but understanding what they're looking for and how can you craft a solution that gets both the small p political support, if you think about the community that it's going to affect, and also be effective. So I think, it's a lot of the those skills of listening, collaboration, and facilitating change in a way that brings people with you.
Wonderful. I'd like to thank both of you for all the enlightening comments and suggestions, and also the presentation. At this point, I think we'll move on to the next session. Thanks to both of you again. Yeah. Okay, so we have 4 very exciting sessions coming up, and session number 1 is on the climate science, and I'd like to introduce three distinguished speakers in the first session. And our first speaker is Professor Marshall Shepard, who is a leading international expert in weather and climate, and also is the Georgia Athletic Association Distinguished Professor of Geography and Atmospheric Sciences at University of Georgia. So Professor Shepard was the 2013 president of American Meteorological Society, AMS. He is the 2018 recipient of the prestigious AMS Helmut Landsberg Award for pioneering and significant work in urban climate. In 2021, Professor Shepard made the history by becoming the first UGA faculty member to be elected to the National Academy of Science, National Academy of Engineering, and American Academy of Arts and Science in the same year. So his presentation is titled The Extreme Weather Climate Gap, Vulnerability at the Intersection of the New Norm. So our second speaker is Professor Gary Lachman. So Gary is a professor in the Department of Marine Earth and Atmospheric Sciences at NC State. His research focuses on the process and the predictability of high-impact weather system and how the systems respond to the climate change. So he's author of an award-winning textbook and the lab manual on synoptic meteorology. Professor Lachman currently serves as editor-in-chief of the journal Weather and Forecasting, and is also a counselor of the American Meteorological Society. In 2019, he was elected fellow of the AMS. The title of his presentation is The Future of Weather Extremes. Our third speaker is Professor Natalie Nelson, who is a professor in the Biological and Agriculture Engineering Department here at NC State. She's also a faculty fellow in the Center for Geospatial Analytics. Professor Nelson's research takes a data-intensive, management-focused, and interdisciplinary approach to the study of complex biological system dynamics in response to local and global changes. She is a recipient of the prestigious National Science Foundation Career Award, and her presentation is titled Rising Sea, Changing Runoff, and the Estuary in Between. So just like what we have done for the plenary session, so the three speakers will talk one after the other, and then we'll be having a 15 minutes QA sessions towards the end. So now I'd like to turn the floor to Professor Shepard for his keynote presentation. Please go ahead, yes.
I had to get off of mute as the Zoom mute bug bit me. So I'll go ahead and share my screen. Okay, and I hope that you can now see my slides, and I will get started. Thank you very much for the invitation to join you today. I regret that I cannot be there in person, but we are in the midst of our semester here, and there's quite a bit going on as well. I want to start by giving a big shout out to all of my former students or weather dogs from the University of Georgia that are sitting in the audience there today. I know there may be at least one or two, perhaps three there. So hello to my fellow University of Georgia Bulldogs and Go Dogs. I want to talk today about extreme weather climate gap, vulnerability, and the intersection. And I apologize for the typo there. That didn't seem to be on the previous version of the slide. But I want to talk about a discussion that has been really on my mind for the last several years, actually, and it's the intersection of extreme weather and vulnerability. But before we really get started, I want to set some ground rules. I want to talk a little bit about when I talk about risk and vulnerability and hazards, this is the framework that I'm talking from. And it's not really a new framework. It's certainly one that has been around. This idea of hazard And I'll use a bit later on the recent Hurricane Ian as an example of a hazard. Now, when we talk about exposure, the people, infrastructure, and societal norms, daily life are exposed to the hazard. And then we have vulnerability because there are certainly people and infrastructures that have greater sensitivity to the exposure to the event. And then finally, resilience is this idea that some people are better able to bounce back from that event, the adaptive capacity, if you will. And so this is one way to quantify risk when we talk about extreme weather or climate vulnerability. So that's the framework that I'll use. And as I just mentioned, Hurricane Ian is a poster child for what I will be talking about today. We had an extreme weather event that affected or was exposed to by all. But as you look on the bottom left here, there are certain communities within Southwest Florida, Central Florida, that will be disproportionately exposed, disproportionately sensitive, and have less ability to bounce back. And that's why I call that the extreme weather climate gap. So you can see this massive hurricane. Those of you that know my career know that I spent a good portion of my career at NASA's Goddard Space Flight Center working on satellite missions like the Global Precipitation Mission. So this is a rainfall footprint from the GPM product iMerge as Hurricane Ian was making landfall. And I show this because one of the unsung hazards, and I know that Professor Lachman and others will speak on this later, is flooding, the water aspects of hurricane. And that's a particular theme that will resonate throughout this particular session. So climate risk is expected to increase. This is a paper that we published in 2021. One of my former graduate students, Dr. Benita Casey, who's now at the NASA Goddard. And we thought about this vulnerability, risk, hazard, exposure framework that I just mentioned to you and mapped the vulnerability of every county in the United States by 2040 to climate risk. You can dig into the paper for the details, but we defined hazards in 2040 based on CMIP estimations of heat, or rain intensity, and drought conditions in that time frame. We did some analysis of vulnerability based on some social metrics projections as well as exposure, and we arrive at this climate risk index for the year 2040. Now, you may initially look at this and say, whoa, most of the country is not climate vulnerable because it's yellow, but that would be a poor interpretation of this particular graphic because this index is highly skewed to the right. So even where you see yellow, there's climate risk and vulnerability, but the purple, blue, and brownish colors are the most extreme at-risk counties based on our projections by the year 2040. And you can clearly see that many of those counties are coastal communities, urban communities, or communities in the Southwest where we have a significant portion of highly vulnerable populations. And so we have to keep that in mind as we move forward. So in 2019, I testified before the House Science Committee. And one of the things that I said very clearly is that the extremes are becoming more extreme, and that's what people feel. We talk about average temperatures and median, and we kind of get stuck in our climate science jargon. We have to talk a language that people understand, and they get the extremes associated with a flood or Hurricane Ian or an extreme heat wave. They don't really perceive the nuances of averages and 1 to 2 degree differences and so forth that we often get bogged down talking about as scientists. So is the DNA of climate change already in today's weather? Unequivocally, yes, from my view as a scientist. And I know Professor Lachman will talk about that and how it moves forward in the future. But it is clear to me that, for example, in storms like Ida, this is a look at flooding in New York City from last year. And you see the little graphic down here, something that many of us have taught and learned about throughout the years, this idea of more water vapor availability to the atmosphere as our climate system warms. I mean, that's basic physics. I mean, that's not debatable. That's not something that we can tweet and debate about. That's just physics. And so we know that these types of things are happening. And so in 2016, I published with several colleagues a report for the National Academy of Sciences. I was one of the co-authors on what we call attribution science. And so we know that some events are more attributable, at least in 2016, based on where the scientific literature was. I'm a member of the National Academy's Board on Atmospheric Sciences and Climate, and we recently did an update, a presentation on that report. And one of the things that we found, again, in that original report, and again, I'm not going too deep into this because I think Professor Lachman will, is we based that report on this notion that if we had sound physical principles on the phenomena, there were consistent observations of the phenomena, and the climate models can reproduce the phenomena. That was the 3 legs of the stool approach that we used in that report to arrive at this sort of ranking. So what we found is that reduction in cold events, increase in heat events, drought and rainfall, these were the events that had the most sort of certainty, ability to attribute based on those 3 legs of the stool. Now, you might notice that tropical cyclones kind of fell in the middle of the list, only because we have a pretty good physical understanding of what should happen as climate systems warm. But we have a truncated record, relatively speaking, and the climate models still don't reproduce, at least in 2016, tropical cyclones at the level that we'd like to. Severe convective storms, tornadic storms, fell very low. That doesn't mean that we ultimately will not conclusively determine that tornadoes are linked to climate change or are changing because of. In fact, there's recent literature that suggests that they are. But at that time, that 3 legs of the stool approach, we had to rank it relatively low. Now, let's talk about this extreme weather climate gap, because this is a figure from the National Climate Assessment Report from 2018, and I'm pretty sure it'll be in the updated version coming up. These are the communities that tend to have the highest risk based on the definition that I gave you earlier. Communities of color, children, older adults, low-income communities. And again, that's playing out in Hurricane Ian and many other communities. So my colleague, Robert Bullard, is considered the father of modern environmental justice. And I'll focus on the second sentence where he says, today's zip code is still the most potent predictor of an individual's health and well-being. Individuals who physically live on the wrong side of the tracks are subjected to elevated environmental health threats and so forth. Now, he's speaking from the context of some of those vulnerable communities having toxic industries and waste dumps and so forth placed in their environment. I've chosen to expand this idea of environmental justice to think about the extreme weather climate gap, or what I often will even call climate justice issues. So, for example, we know that the heaviest rainfall events are increasing in the U.S. This is data from the National Climate Assessment showing the increase or the percent change in the heaviest 1% rain events. It's happening essentially all over the country with the exception of the desert Southwest. One of the things that my colleague and former student Neil Debbage recently published, and it's relevant to the North Carolina where many of you are sitting, African Americans were 44% more likely to reside in areas at risk of flooding than whites in the Charlotte to Atlanta mega region, which we call Charlanta. In the MSA scale, when we bore down a bit, the Greenville-Spartanburg exhibited the largest risk with 80% of African Americans more likely to reside in the 500-year flood zone. That's a classic example of what I am speaking of when I talk about the extreme weather climate gap. We can come closer to Georgia. This is an analysis we did taking total flash flood warnings from the year 2000 to year 2021 here in Georgia. And one of the things that you see, and again, keep in mind this is flash flood warnings, the majority of flash flood warnings are issued in the urban Atlanta area, here Savannah, Columbus, Georgia, in an urban context. And we know that these are areas where a large number of those vulnerable 4 groups live that I spoke of early. So what is the weather climate gap? Just to kind of a sort of recap here of the definition, it is a disproportionate sensitivity to extreme weather climate events and a delay in the ability to bounce back by those 4 vulnerable groups, those relatively vulnerable groups. So you see another example. This is from a book chapter that I just published. It's in print now. It's in revision, I should say. This shows the urban heat island of Atlanta based on NASA satellite data. But then we decompose by race where people live in the metropolitan Atlanta area. And one of the things that you see is that African American, in some cases Hispanic communities, disproportionately live in the hottest part of the heat island. So there's a heat island within the heat island. There's what we call a racialized heat island. And that's what we defined in this paper. And so this is, again, another example of the extreme weather climate gap that I'm speaking of. So, I'm moving beyond, as a scientist, this idea of just telling you the doom and gloom of what's going on. I'm really thinking about solution space now, because we kind of know what's going on. It is what it is. It's here. We can't continue to talk about what's going to happen, although I know Gary's going to talk about it in the future context, but I understand the contextualization of why he's doing that. But I often see the media say, we're going to experience this, or this is what it will be like. No, it's here. And that's a real message I want to leave with you today. We have to sort of shift the narrative. But this is an example of an approach that myself, colleagues at Georgia Tech, Arizona State, and North Carolina A&T proposed to engineer cities for thermal justice. Literally, we want to fundamentally change how to engineer cities to either redistribute, repurpose, or reutilize that extra heat that I showed you in this graphic that are produced in cities and that disproportionately exposing people. This was proposed to a recent NSF ERC and a DOE urban IFL, neither of which were successful, but we're changing things around, going for round 2. Again, these aren't just the simple plant trees everywhere, paint the surfaces white. These are some fundamental and radical engineering approaches in terms of how we engineer cities. And so we have to think going forward, as I draw to a close, about this headline. A year after Hurricane Harvey, Houston's poorest neighborhoods were still the slowest to recover. That headline is just a manifestation of the extreme weather climate gap. And at the end of the day, I wish I had a more elegant, sort of scholarly ivory tower explanation, but the bottom line is that extreme weather climate gap is rooted in the wealth and income gap by race. And so when you see this breakdown, you then begin to understand why that headline exists. So I'll close with this statement by noted geographer Gilbert White. I had the honor of giving a lecture in his name from National Academies a few months ago, I believe. And he said the gap between the rich and poor is growing among and within most nations. The global environment shows signs of widespread deterioration. Both natural and social environments are increasingly vulnerable to catastrophic disturbances. And he wrote that several decades ago, I believe, but it's certainly relevant today. Thank you very much, and I look forward to hearing from you in the Q&A session.
Thanks so much, Professor Shepard. So I think our session will continue with our second speaker, Professor Lachman.
Thank you. Right, let's see, I need to get set up here. Will this work to advance the slides?
Yep, that's right.
Okay.
Yeah.
Okay. Okay. Okay, great. Okay, good morning, everyone. Well, I'm excited to have the opportunity to share some of our work here about future weather extremes, get a little bit into the climate science, and also talk a little bit about solutions. I wanted to mention Katie Hollinger, who's here. She'll be presenting a poster at lunch, one of the climate leaders, and she's doing some interesting work towards the mitigation side of the problem. So when extreme weather happens and my phone rings and it's the media, typically they want to know, what role did climate change play in this extreme event? It didn't used to be that way, but that's the question that always gets asked now. And the answer is complicated because there's lots of different ways that climate change affects extreme weather. It sort of changes the background environment, the jet streams, the storm tracks, the energy transfers. But it also changes the storm scale dynamics and the storm scale impacts. So there's a lot going on. And it also can change the amplification mechanisms that lead to extreme events in the first place. So the question that comes up a lot is, does warming, shift the distribution of a given weather variable, or does it change the shape of the distribution? And the part of that we're most concerned about is the tails of the distribution at the extreme side. So we'll talk a little bit about that today, but first we need to take a field trip. I don't know if the laser pointer works on here, but Lytton, British Columbia. Maybe some of you have heard of the small town of Lytton, British Columbia. And it's appropriate to mention today on Indigenous Peoples Day that it's home to a lot of residents in the First Nations community. But I grew up in Seattle, Washington, and Vancouver is well north of there. I don't know why this thing is just advancing. Let's see. So the city of Lytton, though, made headlines because it broke the all-time Canadian high temperature record on June 27th at 116 degrees Fahrenheit. This is a community north of 50 degrees latitude. Then the next day, it broke that record at 118 degrees Fahrenheit. And then the following day at 121. This is at 50 plus north. They weren't done. The town was evacuated. And then, unfortunately, 90% of the town was destroyed by wildfire the following day. It was a wind-driven wildfire. They barely had time to evacuate. There were 2 fatalities, and virtually every home in the community was destroyed by the wildfire. For this event, more generally, over 1,400 fatalities. And again, echoing Marshall's point about vulnerable communities, a lot of people in these areas don't have air conditioning. The image at right shows the International Space Station had the downward-looking thermal radiometer measuring the urban heat island in the Seattle-Tacoma area, and you can see very pronounced extreme heat in that area. So this was a remarkable event in terms of its impact. The Portland, Oregon area, look at the record. This shows their records, 116 degrees, just off the charts. Seattle hit an all-time record of 108, warmer than Raleigh has ever been. I mentioned the Portland 116. The Washington state record fell at 118 degrees. And then Quileute, Washington, over on the coast, their previous all-time high was 99. They hit 110. So these records are just off the charts. And we can ask, how did it happen? Well, meteorologically, there was a large upper-level high-pressure system shown on the left. We won't get too much into the meteorology, but we have to a little bit. On the right is the sea level pressure map that shows the surface highs and lows. We had a high inland and a low on the coast, and the combination of those weather systems led to strong low-level offshore flow that then descended and compressed and brought that heat all the way to the coast. So that was kind of the meteorological setup of this extreme event that was unprecedented. Now, within days, the World Weather Attribution Team concluded that this was maybe a 1 in 1,000 year event, and it would have been virtually impossible without anthropogenic climate change contributing. They said it contributes several degrees to the extreme heat. So there's an email discussion list of atmospheric scientists that I belong to, and that question came up again, and they said, well, one of our esteemed colleagues, who will remain nameless, they said, well, there's about 1 degree Celsius of warming during the last 50 years, which we can attribute to global warming, but this was a 15 to 20 Celsius anomaly, so how could global warming be the cause of that without some extreme amplification mechanisms? And then they concluded there do not appear to be any viable amplification mechanisms for global warming that would explain what happened. So there's still some debate in the community about this. And how do we understand that? How do we communicate that? And then what do we do about it? So I was thinking about amplification mechanisms, and I will propose a perhaps surprising one to you, that water was the amplification mechanism for this heat wave. Now, sometimes when you think about water and heat waves, you think, well, the soil moisture dries out and more of the solar energy goes into heating. That's not what I'm proposing here. Instead, we need to do a little bit more meteorological analysis and say, well, where did this hot air come from? And we can do backwards air trajectories starting in Seattle, Washington, and going backwards 6 days And if we follow those air parcels back 6 days, we find that a lot of them originated at low levels in the tropical Pacific, and then they rose as they moved northward. They ascended a lot as they reached the southeast Alaska coast, and then they descended as they moved westward again into Washington state. So that's sort of the history of this air. If we go back and just ask, okay, if this air, we can do a little thermodynamics and say if this air had been 2 degrees cooler initially, what would have happened to the latent heat content, the water vapor content? And the answer is that 2 degrees of cooling would have led to 6 degrees Celsius less latent heat in that air. And so that means that you have an amplification mechanism that could take you from 1 degree to 4 degrees Celsius or 2 degrees to 8 degrees Celsius, provided that the heat is going to be retained in that air sample. So is that what happened? Well, if you have air that's rising as it ascends, say, the mountains in southeast Alaska, and then eventually descends on the west side of the Cascades and Olympics, you're adding that heat as the air rises and that water vapor condenses, and then you're compressing that air back down to the surface, and you're realizing the heat that's been added by condensation. So that's one aspect of it. The second aspect, and this gets a little bit technical, but the red and orange colors on this map show where you have upper level anti-cyclonic flow. There's that upper level high that really drove this heat wave. And the purple contours there show where you have condensational heating from water vapor condensing in the atmosphere, and that's really what's driving that upper level high. And so we can do calculations, and the blue shading here shows where condensation is strengthening that upper level high. So that's another amplification mechanism due to water that's helping drive this extreme heat wave. So there's 2 things. We have, when you have a air parcel that rises and the moisture condenses and then you compress it, that adds heat to the air and can help make the heat wave extreme. But then you're also altering the dynamics of the event. And so there's 2 things going on here, both with the impacts and also just the nature of the weather event itself. And so, the point of this is that even modest warming can give you amplified impacts if you account for the change in water vapor. And so you can say, well, okay, this was a sort of an interesting and unusual meteorological pattern off the charts, as you said. Is it an isolated incident? And the answer is, well, if you look at headlines for the last few years, you see lots of examples of off-the-charts heat waves from Antarctica to Siberia. And some of these records are just completely unprecedented when you look at the historical record. And so, not saying that all of these had the exact same sequence that the Pacific Northwest heat wave did, but I think this is what we would predict, that because you're adding this amplifier to the system, you'll see more and more types of events like this going forward. So water in the atmosphere, we know it's a dominant greenhouse gas. We know that it plays a lot of different roles in kind of the science of climate change. But I study extreme weather events, and we also know that water vapor, and I've been studying this for decades, it energizes all different types of weather systems, the jet streams, atmospheric rivers, hurricanes, typhoons, and of course the precipitation associated with that condensation is impactful to society as well. So it's maybe worth kind of as a science communication point to talk about how much heat is released by water vapor to try to give you a more better understanding of this. You've all experienced this when you take your cold beverage out on a hot, humid day, and once water starts condensing on the outside of the glass or bottle, every gram of water that condenses is releasing 2,500 joules of heat. And you say, well, how much is that? Well, that's enough to warm a 12-ounce beverage by about 3 degrees. And note that a teaspoon of water is 5 grams. So that means a teaspoon of water condensing on your drink could warm it by approximately 15 degrees. Think about how much heat that is. That's why we use koozies, right? So that we're not trying to insulate the drink from the hot air. We're trying to prevent condensation from happening and heating the drink. But if you think about that, that small example and scale that up to a rainstorm or a hurricane, and think about the amount of heat being released. It's really a staggering amount. And that's why water is such an effective amplifier of extreme weather. NASA did this study showing that hurricanes release the energy of 10,000 nuclear bombs. Kevin Trinberth at NCAR showed that Hurricane Harvey released 4.65 times 10 to the 20th joules of heat. Those are numbers that are hard to understand, but that's why I like to talk about your beverage on a hot afternoon, because then you can think about how you could, what those numbers might mean in terms of how much energy is being released to the atmosphere. So again, getting a little bit technical, the problem is really that the water vapor content increases exponentially with temperature. So this graph here shows if you're down in the cool left side of that graph, and this is showing temperature on the horizontal axis and the capacity for water vapor on the vertical axis. If you're on the left side of the graph, a given amount of warming adds a little bit of water vapor. But if you're on the steep part of the graph, which is where we are in the area that's shaded blue, a given amount of warming adds exponentially more water vapor content. So that means that we have, we're sort of in the part of this curve where this amplifier mechanism is really effective. So we've done studies where you look at how water vapor energizes the jet stream. I'll skip that in the interest of time. The case of hurricanes is much more clear cut. The blue shading here shows where you have rich lower atmospheric water vapor content. Then the yellow here, that's rotating and rising air, and this is the example of Hurricane Sandy. And if we put that in motion, you can see how Sandy is really drawing on the fuel that's the water vapor that surrounds it in the lower atmosphere. And then the dark shading is sort of the outflow from the storm that you see appear at the end. But once the storm is removed from that water vapor source, then it will typically weaken, especially if it moves over land. So we can simulate a weather event. This is a simulation of Hurricane Floyd from 1999, caused extreme flooding here in North Carolina. And we could ask, well, what would that look like in the future? What would a future Floyd look like? And Katie Hollinger will share some of this work later in her poster. But if you just compare the water vapor content with the present day Floyd with the future Floyd, all else equal, you can run the same weather pattern, but use kind of what the water vapor would look like with some warming. You see, present day Floyd was bad enough, but look at the future Floyd. And this is an extreme, we have to understand how much the precipitation will increase in these extreme events so that we can prepare the infrastructure to handle that. So Marshall mentioned Hurricane Ian. If you look at the sea surface temperature anomalies leading up to Hurricane Ian just recently, you see that there's the warm colors across the western, the Caribbean through the Gulf of Mexico. If you have sea surface temperatures warmer than average, that means more water vapor available to help fuel the intensification of the storm and more water available to condense out as heavy rainfall. Also, you might say, okay, this is scary. We've got this amplifying mechanism. How can we prepare? Well, there's several things we can do. We can take weather models like I just showed for Floyd, and we can simulate the present day storm using a good weather model and compare it with observations. Then we can take the projections for warming to say, well, what would the future thermodynamics look like? And then rerun the simulation of the same weather event in a future climate. And then that way we can say, well, how would this extreme event look in a future warmer climate? And we've done that for a number of events. This sort of shows that in schematic form. We've done this for convective storms, for mid-latitude storms, for hurricanes. And there's a variety of ways you can do this where you measure the uncertainty in those calculations. Now, Katie Hollinger, again, advertising her poster for after lunch. She's done this for Hurricanes Matthew and Hurricane Florence. And we're working with the Department of Transportation. They're funding 2 of our students now to help make sure that we have resilient transportation infrastructure, because they need to know how far do we need to raise the bridge? What does the culvert diameter need to be? There's a team of people here. I see Kathy Delos here, state climatologist, Jared Bowden, Ken Kunkel. that are working with the Department of Transportation to help make sure that we have transportation infrastructure that can handle these future storms. So these are sort of design storms or examples of stress test storms that they can use to see what would the inundation look like. And Katie's, the Keats money has helped allow Katie to learn to run the hydrologic model that can really focus on the future inundation. So see her poster for more on that. With Hurricane Matthew, the yellow shading on this map, on the right is the future Matthew, on the left is the present day Matthew. Those yellow shading colors are 2.5 inches of rain per hour. So that's just an absolute deluge. And you see a much greater area of these really intense rainfall rates in the future storm. So even in terms of short-term flash flooding, this tells us something about what we would need to prepare for in terms of rainfall rate. So to wrap up, we've talked about a couple of different types of event, a heat wave and a hurricane. You'd think they'd be very different, but water plays a huge role in amplifying both of these in a changing climate. And the famous atmospheric scientist Michael McIntyre just recently wrote a personal essay on climate change. And he says that water vapor can reasonably be called weather fuel because of the latent energy released when it condenses. So global warming is global fueling. And I thought that was an interesting way to put that. The message is fairly straightforward. Warming, we know, increases water vapor concentration. You can do that in the laboratory. It's well-established physics, as Professor Shepard said. And water amplifies extreme weather. And we can show this for almost any type of weather system. We know that the amplification happens both to the storm dynamics, but also all else equal to the storm impacts. So those are the messages. The amplifier is water, and we need to prepare for how that's going to energize future extreme weather. And I'll quickly show some acknowledgements. Again, we really appreciate the Keats program, which is allowing us to do more in the way of mitigation and collaboration across silos, as was mentioned earlier. So I'll leave it there, and I guess we'll move on before the next, before the Q&A. Thank you.
Thanks so much, Professor Lachman, for the very interesting presentation. Next up, Professor Nelson.
All right, good morning, everyone. I think I'm gonna hold on to this. All right, well, it's an honor to be here with you all this morning and to speak alongside these fantastic, distinguished speakers. And today I'm going to be talking a bit about our work that's specifically focused on estuarine water quality. So my talk is titled Rising Seas, Changing Runoff, and the Estuaries in Between. And so to start, I know that we have a diverse audience in the group, so let's just touch on what an estuary is. So an estuary is a coastal waterway where you have fresh water that's mixing with marine waters. And these are really dynamic zones that support a lot of life. They're considered highly productive ecosystems. They're very important for different commercial and recreational fisheries, among a wide array of other types of ecosystem services. And here we're looking at an example of an estuary from here in North Carolina. It's the Albemarle Sound, which is located in the northeastern part of the state. So this is a satellite image showing you an aerial view of the sound. And so you can see here is in the sound, we have multiple rivers that are discharging to this estuary. So discharging means providing freshwater flows to the estuary. And you also have marine waters that are coming in from the Atlantic. So they're coming in through a break in the Outer Banks. And so you have then these multiple different water sources that are mixing. And estuaries, because of their positions in the landscape, tend to be uniquely vulnerable to water quality impacts. And when I say their position in the landscape, what I'm referring to is the fact that they're located at the ends of rivers. And in some cases, it's just one river. In other cases, it's multiple rivers, like what you have here in the Albemarle Sound. And so I say that that's a vulnerable position when it comes to water quality because rivers are cutting through really large landscapes. They're draining large landscapes, which we also refer to as watersheds. And in that process, they are carrying potentially pretty large volumes of what we would say is pollutant loads, or the total mass of a pollutant that's going to end up in a waterway. And so it's not only then the amount of water that's coming through, but it's also what types of lands are those rivers draining? So do they tend to be lands that have large pollutant sources, or are they more natural? And we know that stormwater runoff in particular is a dominant mechanism that's transporting pollutants from land to estuaries. And so a storm can be just a few inches from a rainstorm or thunderstorm, or it can be all the way up to a hurricane, for example. And so when rain then comes through, whether it's a small or a large storm, you're going to have rain that falls on the land surface, and then it's going to flush out some of the material that's located on those lands. And so here in the case of the Albemarle Sound, we know that there's really extensive agricultural lands that could be contributing pollutants that are related to fertilizer, for example. We also have quite a bit of development along the Outer Banks, and so there you can have issues with pollutants related to wastewater. But then you can also have water that's falling over natural lands that aren't necessarily then going to drain pollutants into the downstream estuary, but are at least contributing to that overall water quality signature. And so when you go estuary by estuary, you can see different types of water quality impacts, but they have this common theme of being located at that end position of an outlet, making them more vulnerable. And so because we tend to see then this accumulation of pollutants that can occur in estuaries, you also can see some pretty severe ecological and public health impacts. So for example, in the Albemarle Sound, we've seen increases in harmful algal blooms, so that's what's pictured here on the left. And there have also been shellfish harvest waters that have been closed for harvest because of concerns, in some cases, over chronic water quality impairment. And so because we know then that stormwater runoff is this dominant transport mechanism that's bringing pollutants from land to the coast, we have to be concerned when we see that in some areas we're expecting increases in precipitation. So here I'm showing a map that's showing the projected annual change in precipitation under a higher emissions scenario or business as usual in the time period of 2040 to 2069. And so here then the scale is showing you a teal color where we're expecting increases in rainfall relative to historical period, and then the brown is showing you a decrease. And so what I want you to focus in on is looking along the coasts. For the most part, much of the coast we're expecting to see increases in precipitation. So there are some notable exceptions like in the western Gulf of Mexico and in South Florida, but we're seeing that overall there are a lot of projections of increases. And in some cases, although this might look like a small increase, it's important to remember that because estuaries are at the end of these large watersheds, even a small increase in rainfall translates into a really large volume of water that ends up in estuaries. And so it's not only, though, the amount of rainfall that can lead to stormwater runoff, we also have to think about the types of land uses or the way in which we might have development or agriculture across the land that can also then contribute pollutants. And so one question we've been asking in my group is if we account for then spatial variation in both climate and land use uncertainty, which estuaries across the country do we expect are probably most vulnerable to water quality impairment in the future? And we're specifically focusing on nutrient loading. So nutrients would be things like nitrogen and phosphorus, what we tend to see in fertilizer runoff and also wastewater runoff. And this is work that's being led by Dr. Lise Montefiore, who's a postdoctoral researcher in my group. And so Lise developed a really holistic framework for thinking about vulnerability from many perspectives. So Dr. Shepard and I didn't coordinate, but he already gave you this great primer about vulnerability and thinking about exposure to different climate-related hazards. And so here I'm just going to focus in on what she had done with regards to modeling water quality impacts in the future. So this would be the exposure of an estuary to water quality change. And so to do this, she had compiled different climate projections as well as land use projections, and she used these projections to then run a water quality model that would estimate how much nitrogen and phosphorus is going to end up in estuaries all across the US. So in total, it was, I believe, 112 estuaries. And so she considered 2 different climate scenarios and looking at the outputs from 20 different climate models, so from the CMET5 ensemble. And she also considered 4 different land use scenarios, which was from the USGS4C model. And so she ran then all the different permutations of these different combinations of scenarios to basically understand what is the range then of possibilities with regards to nitrogen and phosphorus loading in the future to estuaries. And so here's just a snapshot of some of her results. So what we're looking at here is on the left, you have the total nitrogen results, or TN, and on the right, you have total phosphorus, or TP. And we're looking at the different coastlines of the contiguous US. So on the left, you have the Pacific coast, and then on the bottom you have the Gulf of Mexico coast, and then the Atlantic coast, North and South Atlantic coasts. And the different shapes you see are corresponding to watersheds. So these are watersheds then that are draining directly into estuaries. And the colors of the estuaries, the colors of the watersheds, I should say, are corresponding to the extent to which the average of Lisa's model projections show an increase, or in some cases there was a decrease in nutrient loading, but by and large we were seeing consistent increases across most estuaries. So the darker brown is indicating that there was a really large increase predicted by mid-century. And there's a lot of information here, but the main thing that I hope that you take away is that for the most part on the Pacific coast, we aren't predicting as much of an increase in nitrogen and phosphorus loading to estuaries, but across the Atlantic coast and then also the eastern Gulf of Mexico, we are seeing huge increases expected as a function of increases in precipitation, but also development, urban development that's predicted in these areas. And so that's where you see those dark brown colors. But we also know that it's really difficult to predict what's going to happen in the future, and it's important to consider then what is the full range of possibilities based on the best available information we have with climate projections and land use projections. And so what Lise also did was she wanted to look at not only what's the average of these different scenarios that she modeled, but what's the variation in those outputs. So to what extent are we seeing agreement across the models, the water quality model outputs? And so what you see here is on the top, you're looking at standard deviation of those model outputs for total nitrogen, and then on the bottom, it's for total phosphorus. And then it's broken out across different climate scenarios. And so the lighter color indicates that there wasn't much standard deviation, which means that there was more model agreement, which means that for the most part, for example, if you saw an increase in nitrogen or phosphorus loading, all the model outputs, if there was a low standard deviation, were consistently showing increases. But where you see the dark colors is indicating where the model outputs were kind of all over the place. So sometimes huge increases, sometimes small increases. And so here the main takeaway is that in the southeast, so across both the Gulf Coast and the southeast, but also in the South Atlantic, hugely uncertain. So there's a lot of uncertainty indicating that although we're expecting increases in nitrogen and phosphorus loading, it's not always consistent. And so from this study, we've had a few sort of larger takeaways, and I also have a bit of a call to action for potential collaborators in the crowd. So the first is that, of course, none of you will be surprised to hear that predicting future conditions in terms of how natural systems will respond is really challenging. It's important, but it's fraught with uncertainty. And so we really struggled with wrestling with this uncertainty to try and understand what useful information is in these model projections for our application. And so what we did see, though, in terms of the value is that we were able to identify then areas where we were seeing consistent increases that were predicted across our model outputs. And this was really helpful because it indicated that there is this spatial variation where you have the intersection of climate projection or climate change and also land use change that can lead to these different water quality outcomes. And we know in those areas where we're seeing pretty consistent model projections of having increase in nutrient loading, that these would be areas that are in more need of aggressive interventions for mitigating those nutrient loads in the future. But we also found that there are ways that if we had access to more data products that I think in many cases some climate researchers might be adept with. So for example, Dr. Lachman and Dr. Shepard, probably they have these methods in their tool belts, but for those of us who are working in applied engineering sciences, it can be difficult to access information such as having projections for climate projections that also account for storms and extreme events. So we know that storms are really important in terms of explaining water quality impacts. And right now in climate projections, you often don't have that level of resolution. And so we would need better access to products that do include storms and extreme events. And also, there aren't many land use projections that are available at a national scale. So you can sometimes find really nice localized products, but if you want to look at something a bit more nationally, it's very difficult to find projections that are out there. So if we had better access to this type of information, I think we could really improve our models. But we're also thinking beyond stormwater runoff. So I keep saying stormwater runoff is really important for explaining pollutant transport, but what we're starting to see is that there could be other mechanisms that could have this similar type of landscape flushing effect that could deliver pollutants to estuaries. And in particular, we're starting to think really critically about the role that tidal floods could be playing in driving nearshore contamination. So here you have a photo of a tidal flood that occurred in Beaufort here in North Carolina. And so we're seeing that these high tide floods are occurring with more frequency because of persistent sea level rise. And so as part of an NSF-funded project, we're starting to investigate then what is the water quality like in these floodwaters, these high tide floods, as well as then in the estuaries that are receiving the floodwaters when they recede. And so this past summer, we just started collecting data throughout Beaufort, which is located there on, like I mentioned, on the central North Carolina coast. And it has this really developed waterfront that's right there along a coastal creek. And this work is being led by Megan Carr, who's a PhD student. And so Megan then was out there this summer. The high tides hit in the middle of the night, so she was there like 2 o'clock in the morning collecting samples, a very dedicated scientist, collecting samples from the roadway to then understand what are the pollutants like in those flood waters, but then also collecting samples in the estuary to see what happens when you have those flood waters receding. Do you also see a water quality impact there? And so here we have just some preliminary data from this project. So on the top, we have daily rainfall. It's shown as these inverted bars where basically you see up to 3 inches of daily rainfall that happened throughout our study period. But in June, we had almost no rain, and then in July, we had quite a bit. So we were able to evaluate the effects of rain combined with tidal flooding, and then also tidal flooding on its own. And on the bottom, we have a concentration of Enterococcus, which is a fecal indicator bacteria, and it was the pollutant that we decided to focus on in this case because it has a lot of relevance for public health decision-making. And so the data are shown on a log scale, and the red line is telling you the regulatory threshold, where if you have a value that falls above that threshold, it indicates that there is concern then from a public health perspective. And the gray and purple dots are corresponding to samples that were taken from the coastal waterway, that estuary waterway receiving the floodwaters. And the green dots correspond to the concentrations of the fecal bacteria in the floodwater samples. And so there are a few things that we can already take away from this, although analysis is ongoing. So the first is we have this question of, are tidal floods driving nearshore contamination? And so all we can speak on is what's happening at our study site. But what we found is first that rain was causing much more of an effect in terms of driving nearshore contamination. And so this is to be expected given that rain is falling over a really large land area and can flush a lot of pollutants into the estuary. And so we had that as our benchmark. But then what we also found, though, is that these high tide flooding events, it seems like at our study site, we weren't seeing a huge impact of estuarine water quality, but the floodwaters that were in the roadway had very high concentrations of the fecal bacteria. And so this wasn't really what we had anticipated going into this. And so now moving forward, we're starting to also focus on what could be potential public health threats to pedestrians who could be walking through these floodwaters. In many cases, it just looks like puddles. It doesn't seem like it could be so bad, but they could actually potentially be carrying larger pollutant loads than what we had originally expected. And although right now we aren't seeing much of an effect on tidal flooding on the estuarine water quality at our study site, we know that as these types of floods become more and more frequent, we would expect that there would be an increased opportunity for more and more pollutant loading. So we think that this could still be an important mechanism to consider. So to conclude, there are multiple climate impacts that are colliding at the coast, which can create these really severe and vexing water quality challenges. And predicting future water quality impacts could be improved, we think, if we had improved access to probabilistic climate projections that could include storms, so basically a ready-to-use product. And also if we had more wide-ranging land use projections that would consider business as usual scenarios, but also then alternative approaches to land use planning. And then finally, we think that high tide flooding could be an emerging mechanism for driving estuarine water quality impacts, but this is an area where additional research is needed. So thanks so much for your attention, and I look forward to the Q&A.
Okay, now we're going to invite Gary and Natalie sit on the stage, and also Marshall join us on the Zoom call. So we have a Q&A session. So any questions from the audience to begin with? Yes.
Fascinating presentation. So happy that I got the chance to stay and listen. A question for you, Dr. Lachman, or maybe just a request for a suggestion. It's really clear that recent hurricanes have demonstrated the, really severe impact of heavy precip. But it's interesting from a Weather Service perspective, when we categorize hurricanes, we do it all according to wind speed. A Category 5 hurricane has to do with X miles per hour of wind speed. But increasingly, with water being such a strong driver of the impacts, is there a way for us to think about recategorizing or a supplemental category that talks about the precip effects, and would that be predictable?
Yeah, that's a great question, and probably Professor Shepard could weigh in as well. But I think the answer is yes. I think there's a lot of potential there. We have the National Hurricane Center, which will sort of hand off the storms once they make landfall. And then the Weather Prediction Center and the local National Weather Service offices take over. But I think sometimes there's something lost in that handoff. I know they've been working between the Hurricane Center and the other INCEP centers to improve that handoff. But yeah, we are sometimes overly focused on the track and the wind speed, and we should be thinking more about the flooding hazards. I don't know if it's worth a category, because it also depends on the size and the speed of motion. And so it's complicated, because you could have a relatively weak storm that's moving very slowly that could have a huge impact. And so how would you kind of build that into the categorization? I think it's hard enough to get the public to understand the cone graphic, but then to add graphics that include those additional complications, it may not lend itself to an easy classification scheme. But I do think we need to think about more creative ways to warn people about all the different hazards, and to let people know, even if you're outside the cone, you still need to be concerned and consider evacuation if those suggestions are made.
Yeah, I'd like to chime in on that if I could.
Yes, please.
Yeah, I've been writing about that very topic on and off for about 2 years now in my column in Forbes. The studies have been clear for some time now that water is the deadliest aspect of a hurricane, the storm surge and inland freshwater flooding. And we know this, and that has been a long-standing issue. The Saffir-Simpson scale is a wind scale. When it was designed, it was designed as a wind scale. So it does its job as a wind scale. But as your question sort of notes, it is not capturing the full suite of hazards. And the National Weather Service, I know, has moved to impact-based forecasting. But we have a category problem, in my opinion, in this society. There is such an inertia towards anchoring to category that it can be dangerous. I'll give you an example, even with Ian. Hurricane Ian, as it was approaching Florida, was a strong Category 4 storm with 155 mile per hour winds. And I just kept seeing discussion, will it get to Cat 5? Are they going to add 2 miles per hour so it'll be Cat 5? It didn't matter. A strong Cat 4 and a low-end Cat 5 were going to do the exact same amount of impact, no matter what category it was. So we tend to be sort of focused on that. I'll give you another example to your point. Hurricane Harvey in Houston in 2017, the majority of the rainfall that fell from Harvey it wasn't even a hurricane anymore. It was a tropical storm. And so this sort of idea, oh, it's just a Category 1 or it's just a tropical storm, can be very dangerous, because I do rainfall. That's what I do. And we know that some of the most devastating water flood producing storms were not high category storms. They were slow movers. Those of you in that area in the Carolinas certainly remember Hurricane Florence, or Tropical Storm Florence, from a few years back. And the damage that it did to much of the agricultural, poultry and I guess pig industry there in the coastal and tidewater areas. So there are a couple of studies in the literature. Jason Sinkbile at the University of Alabama has developed an all impacts-based metric. We published a paper in the Bulletin of the AMS just a couple of years ago, led by Daniel Wright, on a new metric or way of conveying the rainfall threat from hurricanes. So there is some scholarly literature out there on exactly your question. But as the National Academies pointed out several years ago, they're still sort of languishing in ivory tower land. They haven't crossed the fence into the applied world. And so I think that we just need to continue to see more impact-based forecasting. The categories aren't, the Saffir-Simpson's not going away anytime soon. It has too much inertia. But I did write a column just this week also to allude to Gary's point, questioning whether we should get rid of the cone even. The cone sort of creates this bias that either I'm in the risk or I'm not in the risk. But in Hurricane Ian, from Friday through landfall the next week, the region that ultimately was impacted was always in the cone. So there was a 67% chance that the storm center would be somewhere in the cone, but that's not how the public interprets what the cone is. So we definitely have some ways to go with hurricane communication.
Do you have a comments to add on? Okay.
Thank you for an enriching panel. And just to personalize this a bit, the folks in Volusia County, Florida, the place where I grew up, could have cared less if Hurricane Ian was a Category 1 storm when it made landfall. They did care about was that it dropped 24 inches of rain in the span of 12 hours. Folks who never thought their homes would flood lost everything. It's a really alarming fact. And even more alarming during the panel, Dr. Lachman, you showed a graphic projecting, I guess, Hurricane Floyd's trajectory with projected future models of warming. There was a dot there that said 2.5 times in yellow. I just wonder if you could kind of quantify what that 2.5 times was referring to, and invite Dr. Shepard and Nelson to kind of reflect on your own work in these very tough times and conditions. How does that change if the impacts are 2.5 times what they are now? Thank you.
Thanks for that question. In the graphic I think that you're referring to, I was going too fast, and so I should have explained it a little more clearly, but that was actually for Hurricane Matthew, and it was showing some work that Katie did, looking at the hourly rain rate, and the yellow shading is where you're getting 2.5 inches of rain per hour, which is an astounding amount of rain in 1 hour, and that happened in the future version of the storm, but not in the present day version of the storm. So yeah, I think that the point is still well taken that the impacts would be significantly increased. And I'll let Marshall and Natalie further comment.
Natalie, you can go first.
Okay, thanks. Well, I think, yeah, it's an important point in terms of when we're, in my case, since I'm focusing on water quality, the intensity of a rainfall event is really important in understanding to what extent you are going to see really fast flushing of the landscape, to what extent is stormwater infrastructure going to be overwhelmed, is wastewater treatment infrastructure going to be overwhelmed. And so being able to have then access to projections, for example, that would allow for us to test out these alternative scenarios of having different levels of intensity, I think is a natural next step in our work to really understand what are the risks for water quality impacts, especially because I think that what we're showing in our current maps is really underestimating what is likely to actually happen when you account for differences in storms.
And I would just add to that, when we think about flooding, particularly in an urban context, flooding is not just a function of what falls from the sky. It's a function of the urban impervious surface and the assumption of stationarity in much of the stormwater engineering design in cities, which assumed that the rainstorms, either in a garden variety thunderstorm in the afternoon or a hurricane, would be the same in 1970 as it is in 2022. And we know that it's not. There's much more intensity to the rainfall, falling on imperviousness that limits infiltration and increases runoff or conveyance into streams and so forth. And so we have to think holistically as we think about the fact that the science is telling us that we're going to see or are in and will continue to be in this generation of heavier rain events. We now have to start an adaptation plan. We need adaptation. We talk about mitigation, reducing CO2 and all, but for flooding, we need adaptation plans because we know what's coming. We have to think carefully about sort of engineering with nature solutions, which we're thinking about here at UGA, porous surfaces, pavements, and so forth, and the impacts. We can look at Jackson, Mississippi just recently, an environmental justice nightmare. related to rainfall. Heavy rains overwhelmed the storm of the water treatment facilities and left that city without water in some cases for a week to two, many of which were part of the extreme weather climate gap that I talked about. I am working on a proposal right now with Catherine Coleman Flowers, who's the chair of the White House's Council on Environmental Justice, looking at what we can say about changes in extreme rainfall, soil moisture, and water tables as it relates to septic systems. Much of the southeastern U.S. is related to septic systems, and there are significant failures in extreme rainfall. So to your question, again, as scientists, we're reporting what's happening in the rainfall. Now we have to start looking at our infrastructure and societal aspects and develop adequate and appropriate adaptation plans.
I could just make a quick follow-up point. I wanted to do a plug for the Keats support that we've had. And again, I keep mentioning Katie Hollinger, but the Keats support enabled us to work with a new professor at UNC named Tony Sebastian. And Professor Sebastian has these future land use projections so that you can then take a hurricane simulation and look at what areas would inundate with a given type of land use. And so I think that's the type of work we need to be doing to, cut across the silos and start thinking about what type of mitigation would actually help reduce the inundation.
And to follow on Gary's point, I think especially for the low-lying coastal regions, nowadays when we talk about the sea level rise, it's actually coming from the storm surge from the ocean, also from the river flooding, as well as from the large precipitation. So this is so-called compound flooding. And some recent research shows that in the high emission scenario, the compound flooding event on the global scale will increase by 25% by the end of the century. So apparently this is not just an atmospheric science issue, it's not just the oceanography issue, it's not water quality issue, it's required this joint collaboration cross-interdisciplinary to address the compound flooding. And of course, that has an impact on the water quality, on the coastal infrastructure, and also on socioeconomics. So this is a cross-cutting issue that require many of us to join force, join expertise, and to start addressing this emerging and high-impact climate challenge. Yep, so we have one quick question from Paul, Professor Paul Liu.
Yeah, thank you. This is Paul Liu from MES, same department with Roy. And thank you very much for the three wonderful panel, great talk. Now we understand the impact of climate change is not even. From the coast, you can see the different watershed have different load, and also from different topographic. And also appreciate very much of Dr. Shepard's strong message that climate change particularly have a severe impact to the low income and the poor community, and particularly for African American community, that's much, much amplified, some kind of same message. But my question also is for the global perspective, like this year we had so many about Pakistan, the flooding impact, and also in those the high latitude area, like the Arctic coastal region and Greenland. So when we're there, the people cry. They said, if for those people don't believe climate change, let's come here to visit Greenland. They can immediately tell it is real, it's happening now. So my question to Dr. Shepard, so what's your information? Do you have a list of the high vulnerable country or area globally, not only in US, in city-wise, urban area, but how about the big picture for us? Which area is the most vulnerable, or we should have invested for education money or help? Thank you.
Well, I will start that question. My colleagues might be able to weigh in from their perspectives as well. We've only done our analysis on the US, but I certainly I can give you my thoughts on it just from my ear to the ground. It is very clear to me that low-lying coastal communities globally will experience inundation that will likely drive many of the people from those countries out of those countries, the so-called climate refugees that we've heard so much about, displacement of people. I think areas in North Africa and Middle East, where we already have significant water scarcity issues, will be, sorry, I need to plug in here. My battery's going to die on my laptop. Will also be of significant concern. And if you go and read a report that I did with the National Academies on national security and climate change, that's of big concern, because when we start to see sort of some of these sort of regions destabilized by increased drought, heat, and so forth, you start to see people displaced from those places into Europe and other places, and it kind of amplifies or compounds immigration and sort of social strife issues already within those countries. So they're sort of threat multipliers or threat amplifiers as well. So, again, the simple answer to that question really, if you use the metric that I use for the U.S., look at countries, the least economically developed countries around the globe. And those are the ones that you're going to sort of clearly indicate vulnerability. But I also think very developed countries in China, highly urbanized spaces, the cities will also feel the brunt of these storms as well. But that's just my thought. My colleagues may have additional thoughts.
Truthfully, my focus has really been on the United States, and so I think I would struggle, and I'd be stepping outside my expertise to touch on other parts of the world. But at least following up on what Dr. Shepard said, I think that definitely coastal communities, I'm from Florida, and when I think about risks associated with sea level rise in Florida, I find it completely overwhelming, truthfully. It's such a grand challenge. And so I thought that the comments regarding coastal communities and low elevation communities, it really resonated with me.
I don't have too much to add, but certainly for tropical cyclones, places like Bangladesh are just incredibly vulnerable. And it's hard to know how to mitigate in those places because it's so low-lying and prone to flooding from cyclones. But also the kind of the geopolitical destabilization aspect that Professor Shepard mentioned. I've seen studies that linked the Arab Spring geopolitical changes to the Russian heat wave that preceded that and drove up food prices and led to unrest and protests that then amplified. So all these things are interconnected, and it's important to understand and how to prevent the worst of the disasters from happening. But that's all.
Great. Well, thanks so much. I'd like to thank Professor Shepard on the call and Professor Lachman, Professor Nelson for your very insightful presentations and also a great discussion this morning. So with that, I think we conclude session number 1. So when do we come back? Sure, yes.
Thank you to all of our speakers. And it's great to turn around and see faces again. So we do have a 20-minute break. So I ask that you be back in here at 10:55 to start our second session. Upstairs where we had breakfast this morning and where we'll have lunch later, there is still coffee and snacks that have been brought up there as well. So stretch your legs, maybe get some fresh air, and we'll see you in 20 minutes. Thank you. Goldenrod hallways, the golden arches, if you need a restroom, this floor or upstairs as well.
tries to do something. Still here.
There we go. Okay. All right. Thanks, Amanda.
Yeah. Thank you for bearing with us.
Yeah. All right. Well, good morning, everybody, and welcome to session 2, which is the ecosystem responses session. I think it's on, Roy. Yeah. Okay. My name's Dave Eggleston. I'm a professor in the Department of Marine, Earth, and Atmospheric Sciences, and also service director of NC State's Marine Lab, known as CMAST, located in Morehead City. Before I introduce our speakers, I just wanted to provide a somewhat broader context for the presentations. Okay. Check. There we go. Okay. All right, so before I introduce our speakers, I wanted to provide a brief, somewhat broader context for which the different speaker examples would illustrate. And so just as a reminder, the oceans absorb, oceans absorb 1/3 of the CO2 emissions and approximately 90% of the excess heat. Marine ecosystems and species are facing critical stresses and threats due to sea level rise, ocean acidification, deoxygenation, severe weather events, shift in species distribution and habitat suitability, changes to food webs, altered biogeochemical cycles. And what I think is one of the more important challenges is challenges to policy and management. So in terms of some of the solutions, one theme that we've heard about this morning, we're going to hear about it again in this particular session, is managing for a new normal, and that is managing for resilience. And so there are a lot of different ways to think about resilience. I just wanted to touch on one, which involves these nature-based solutions. And one way to think about this is a way to promote the extensive and connected ecosystems that are illustrated right up here. So these are all coastal systems that are inextricably intertwined with the climate. So this marsh, oyster system, seagrass, mangroves, coral reefs. So for example, all of these systems are involved in the carbon cycle, water cycle, biogeochemical cycles, and also can serve as essential fish habitat. And these habitats are often found in mosaics. So it's not just one single habitat. And a great example right here would be this salt marsh system. So in this case, these plants are photosynthesizing. They're taking up carbon, releasing oxygen during the day, respiring at night. They help to desynchronize floods. So think about them as a sponge. So they're absorbing these flood waters during those events, but during droughts can start to release that water. This oyster reef right here, which is actually man-made living shoreline, is helping to reduce some of the storm-driven erosion that might occur to this marsh, allow it to accrete, and provide a lot of the ecosystem services such as water filtration and essential fish habitat. And so with that, I'd like to come back and introduce our speakers. First up is Dr. Cisco Warner. He's Director of Scientific Programs and Chief Scientific Advisor for NOAA's National Marine Fisheries Service. In this capacity, he leads NOAA fisheries efforts to provide the science needed to support sustainable fisheries and ecosystems and to continue our nation's progress in ending overfishing and rebuilding fish stocks. Prior to taking his position with the National Marine Fisheries Service, he was the director of the NOAA Southwest National Marine Fisheries Lab in La Jolla, California. Prior to that, he was director and professor of Rutgers Marine Lab, And prior to that, he was department head of the marine science program at UNC Chapel Hill. Our second speaker is Marcelo Ardon. Marcelo is an associate professor in the Department of Forestry and Environmental Resources at NC State University. He received his PhD in ecology from the Odom School of Ecology at University of Georgia and his BA from Gettysburg College. Prior to coming to NC State, he was an assistant professor at East Carolina University. He has a very consistent track record of NSF funding. He's an NSF Early Career Award winner and has a very impressive track record of high-impact publications. And then our last speaker is Chris Osborne. Chris is a professor in the Department of Marine, Earth, and Atmospheric Sciences. His research spans carbon and nitrogen cycling across the aquatic continuum, using optical and chemical properties of organic matter to assess the effects of human activity and climate change, and especially extreme weather events, on water quality and sustainability of rivers, estuaries, and the coastal ocean. And prior to coming to NC State, Chris was a research chemist at the U.S. Naval Research Laboratory in Washington, D.C., and he earned his BA in geology from Indiana University and his PhD from Lehigh University. And so with that, I'd like to invite Cisco up.
You, Dave, and Roy, and Amanda for the kind invitation to be here. It's, as Dave said, I used to be down the road about 15 years ago or 10 years ago, so it's nice to be back in North Carolina. Go Heels. Sorry, it just slipped out. I didn't mean to say that. I couldn't help it. But anyway, it really is just great to be here. And the topic today and tomorrow really couldn't be more central to a lot of the things that are keeping us up at night, if you will. And that's, at least in the part I work in NOAA, which is in NOAA Fisheries, is this whole concept of how do we evolve, our science to provide the right advice. And in NOAA Fisheries is one of the line offices that actually does deal with regulatory components of our work. And so this sense of understanding what's going on in the environment and how to translate it into advice to management is something that is a challenge. And perhaps today I'll get a chance to perhaps give you a little bit of a sense of how we're doing it and where do we need to go and what do we need to think about. So a lot of presentations this morning were really excellent in terms of pointing out a couple of things. One is that things are changing. And so the picture on the left is actually a 1,000-year record of northern hemisphere temperature, but you can pick any record. You can go 200 years, 50 years or whatever. We know that things are changing. And that means that we're shifting from basically what is referred to as a stationary system to a non-stationary system. And non-stationary systems are rather different because, they're not fluctuating about a mean. It's not just ups and downs about an average, but the average itself is changing. The variance itself is changing. And we've heard about that with the extreme events falling outside of the normal baseline of variability. So this is rather a challenging problem statistically, forecasts, et cetera. So even if you just want to get into the nitty-gritty mathematics of it, as you go from stationary to non-stationary systems, you have a challenge in front of you. The other thing that was pointed out is that, the outcome is quite variable. And so the picture on the right says, rather than managing for stability, which we kind of could, if you said that we're managing about a mean, and we know that things go up and down, we can manage for some stability. We know we can't do that anymore. We have to manage for variability. And so that means thinking about how do we do projections in a quantitative way going forward. Non-stationary systems. I'll just give some real quick examples of what we see is happening to the systems that we're looking at. The picture in the top left is off Alaska. If you look at the purple, it's where the distribution of the Pacific cod is. And that pinkish area there is a bottom water cold pool that they refer to. And the disappearance of the cold pool has caused shifts of several thousands, almost 1,000, I should say, almost 1,000 kilometers in about 10 years of the distribution of the fish. I mean, we're talking about things that are really remarkable in terms of an interaction, if you will, between a physical barrier, quote, a physical barrier, the temperature, and the distribution of the fish. The picture on the top right has to do with North Atlantic right whales and the relationship of where they can find their primary source of food, which is that little thing up at the top, which is a copepod. It's a calanus, and it's now shifting further north because it's there. So it's a change in food in the trophic levels, if you will, that has caused a shift in what we're looking at. The picture in the bottom left, actually, it relates to the talk that Natalie you gave this morning about, how do we, what kind of things can we see by changes in nitrogen and phosphorus input from the coastal ocean into the coastal, from the watersheds into the coastal ocean, and that might have to do with changes in, for example, harmful algal blooms and such, and that also we're seeing a change in frequency and magnitude of these, and that also brings the whole concept of Earth system as we begin to couple not just the ocean, we're looking not just at the ocean, not just the land, not just at the atmosphere, but we actually have to look at the Earth system in a coupled way. And the last one at the bottom right is sort of an indirect part of climate change, which is we know that wind farms are being proposed. You see the map there, and these are proposed lease areas along the East Coast. It might be a dated map, but the sense is that they're going there. And you see a picture there on the bottom right in terms of a ship and these wind farms. And how is that going to affect our ability to understand those systems, those ecosystems, and also how we're going to be able to perhaps continue prosecuting the fishery in those areas. So these are things that are happening as a result of the changing climate. In terms of models for living marine resource management, LMR, living marine resources, in general models, again, because things were fluctuating about a mean, there were really no long-term trends or no regime shifts in general included in these models. There were inclusion of random year-to-year fluctuations, perhaps some autocorrelation, but there were some assumption of prevailing environmental conditions. And we know that's not the case. We know that we're moving not just into regime shifts, which is something we've looked at in the past, but as I said, a non-stationary part of what we're looking at. If anything, what we're looking at is moving towards what are called management strategy evaluations, which I'll get to in a second, which really brings in everything from the different objectives, the different ocean use sectors that are trying to work in this changing ocean environment. How do we make a decision, which was a subject of the conversation this morning? How do we make a decision about how we're going to manage the system given that there's so many potentially competing or overlapping needs to that sector? So we've moved from what we're saying from it would be nice to know, what things are because we could make some assumptions about stationarity to now we need to know what these processes are. So we've moved again from a different way of looking at it. And the picture on the right is a simple way of saying we know that the trends are changing, the amplitudes of what we're seeing as well as the frequencies. And so what I'll talk about is three things today. Real quick, I'm going to give you an example of sort of a tactical way that we do stock assessments nowadays. Also now needing to think about the long term. How do we project out into 10, 20 years out, and how do we think about that? And also talk about something that we're just establishing, which is what we refer to as a climate ecosystem and fisheries initiative within NOAA. So I'm going to give a simple example here, and simple is a deceiving term. This is actually quite a bit goes into this thing. I'm going to give you the highlight of what this is. And it has to do with this fish called the yellowtail flounder. The distribution is, along the middle Atlantic bight. So you see Cape Hatteras there, it goes up to Cape Cod roughly. And you see the picture in the top left, there used to be, a certain amount of catch. Now that catch is no longer at the levels it used to be. The spawning stock biomass is also dropped. In other words, how many fish are there, if you want to think about it. And recruitment is also dropped, which is how many new fish are getting into the population. So you see basically that from the 1990s forward, the population has reached pretty low levels. Despite the fact that there's obviously restrictions in fishing, et cetera, the question is why are we not seeing more fish coming in there? Where is the recruitment? Where is the spawning stock biomass? And it's related to that cold pool that I have on the right there. The cold pool is in this case, it's a relatively simple to understand. You get the winter time, the water column is well mixed, everything is cold. You get the winter time, the surface heats up, and then you have the cold at the bottom. And so that's how you form the cold pool. That's sort of the back of the envelope explanation of it. But there's more to what that cold pool does. The cold pool varies. We've noticed that it's decreasing in size, it's decreasing in intensity, and it's also the temperature is changing. But the cold pool is important because it's hypothesized that the late state larvae and early juveniles settle to the bottom of this cold pool and depend on this cold pool in order for them to recruit, which is to make it to the next year and to become part of the population. And so the hypothesis is that the changes in the cold pool are what affecting what's happening, why these fish aren't coming back despite the regulatory efforts to do that. Picture in the bottom right just simply says that whether you look at the spring or the fall bottom temperatures, you see generally a trend of either warming or a flattening at a higher level temperature. So we developed what's called a cold pool, the folks who did this developed what's called a cold pool index. They looked at many, many years of data as well as model runs, and I'm going to get into the model bit here in a second, and began to look at what's happened over the last, say, 30 years or so to this cold pool, which is this feature that is hypothesized to drive the yellowtail flounder. And what we've seen is that there is the intensity, the persistence, and the volume, if you will, have all changed. It's gotten warmer. It's not as cool as it used to be, perhaps. The persistence, it doesn't last as long, and the spatial extent is smaller. And this is something that was done both, using observations, which is the picture there with the ship, as well as model simulations, which is the other diagram there. And what we find is that, okay, given that we have developed this index, how do we incorporate this cold pool and assess whether, we can say why this recruitment is lower? And again, I'm simplifying it, but the idea was that we can look at the effect on carrying capacity, in other words, a suitable habitat, the effect of the cold pool on larvae, the effect of the cold pool on later stages of mortality, or that would affect mortality or growth of later stages of the population. And you can do that by relatively simple formulations. And again, there's a lot behind, from where I started to those expressions there. There's about 25 pages of algebra or something like that. But anyway, so there's a lot that goes into how you get there. But what you find is really, what's the bottom line here? The bottom line is that we found that these bottom pictures here with the 3 dots and the ellipse around them, these are the values of recruitment of including environment versus not including environment. So the message here is that if you include environment, the recruitment is a lot lower than if you didn't include environment. It's not surprising. Environment matters. But the point I was trying to make in these slides is that we are now at this point of, it's no longer nice to know that this matters, but we need to know, and we need to try to find ways of how to include these temperature effects, in this case temperature effects, into the recruitment, and perhaps why is it that the populations may not be rebounding as much as we had hoped, or as we had planned in the rebuilding plans. So that's number one. Environment matters, and we have ways of moving forward. The second thing I want to say is that we noticed that using the model formulations, or interpreting or inferring the temperature from the models, gave better results than the observations. And that's not that the observations aren't good, it's just that the observations are limited. So with the models, you can take a much longer view of the state of the cold pool and get a better quantitative estimate of what the existence or not of the cold pool is. And this gives us a little bit of hope as we think ahead in terms of how we use models. So the point here is, it's not a model data comparison. It's just simply that we have more information by, through the models, which of course are initialized by data, et cetera, but so on. Okay, so that's really the quick story here. But I remember that there was a program manager that looked at me many, many years ago when I did all these studies involving physics and things like that. And she said, yeah, but Cisco, fish don't eat temperature. And this was, the part about, yes, we can include all of this physical aspect of things, but there's more going on than just the relationship to temperature. So what's that next step? Well, the next step is a big one. The next step is a big leap in terms of how we're thinking about how we're going to move into the next level of science, and how do we communicate the advice. I'm going to start with the top right picture, which is it's schematized as something that's referred to as a management strategy evaluation in MSE. And it basically says we're going to start with some scenarios, in the top right again. We're going to consider these scenarios in the context of what the different ocean use sectors might be. It might be fishing, it might be energy, it might be commercial transport, it might be a whole host of things. And then we decide, well, what management scenarios can we bring to the populations that we're looking at or to the ecosystems that we look at to essentially then come up with recommendations that hopefully, and you can see that little checkerboard there with the different colors, might give you different alternatives in terms of how you manage the system, red, yellow, green, depending on your objectives and depending on the use sector that you represent or that you belong to. And so the picture on the left is sort of this cascade of the approach that we're taking is beginning with global scale models, downscaling to, pick your favorite regional model, which also includes, the different trophic levels, which also includes different higher trophic levels, which also includes different fishing management scenarios, fishing fleet scenarios, and so on, to give you ultimately in the bottom right, which are these scenarios that you can make decisions about. So the idea isn't to say it's really complicated, we don't know what's going on. The idea is how do we come up with scenarios that we can quantify that provide the managers and decision makers ability to make decisions. And this is an example, again, the wiggles don't really matter, but the point is looking at different climate scenarios. On the left side, looking at effects of temperature under the different RCP scenarios. In this case, on the lower trophic levels of zooplankton, you see that increasing temperatures cause a decrease in at least the lower trophic levels. The ones on the right say, given that, and given our understanding of the fishery, what happens if we impose different ecosystem-based fishery management approaches? Caps and catch, restrictions in total quotas, et cetera, going out to, say, the next 30, 40, or 50 years, right? So this is a really ambitious, I shouldn't say it's aspiration, it's an ambitious way to think forward in terms of how we bring together our understanding of global systems all the way down through the various trophic levels to decision making, which is included in here in terms of setting quotas, in terms of the recovery or not of populations, or how long they can last under these conditions. And so I'm going to close by just highlighting that we're bringing this together in all of this science and all of this decision making into something called the CEFI, the Climate, Ecosystem, and Fisheries Initiative. And what we're looking for is looking towards to providing this national capacity of providing regional ocean and climate information across the living marine resource management timescales. Again, it's not simple, but that's the idea, is to see how we provide this national capacity to decision makers and stakeholders. The approach follows what I described before, which is basically this Alaska Climate Integrated Modeling Project, the ACLIME project, from global scales down to the local scales. We're taking the approach of creating these, what were referred to as grids for the North Pacific, the Arctic, the US East Coast, Gulf of Mexico, and other regions where we will then be able to bring this, regionally, because each region obviously has different questions and different challenges, to see how we actually evolve our science advice. And this is where it becomes tricky. How do you actually translate this into science advice? So we have this double Mobius strip, if you will, where we say there's a lot of science to do. The ocean is changing. The ocean that I studied when I was in grad school 40 years ago is not the same ocean that you see today. So there's still a lot of curiosity-driven science that has to happen in understanding. We need some very high-performance computing to do this, but we also need to include the extension and the engagement of the management and the decision-making. So these three are intricately interwoven, if you will, in terms of the science that we need to do, the technological and innovative part that we need to do, as well as how do we communicate this to the managers. And this was touched upon very quickly this morning. How quickly can you run with new science, new advice, and still bring people along? And the answer is not that quickly. I think it's important to make sure that you perhaps, you keep providing the advice that you've provided, because there's a lot of changes that are happening. But at the same time, begin to provide, and I've called this a shadow assessment. So you can start off with an assessment the way that we do it. Say, well, this is our understanding as we have done it, say the past 20 years. This is the advice we want to provide. But if we take this new approach, and this is an example of what happens if you include all of these other components, you can begin to see the differences, and the zeros and the X's there give you a difference in terms of what would have happened had you included the environment, had you included multi-species, had you included the full understanding of the system to the advice that a manager needs to make about a particular fishery or a particular system at that time. So it's important to do this in an integrated and there has to be a handshake the entire time that we're doing this. We can't just come in and just say, okay, this is the new way to do it, because we also need to learn. We also need to understand what's possible and not. So I think this is sort of a deliberate approach in terms of how we're going to move forward. And so in summary, I covered a lot, but hopefully you got it. We know that the systems are now non-stationary. We know that we're no longer on a nice to know, but a need to know basis. We need to evolve our advice, and we need to do it, together with everybody else. And ultimately, hopefully, we can do this through this CEFI, the Climate Ecosystem and Fisheries Initiative, which I know that we're talking here to folks on campus. Like it was said earlier, we're hiring, and it would be really nice to bring people. There's so many parts to this thing that it would be really fun to have you on board, because it's anything from, as I said, basic biology to artificial intelligence to high-performance computing to management, you name it. You got it all. So with that, I'll stop, and thank you again for the opportunity.
I think he made a great case in terms of the need for embracing adaptive management and sort of learning as we go and responding with policy. So next up, Dr. Ardon is going to speak to us about ghost forests as indicators of wetland resilience in the face of sea level rise and climate change.
Thank you very much. Is this on? Is the microphone on? Yeah? Okay. Thank you for the invitation and the opportunity to talk. It's been great to hear all these talks so far, and we're going to go a little bit on land, a little bit different than what we've heard so far, but definitely I'm very interested in this linkage between land and water. And what I'm going to talk about is forested wetlands that are really in this interface between land and water. And so I always like to start by telling people how I got interested in ghost forests. So about a decade ago, I finished my PhD and I started working as a postdoc looking at wetland restoration. We were studying a restored wetland in the coast of North Carolina. They had planted 750,000 trees in this area. We were looking at these trees as they were growing. They were growing like gangbusters. We were looking at the water quality of the site. We were looking at the greenhouse gases of this site. And because it was a restored wetland, we wanted to compare it to mature wetlands nearby. So we found mature wetlands which were like, well, if we give this area enough time, eventually it'll look like this, right? A swamp, a cypress, tupelo swamp that were nearby. But what we noticed in the time of looking at the restored wetland was that our mature wetlands were dying. And so the trees were dying, the canopy was opening up, and there was this marsh vegetation that was coming in. And so in some cases, our mature wetlands were being replaced by marshes. In other cases, the forests were being swallowed by the water. And so that got me really interested into why is this happening? What are the timescales? What is driving this? I also realized in doing this research, every time I drove to the beach with my family, we would see these ghost forests. So these ghost forests are all over North Carolina. And if you've driven to the coast, you've seen them. And so again, we were interested in, again, what are the drivers? What are the consequences? We've been borrowing, these ideas of regime shifts and ecosystem changes. So, our general hypothesis, these systems tend to withstand certain amounts of flooding and salinity, but once you get to a certain point, you get a jump, and so the forest maybe turns into a marsh, or it turns into open water, and sometimes there could be a jump that happens. And so we're trying to adapt these ideas of resilience and also trying to find early warning signals. Can we identify areas before they change that maybe we need to go and protect? And so in terms of what are the drivers, of course we know there's the background of sea level is rising. So these are just some IPCC figures. So, we know that sea level has risen about 1.5 meters going back to where we started measuring. And going forward, we know that this is going to continue to go up. These are different projections from the IPCC, the 2014. We know that these are already outdated, and it's likely that we're going to have even more sea level rise. And so this kind of gives a background shifts that is changing the baseline, it's changing the mean high tides, but it's also changing the strengths of the storms that is hitting these different systems. In addition to that, we know that sea level is making the sound saltier. So Dr. Nelson did a beautiful explanation of the Albemarle Sound, and this is the Albemarle Sound right here. So we found all the records of salinity that we can find for this area, and we put them together, and we can see that there's this very clear line of salinity going out in the Albemarle Sound. And while there's a linear increase going on, there's also pulses associated with droughts and associated with storms. But the storms, a matter of whether the storm comes on land or on the water, and whether it's pushing salinity into the land or clearing the salinity out. So again, talking about this variability, there's going up and down, but there's definitely a clear trend. You can see a map here of what salinity used to be in the 1970s. Look at the Albemarle Sound was pretty low salinity. The 2010s, there's higher salinity, and here's the change between the two. And so we know that, the sea level is rising, but these systems are also becoming saltier. In addition to that, we know that we've changed this landscape, and we've replumbed this landscape. So a lot of this area got they put lots of ditches and drains so that we could put agriculture in there. And these ditches and drains are really good at moving water out of the system, but they're also good at facilitating salt water moving into the land. So we're bypassing the natural systems that used to capture some of the salt and filter it, and that salinity is making it further inland, making it much more vulnerable for these systems, to these rising salinities. So how many ghost forests do we have? So we've had a couple of different estimates using different methods to estimate how much ghost forests in the North Carolina have increased. So Lindsay Smart did one study where she used LiDAR data, and she estimated that there were 167 square kilometers of new ghost forests between 2001 and 2014, which is a lot of carbon that was lost. There was another study using the Landsat record, and this is a slightly different area, but they were overlapping, and they came up with 193 square kilometers since 1987. And so to put those numbers in context, Washington, D.C. has about 171 square kilometers of land. So in the last 2 decades, we had an area the size of Washington, D.C. that's turned from a forest mostly into ghost forests. Some of these are marshes. Some of these have been swallowed by the water. So we know this is happening, and we know that it's accelerating. One of the things that I was interested in is what are the consequences, right? If you have a forested wetland change into a marsh, you're changing one wetland from another. Wetlands are very good at sequestering carbon. So we went out there and collected soil cores. I like to joke that my student likes to get to the core of the problems. She's collected lots of soil cores. We estimated carbon and nitrogen sequestration. And so we were comparing forest to marsh. This is our work here in North Carolina. The forest sequester more carbon than the marsh, which is different than what they found in Georgia. In Georgia, they found that the marsh sequesters a lot more carbon. So if you're having a forest change into a marsh, depending on where you are, the consequences might be different. We also did the same thing with nitrogen. We also combined those estimates together. So we combined our estimates of below ground carbon with the estimates of above ground carbon in these forests that Lindsay Smart had put together. And so we could see, this didn't come out very well, but anyway, the line separates below ground carbon and above ground carbon. What I want you to get from here is that we looked at these estimates of above ground carbon and then compared it to the carbon sequestration rates of the marshes. So let's assume base case scenario, all of these forests turn into marshes. How long would it take these marshes to sequester the amount of carbon that it's already in those trees? And it could take 200 to 600 years for these marshes to sequester that amount of carbon. And unfortunately, these marshes do not have that much time. In about 100 to 200 years, these things are going to be underwater. So this is kind of falls into what's been called irrecoverable carbon. If we lose this carbon, we can't gain it back in the time we need to prevent the most negative things associated with climate change. Another consequence we were interested in looking at is, well, we have all these snags, right? These snags is why they call these ghost forests, because these trees are kind of white looking and eerie looking. And we know that trees are very good at moving gases from the soil into the atmosphere. So we wanted to know if the trees were functioning as straws, facilitating the emission of greenhouse gases from the soil, or if they were functioning as corks and keeping those gases into the soil. And what we found is that they're kind of both. So they're a filtered straw because they facilitate the movement of some gases, particularly CO2 and sometimes nitrous oxide, but they also keep some gases down. So methane, as methane moves through these snags, gets filtered out. And we know that the snags emit less than the soils, but when you put them both together, the snags emit about 25% of the soil emissions, so they can play an important role in the emissions from these ecosystems. And so we know these things are happening, we know they're growing, and we know that they could potentially be a positive feedback to climate change. Some of the things that we're trying to look at is, okay, what can we do about this? So another thing we've been working on is, well, we mapped them in North Carolina. Can we map them all across the Southeast? So I've been using the Forest Service inventory analysis to map out dead carbon across the site, across the southeast of the US. You can see that there are areas that there are hotspots of dead carbon. So these are places where we have a lot of ghost forests. So what explains these? Is it the storms? So we're comparing it to tracks of storms. Is it the rate of sea level rise? Is it the rate of warming? Is it changes in precipitation? So we're trying to explain these so that we can figure out what do we do with these systems. Some of these we're going to have to accept that they're going to change and just let them change. For some of them we can try to resist that change maybe for some time but not for very long. And for others, maybe we want to direct the change. Maybe we want to facilitate the change from a forest to a marsh. Something else we've been working on is restoring these wetland ecosystems. So I mentioned the ditches and the drains for all of these systems. That has facilitated the emission of greenhouse gases from these systems. So we've been working with the Fish and Wildlife and the Nature Conservancy and USGS in raising the water table from some of these systems. And we've noticed that when we raise the water table, we decrease the CO2 emissions by 58%. And they've come up with a methodology that this can create carbon credits that can then, in some future market, be sold to help promote or fund further restoration of these ecosystems. Another thing that we're working on is because these changes are so dramatic, we're trying to use citizen science to raise awareness that this is happening now, that climate change is happening right now, and that it's happening in our backyard. So in a collaboration with the park system, we've installed these chronologue sites in a couple of different state parks and some wildlife refuges. And so people come to the same place and take pictures, send it to a website that builds a chronosequence so that we can see these changes happening. And it's also a way for people to know that, that these changes are happening right now. So we know that ghost forests are increasing due to climate change. We know that the loss of this carbon might not be recoverable in the time that we need it. These snags are functioning as filtered straws. But I'd like to point out that, ghost forests are an indication that climate change is here, that it's happening now, but they're not an indication that we're too late. We can still enact change and we can slow down this change. And in many places, we're going to have to make decisions about which way these changes are going to go. And I want to acknowledge all the people that have helped with this work and also point out Rihanna Absher, who's a Wondergrad who's been working in my lab, and thanks for the kids' funding, was able to do an internship with the U.S. Fish and Wildlife working on wetland resilience using surface elevation tables, and she has a poster that you can see. Thanks.
I thought it was interesting how variable salinity became after 1999, and then that's when the ghost forest started increasing. That was interesting. So next up, Dr. Chris Osborne, title of his presentation, Lingering Effects of Extreme Weather in coastal waters.
Okay. All right. Yes. Well, thanks very much. I am also very happy to be here and to be interacting with such an interesting topic and talking a little bit about some of our work here. My title, Lingering Effects of Extreme Weather in Coastal Waters. I want to acknowledge the fantastic team of collaborators and students that have been working on this over the past few years with me. And when I was invited to present, we all were sort of prompted by Dave to answer this question: what's the future of climate change threats to coastal and marine ecosystems and the associated opportunities and solutions? And so I'm going to try to point out that question in relation to what happens after we experience these effects and the kind of short-term, very turbulent and disruptive types of things that happen along with some of these effects, and focus on what happens on the back end. And so one thing to sort of note about these events is that we do see these pulses of extreme weather are increasing in frequency, and our earlier speakers in the morning session framed that quite nicely. One thing I will point out is that as well with the, where's my button? The extreme flooding that occurs, as pointed out by Dr. Nelson, is that along with the water is coming a lot of other things. And that will be a linkage to some issues we want to think about with respect to carbon. You've also heard this term, the new normal. And so we seem to be in this period of increasing intensity of these events and the precipitation associated with it. And it's stark. We can see that affecting our coastal waters. We can also see, if you disregard the jumping dot that's there for some reason, but I will come back to it here. We are in this increasing period of extreme precipitation, and some of the 7 wettest storms have occurred in coastal North Carolina in the past 20 years. And so I'm going to let you have a look at these different screen grabs of papers that have been published over the years. And what you're going to see here as you look through these titles is that the impacts tend to directly relate to carbon cycling processes. And these are going to be important in our framing today because we want to understand what this eventually means for our carbon-based climate solutions. And so these will come into thinking about where carbon is being redistributed, what types of carbon are being reacted, are reactive and are being reacted. How is this changing in different depositional pathways? How is it linking towards or with the hydrological cycles? And then we also have to consider small systems. So not just the large estuaries, the large rivers, but the small coastal environments, which can be very significant. How different things such as color, chromophoric dissolved organic matter, which I love to talk about, and I'll talk about a little bit more, impacts and can influence the effects. And eventually we're going to get to this point where we can think about how these recent sort of catastrophic events are changing CO2 emissions in various spaces and ultimately leading to an extreme future for our coastal waters, especially our estuaries. And I'm going to draw on that by focusing on a couple of points that Wetz and Yoskovitz make in their paper related to these lingering effects. Now, they weren't exactly framing it this way, but this is the perspective that I want to talk about today. So how can we look at the effects of mobilizing not just CO2 emissions, for example, but say the significant quantities of organic matter and nutrients that are stored in the landscape? What happens to all of that once it gets into coastal waters? How do physical processes like stratification facilitate these lingering effects? How long does the system stay stratified and poised to react this organic matter, deal with these nutrients, and what are the outside effects? And then looking not just at the quantities, but also the quality. So I'm a chemist and I tend to think a lot about how the quality of different carbon compounds matters as much as the quantity of them. So we want to look at that as well. And I'm going to try to put this together with this idea of coastal indigestion. And so what is coastal indigestion? Okay, now bear with me for a second here. If we compare a coastal environment, an estuary, we can think about it in the same way we think about the human digestive system. The coastal system brings in food, it brings in carbon, brings in nutrients, and it does something with those, much in the same way heterotrophic organisms do. Okay, we process some of those things. And key to that entire operation is the microbiome. Okay, so a healthy microbiome in the estuary, much like a healthy microbiome in us, will sort of set the stage for looking at some of these long-term effects. So then what happens when the microbiome gets altered or gets unhappy? We can think about the symptoms of the indigestion in much the same way. If we look at how storms can cause too much carbon to be saturated in the system, something like overeating. If we change the sources of carbon, if we change the diet, and then looking at both the balance of the acute effects and then the chronic effects downstream. And so what I'm going to do is to also pose that we can see these effects from space. So I'm sure most of us, if not all of us, remember this image after Hurricane Florence in 2018. It appeared a lot in the media, and it just shows you how in coastal North Carolina, after landfall, we see our coastal waters, these sounds enclosed by the barrier islands, are normally look green or blue from space, not brown. But the brown is all of the carbon that's being translocated from land into our coastal waters. And if they're retained in a long enough period of time, we can see some effects. Now, if I borrow a little bit from Hans Perl's work, we can also think about what happens with loading in nitrogen and phosphorus. And some of their work from the Pearl group has showed over time that after these events, you get severe spikes in primary production. Now, that could be a good thing in the sense that it's a carbon or CO2 capture mechanism. A lot of production, we get a lot of carbon capture. But I want to think about this a little bit in more detail as to what some of these effects, especially of the color, might do to offset that potential benefit. So we're going to talk a little bit about a couple of examples looking at different carbon pools in the Neuse River estuary, one of the major tributaries to the lower Pamlico Sound here in eastern North Carolina, and just some kind of statistics on this combined system, the Pamlico Sound. It's very important from a number of perspectives, not just to the state, but regionally. And it's also a very large and enclosed system that has a residence time long enough to be able to observe and understand how these effects play out. So let's look at Hurricane Irene. This is some of work from Joey Crosswell and others, and we're looking at the Neuse River estuary and the Pamlico Sound. The flux that we're looking at here is CO2 flux, and we can think of this from sea to air. Okay, so from the water's surface back into the atmosphere after the storm. Now, what you can see in both cases is that once Irene comes through, you have this huge pulse and release. That's the disruptive physical, the wind and the wave action stirring up and sort of disrupting the entire ecosystem, releasing an awful lot of CO2. On the back end, once the storm passes, notice that in both cases, in the estuary as well as in the sound itself, we can see these positive CO2 to air, or C to air CO2 fluxes. So the system stays poised and stays disrupted in this CO2 source mode. And if we then kind of link this back to this idea of chronic indigestion, this long-term release, if we take a look at the entire year, what we can see is that it's a disruptive and it's a major part of the annual CO2 budget. So what does that mean if we want to try to look at carbon capture mechanisms and how natural ecosystems such as estuaries serve as those purposes? Well, we have a long-term gas release, and we can see that the importance of these single events matter. Here's another look at this, same region, This is a time series, and this is after Hurricane Matthew in 2016. And so what we did is we looked at data down the estuary, so that's what the y-axis is showing here, from the upstream riverine part all the way out into the lower Pamlico Sound over time. And so what this contour plot is trying to communicate is that we have this positive flux of CO2 from sea to air, and it remained so, it remained positive, it was spatially consistent over weeks well after the storm had passed, okay? And so this is troubling to us because if we start looking at how the microbiome responds, we also see that what's happening is the CO2 appears to be coming from the stuff that's loaded into the system. It's still being metabolized. And we can see that in, if we compare carbon respiration measurements, in the perspective has changed a little bit here. This is time, and then this is a station down the estuary, but still, we're looking at carbon respiration measurements. Several weeks after Hurricane Florence, it's the same kind of thing. We see this sustaining respiration and an active microbiome and this coastal indigestion. So that's North Carolina. If we look at some published work from Galveston Bay, after Hurricane Harvey, the same kind of thing pops up. We see, in this case, what these folks did is they looked at the change in the community composition, and they found that the microbiome shifting towards organisms that can metabolize those types of things that are underscoring that brown color that we see in that land-ocean transfer. And the degradation or the decay constants are some of the highest that they've measured. So that's telling us that carbon's active and we're having these very active pulses and this kind of chronic indigestion. As well as what happens when we get this color loaded in is kind of a shutdown of that response that we would expect from loading in all those nutrients. So primary producers that are photosynthesizers, they need to have nitrogen, they need to have phosphorus, and they need to have sunlight. So if the sunlight is shut down by particles and the brown stuff, the CDOM, that color, then what that can do is that can suppress, especially in these long residence time systems, suppress that primary production that would offset otherwise active CO2 sink that we might get from loading in those nutrients. So again, the microbiome, the system is shifting around, and then we just did some calculations recently. We took a look after Hurricane Florence in 2018, and what we show here is CO2 fluxes again. You can see for the Neuse River estuary, we get a spring sink that appears from the early primary production in the first part of the year. But notice the CO2 fluxes associated with and then after the storm, the same kind of thing. And just sort of our initial calculations, we look at the net annual release out of the estuary was 2 billion grams CO2. So a pretty good sized amount. And putting that in perspective, if we look at the effects, the release from Matthew, about 0.02 teragrams CO2, from Irene, 0.1 teragrams CO2, these are significant components, okay? These are significant components of the kind of carbon budgets that we already sort of depend on to understand in the larger scale where CO2 is going. And these estimates, I'll also point out, are just for our systems. So if you think back to what we heard earlier about variability and uncertainty in measurements, this comes into play quite readily. And so what it means, I think, is that as we begin to look for solutions, and they're out there, and there's a lot of very good solutions that we're working towards, we have to keep in account two things. One, how do extreme events offset carbon capture by moving around carbon, both in terms of lateral transfers as well as vertical transfers, CO2 and methane? And then, can we develop solutions themselves that are resilient? So as we just try to work on solutions for mitigating climate change, those solutions, as they try to improve resiliency, must also be resilient themselves. So I've just thrown a couple of examples up here and noted some challenges. We might be hearing more about this as we go through the symposium, but approaches like alkalization we get complicated by coastal acidification. We know that in certain instances that our estuaries and coastal waters are becoming more acidic, much like ocean acidification. In carbon capture, we have to worry about how these fluxes, both in the vertical and in the horizontal, in terms of export within water, are being affected. And then in terms of carbon retention, so those strategies we might take towards actually containing and storing CO2 as different forms, we can't neglect the protection of habitat. And so I'll just summarize here that the increased period of these extreme events, they cause these disruptions. That sort of indigestion can linger long after the event. And then accurate carbon and nutrient accounting should incorporate these events for their effects, as well as help us design resilient strategies to improve resilience. Thanks.
Okay, I'd like to invite our speakers up for the panel discussion. It made me think about probiotics for the estuary. I wonder. So, questions, please. Nope. Okay.
Start and then you can. Thank you all very much, obviously. So each of your talks kind of triggered in me, one of the concerns with climate going forward is food security. So especially as I think of the fishing industries, and Cisco, you were talking about those shifts in populations and without that recruitment rate. So I'm wondering if you have any future projections, future hopes, either on, from a recruitment perspective or from overfishing, and then how that ties in as well. I can think from both of your perspectives with the marsh, right, and from the other industries that come from those habitats, and then nutrient inputs as well.
Thanks. Great question. It's a complicated one in some ways. Part of the food security aspect does several things come to mind. One, the simple shifts, if you will, in terms of biogeographic shifts that we might need to anticipate. I gave the example of Pacific cod, moving almost 1,000 kilometers, and how that changes, particularly, the decision making, if you will, of communities that depend on seafood for their sustainability. The case of recruitment in the case of the flounder, well, that could be something that we just need to be continuing to watch and see if the rebuilding plans are either too quick or too slow, and we need to think about that. So again, we need to consider those two in terms of how our anticipated rates of change of the environment are keeping up with the recruitment rates. So I think these are all questions that we need to look at and work with the management community, right? In terms of how is it that we prepare those communities that perhaps depend either commercially or for sustenance of those populations, to anticipate and reduce their exposure, the risk, and maximize their resilience. So it's that conversation, is trying to find that sweet spot, if you will, of all of those topics that we do need to consider explicitly from now on. But yeah, no, great question.
Oh, yeah. Yeah, I think that's a great question, and marshes are very important nursery habitats, right? And so losing marshes and losing these wetlands is I guess, indirectly, but definitely going to affect food security as well. Fisheries in North Carolina, both commercial and recreational fisheries, are really important sources of income. So having the loss of these systems is going to affect those as well.
I would just kind of follow up with that and say it's a similar type of thing. If you think about how long these effects go, how long does the ecosystem stay disrupted?
Next question.
There, yes, really enjoyed the talks. Thank you for all the speakers. This, my question is also kind of a comment more directly to Dr. Werner. I'm a biogeochemical modeler and kind of a young early career scientist, and really excited by the idea of using these, highly realistic ocean models to start to answer ecological questions, doing ecological forecasting. From my perspective, there's kind of these three layers, which is, the physical model, then you have the biogeochemical model, and then above that, you have the assessment models. If I guess my question is, if there was a really idealized, perfect biogeochemical model, how would you even connect it to the fisheries assessment models? What, I guess my question is, what are the most promising avenues that you see as, kind of connecting those? Thanks.
Super question, and that's almost at the core of a lot of the things that we're looking at. How do you connect from physics to fish, right, through the biogeochemistry? And the answer is that there's a number of ways of doing it. You can do it in terms of overall budgets and try to see how much of whatever nutrient is available, or how much of a particular lower trophic is available to the fish populations. The tricky part comes in the details, right? Because it's looking at the fact that each one of those components is also changing, perhaps temporally and spatially. And so how do you actually keep track of the changes that might be happening, let's say with the biogeochemical component, at the same time that you might be seeing shifts in the higher trophic levels? So I think it's a combination between looking at what might be, looking at overall budgets and see how they're changing, to actually looking at more mechanistic approaches that might be more individual-based approaches or agent-based approaches and such. So I think it's one of the areas that I said earlier. There's a lot of new things that are happening that are, I think, important to take on in a curiosity-driven sense in terms of how does this work, as we then work to try to make that connection more quantitative and more perhaps directly applicable to decision making. So it's a question that is on the table for us to look at. So I'd love to talk to you more about how to do that. But great question. Thank you.
Thank you.
Thank you. Again, I'm Wei Jun Cai from Delaware. So excellent talk, all of you. And my question is to Chris. You showed this during the storm season that within a short period, lots of CO2 gets to the atmosphere that equivalent to like months or even longer of carbon barrier in the sound. So that's great. Really, we need to pay attention to that. However, there is another side of that story: is you mobilize both organic and inorganic carbon to offshore. And what is the fate of these carbon organic that will face a different maybe pathway or time scale of degradation, and inorganic carbon as well? I wonder if you could comment on that, and thank you.
Yeah, thanks. That's the great question. What happens when you escape the barrier islands and you get offshore? Well, you have a dilution effect, so to some degree, some of that, especially the organic matter, might be diluted out. But you can facilitate the opportunity for photochemical reactions, that is sunlight actually reacting, getting absorbed by that color, and degrading. So it's a feedback loop to CO2. And even there's some evidence that starting that process will make some of that carbon more labile or more usable by different bacterial populations. So as you move that material offshore, and I'm focusing primarily on the organic side, which is my main focus, is I think those are some of the long-term effects that can happen. We see this we've discovered it in large river plumes. And so you can imagine that translating more of that material beyond the estuaries out into the coastal and open ocean is going to help facilitate those processes to some degree. On the inorganic carbon side, I would say that it could be a substantial load, but that's less of my study area as far as those chemical pathways. And so I'd be interested in learning more and talking more about that.
And if I could just jump in, I was going to follow up on a question, if I could, and actually tie in with your question about understanding the microbiome and such. There's changes that in the past I don't think we would have thought about needing to understand the microbiome of open ocean systems, particularly as they affect the higher trophic levels. And there's some interesting recent studies that, for example, suggest that there might be changes in vitamin B availability in some systems that, could be two things. It could be either something, a predator-prey interaction and some, amino acids or such that are out there, versus actually changes of, in this case, vitamin B in the water column itself. And that, in turn, goes perhaps to the remineralization rates of some of the populations that are out there. So I think these are, frontier kind of questions in terms of what we should be looking at, and things that I don't think we would have thought about that. Nobody's ever asked, does your model do vitamin B? And no, the answer is no, most models don't do vitamin B, but they're out there as some things that we might want to look at. So anyway, sorry, it occurred to me that's a very relevant question, so thank you.
So thanks again for the three wonderful talks. What strikes me very much is there's multi-scale, multi-dimension processes. Like Cisco talked about the fishery, which happens over probably multiple year scale, and Marcelo talked about the ghost forest, which is probably happens over decadal time scales, right? And Chris talked about the extreme events, which happens over days to week scale. So this is our nature. Nature has there's the dynamics, nonlinear interactions across all the spatial and temporal scales. How do we make a good prediction that can account for such a complex, nonlinear, multi-scale, multi-dimensional interactions? What is the next step? Like, we're making lots of climate projections without considering all the nonlinearities, interactions. Are we there yet? So are we making a right climate projection, or there's a lot more work to do?
I'd say it's a little bit of both. I mean, yes, it's a complicated problem, but I don't want to say we don't know where to start. I mean, I think that we have our arms partially around the problem, and I'd say that because it goes together with what's been said before. There's a lot of hope in terms of what we know and what we can do. I think it's just making sure that we don't bite off more than what we can chew, and in some ways, you talked about multiple scales. It also depends on the question that you're asking. So maybe part of the art is understanding what questions should we be asking that we can answer, and the uncertainty shouldn't be something that holds us back. I mean, I think the uncertainty that's out there is something that we should embrace, and try to be a little bit quantitative about the likelihood of outcomes and the likelihood of what might be happening, depending on whether you're looking at rebuilding a population or long-term, protection of an ecosystem or something. So I think that we do have ways to go forward. I mean, we do have steps that we know that we can take, but it's one that we also need to be deliberate in terms of how we proceed. So, and that's also the invitation I had earlier. I mean, I think we do need new ways of thinking, and so again, we're hiring. I'm going to say it a second time, and so if there are ideas that people bring in terms of how we can tackle this problem together, and I think it was said earlier in one of the talks today, we really need to bring the different ways of thinking, both internally and externally, in terms of how it is that we step forward. So, it's challenging, but I think we're capable of making significant progress.
Yeah. I would add to that one of the things as an observationalist and experimentalist we need to do is to improve our resolution of being able to observe the events and the effects of the events. And, I can say like, oh yeah, more data is always good, right? But it's not always easy to go out and get that data, especially during an event or even perhaps after an event. This is an opportunity. It's an opportunity for different ways to access inaccessible sites. It's a way to develop technology and develop strategies to make coherent observations. And you can think about, well, there are storm chasers, but maybe there are after storm chasers. that want to get into the biogeochemistry. And I'm not hiring, but if you're interested and you want to go sampling with me sometime after a storm event, I'd love to bring you along. And but in all seriousness, I think it's those types of multi-scale activities that need to also follow with observations so that we can help calibrate and validate our modeling efforts.
I'm not a modeler. You know, I do think there's all of these nonlinear and spatial, you know, we have spatial variability, we have temporal variability, we have interactions, nonlinear interactions. I think there's definitely a lot we already know, and even though, you know, we're not to the point where we can model all of these things, I think, like, you know, we're saying we have to embrace the uncertainty. What I always worried about is, like, let's not let the perfect be the enemy of the good, right? I think we know enough that we can start to put in action, put in changes, and then we need to track those changes and see how they result and how they work. But I think there's so much we already know and so many things that we're asking now that we never thought we would ask, right? It's always going to be improving. It's always going to get better. So let's just keep doing it, right?
And with that, Amanda's telling me that it's time for lunch. And so I'd like to thank Cisco Werner, Marcelo Ardon, and Chris Osborne. I thought it was a really very interesting session. So thank you all. Thank you all.
So we do invite you to join us for lunch back upstairs. So you get your stair exercise or elevator if you wish. At the start of that, we'll have our Climate Leaders program giving you lightning talks as introductions to their posters. And then we'll be joined virtually by Stan Posey during that time as well. So we'll join you upstairs.
Hi, everyone. Can you hear me okay? Hello?
Yeah, I could hear you just fine. I'm not in the same
Okay.
room as you're presenting. I'm in the other room that they're bouncing back and forth in. So I'm checking with my team right now to make sure they can hear you. But
Okay.
audio-wise,
Thank you.
you sound
Thank you.
crisp and clear.
Terrific. Thanks.
Thanks.
Testing. Hello, this is Stan Posey. Hey, Emma, could you shut your door?
Okay, can I have your attention, please? So please continue get your lunch, but we're going to start our luncheon presentation. So the design of the climate...
I can't hear the introduction.
Is to have components coming from academia, government, and also industry. So we have quite a few industry representations here attending in person, but we also have folks online who will also share their industry perspective, especially in the climate research domain. So we are very fortunate to have a scientist, a program manager from NVIDIA, Stan Posey, who is going to give our launching presentation for today. So let me introduce our speaker. So again, very excited to introduce Mr. Stan Posey. So Mr. Posey is the program manager of Earth System Science in NVIDIA Corporation. He joined NVIDIA in 2009 with more than 20 years of experience in the high-performance computing industry. And Ms. Posey currently manages the NVIDIA's worldwide strategy of HPC applications and solutions development for the domain of Earth system modeling and also the computational fluid dynamics. So prior to joining NVIDIA, Ms. Posey has contributed in applied HPC with an end user role at Oak Ridge National Laboratory. He also played as a vendor technical role at Silicon Graphics and other industry leading companies. So Ms. Posey earned bachelor and master degrees in mechanical engineering from University of Tennessee. And his presentation, again, trying to highlight what NVIDIA is doing in the climate research, is titled NVIDIA Earth 2 Digital Twin Initiative. So without further ado, I will turn the podium to, well, virtually to Mr. Posey. And let's welcome Stan for this launching keynote presentation.
Good afternoon, everyone. This is Stan Posey. I'm going to give you a short review today of a new project at NVIDIA, one that is unlike any I've ever been involved in my 10 plus years at the company. And I'll start with a brief introduction of the project itself and then the problem statement. First off, I would encourage you to read this blog that was written by our CEO, Jensen Huang, that describes what we are planning to do in the Earth-2 project. And it's to build a world-class system along with a climate prediction capability based on a digital twin concept. I want to point out and emphasize in the second bullet that we're doing this conforming to the directions of the climate science community. We're not climate experts ourselves. We have hired some climatologists for this project, but we're really conforming to the direction the community is going. And certainly there's a lot of technologies that will contribute to this, and I'll describe some of those as we go forward here. To start with some early inspiration though and vision for the project, I'll point out that Jensen, the CEO himself, had attended a few lectures. One was the Supercomputing 20 lecture from Professor Bjorn Stevens of the Max Planck Institute. And if you haven't had a chance to view this lecture, I would really encourage you to do so. I thought it really described the problem well, laid out the groundwork for what we need in the way of making interactive use of climate data at an actionable level, one that would be more towards having policymakers be able to use this in a way that, or non-climate scientists in a way it hasn't in the past. This kind of led to the second point here, the EC Destination Earth. Destination Earth is a project led by ECMWF with contributions from Bjorn Stevens, the Max Planck Institute, and led by Peter Bauer, who's the director of the program. There were two other activities that were influential. CLIMA is a new climate model developed in the US based on philanthropic funding from the Schmidt Ventures Institute. It combines numerical and AI modeling. I'll describe a little bit of that. And then the AI2, the Allen Institute for AI, which is based in Seattle by Paul Allen, another philanthropic program that also combines numerical and AI modeling. These all contributed to the inspiration and vision that we have in place today. Earth-2 is a collaborative and open science project. I'd like to emphasize that. We have a number of key people at NVIDIA involved, several with domain experience. I'll point out David Hall is one of the contributors who we had known Professor Huff from through the AI2ES, where he's a co-PI, but a number of people are contributing at the company. Now, some of the scientists that I mentioned on the previous slide have become science advisors to the CEO on this project, including Peter Bauer, sorry for that advance, Bjorn Stevens, who I mentioned, those two, also two others from ECMWF, Peter Dubin, Niels Weddy, and now also Paco from Barcelona Supercomputing Center, who's contributing on some of the other components besides atmosphere, starting to look at models and fully coupled environments. On the HPC side, we had guidance from several, including key customers like CSCS in Switzerland, NASA, and NCAR, who were all contributing on some of the HPC directions. Now let's start though with some of the motivations for why NVIDIA decided to do this. In the CLIMA lecture that I mentioned, this was shown how there's an expectation that we'll not get to what's needed in the modeling community, which would be getting to the point past storm resolving onto cumulus clouds resolving until around 2060 based on the current roadmap of HPC. Now this is a pure numerical modeling approach, and it was decided that maybe it would be too late if we waited till 2060 to get to that level of resolution that would provide a certain capability in modeling. But resolution is only one axis on the computational demand. There's certainly a focus on complexity, adding more components to the model as we go forward in time, as we've seen historically, looking at ensembles. And in this case, we're going to propose massive ensembles are necessary. And all these play into the requirement for a new approach. A third motivation would be that which was described by Bjorn Stevens in his lecture about the need for interactivity. And here's an example of where we might take global climate data, develop regional types of information that can be applied to certain applications, in this case, applications on the power grid. And as Bjorn pointed out in his lecture, we can compute KM scale predictions, but not effectively interact with the content. And that's one of the overarching goals of this project. So the climate community, though, is responding to many of these challenges. Again, I pointed to Destination Earth in our area of influence and inspiration. It really envisions how Earth modeling should be developed, and we're contributing to that project. We've got developments in the models to help them get to the kilometer scale by running on GPUs. And also 2 of the systems that will be used in this project, Destination Earth, are based on NVIDIA GPUs. That would be the Leonardo system at Chineka and the Mare Nostrum 5 at Barcelona. And you can learn more about the Destination Earth at the link provided. Now, but what will be different about what NVIDIA is doing? And here I describe some of the features of what we expect with Earth-2 as it develops. What's different in NVIDIA's approach is we'll have a very heavy focus on the latest AI methods and research, something that we don't see in the community today. And the CEO has stated we're not going to do things others are doing. We're going to conform to the directions of the community again, but we're going to offer some alternative approaches that may be able to help us get there sooner. Certainly there'll be an operational supercomputer stood up sometime in the next year or so that will be designed for a massive scale of AI training. We'll focus on very fast AI surrogate models with high resolution, massive ensembles. We'll have the leading scientific research, and I'm going to give you an example of that later, on deep learning and physics machine learning. And climate data interactivity will be important. That will come through an environment we developed called the Omniverse that will help us get to the interactivity from global to regional scales of climate data. And then we'll have continuous learning from Earth observation data and Earth system model data as it becomes available. And again, what's different is we're leveraging what's available in the HPC community for large scale AI training. And here's just an example of the gap that has developed over time of the top 500 systems in the world based on their HPL or LINPACK, high performance LINPACK, which is the measure of the top 500 that has to be met, versus what you see today with AI. And you can see there's a gap that continues to grow, and we'd like to leverage that opportunity with AI. So we've gotten started, and we've been training on reanalysis data. We also now have IPCC data available. We can start to look at some of these climate predictions to train this AI model that I'm going to describe here later. And we've started with ERA 5, which we think is the most appropriate data set available from ECMWF, and have been able to achieve medium range weather scale. I'll describe some of that. We're now looking at the CMIP6 data that's available. Later, we'll move to the high-res MIP at 25 kilometer. But we really have to plan for progression to higher resolutions and then diversified models. And there we've been working on collaborations with NCAR and NASA on the reanalysis data. The NCAR CSM is probably the most widely used climate model in the world. There'll be data available from that. We have the impasse model running on GPUs. We'll be able to get convection permitting data from that, which is coming soon on their new derecho system. The USDOE is working on the E3SM and new SCREAM storm resolving model that will contribute. And there already exists high resolution data from the Diamond project, and that was based in Europe. And these include models like IFS, ICON, MPAS, and GEOS. And soon they'll have the Diamond 2 project rolling out results for atmospheric coupled ocean. But ultimately, we need to get to these storm resolving ESMs towards 1 kilometer resolution. And there's a project in Europe, the Next GEMS, that's focused on that, getting ICON and IFS to 1 kilometer global uniform resolution. And then we're talking to the various organizations, NASA, NOAA, ESA, on Earth observation data. But ultimately, we have to tether to high resolution predictions. If we're going to get to these decadal, centennial simulations, really what we've got here is an opportunity to have those in place, these large high resolution kilometer scale simulations, but then have the AI model generate details between the checkpoints, and will save us both in computational time and also the amount of data that must be saved from some of these very high resolution simulations. And of course, Earth observations will be needed to continue this collaboration of the predictions to make sure that our observations and feedback for simulations of the future will collaborate back to those simulations in the past. So to give you an overview, though, of the contributing technologies, I've described this AI surrogate model approach we'll take. That's being developed in this environment called Modulus. If you haven't seen that, there's a link there. You can go and read more. And then there'll be the Omniverse environment that can provide connections between the different models and provide us the move from global to regional models in order to understand the interactivity that could be available with these types of models. The HPC will contribute the synthetic data. The Omniverse can also read the observation data. These will contribute to Modulus, which will then be the AI surrogate model to help us understand how to develop these various digital twins that can become actionable in a regional modeling environment. So I'm going to describe now some early results we have at weather scale. And we developed this AI model again. We call it ForecastNet for the method behind it, Fourier neural operator. Different than what you might be accustomed to with conventional CNNs, neural networks. And it's a collaboration that was developed between NVIDIA and several US academics and national labs, in particular the Lawrence Berkeley Lab here in Berkeley, California. It's a data-driven ML surrogate approach for medium range prediction. It's been trained on 10 terabytes of about 35 years of ECMWF Era 5, which is at 30 kilometers, 137 vertical levels, a reanalysis data set. We're using what's known as AFNO or adaptive FNO architecture that was trained on 20 input variables per grid point that you see listed in the table on the right. And the one of the key advantages of this has been the highest resolution model ever trained. And I'm going to show a comparison of that here in a moment. And other great advantages include that we can run an inference of the model once it's trained that requires about 2.25 seconds for a medium range forecast of 2 weeks. And that gives us a speed up over a conventional NWP of 4 to 5 orders of magnitude on speed up, and then 4 orders of magnitude on power savings, which also equates to savings on carbon emissions. And we're seeing exceptional skill for the predictions so far, which I'll be giving you some preview on. This represents some of the skill scores we've developed versus comparing our ForecastNet model again with IFS, both trained on the Era 5 dataset. ForecastNet trained on the Era 5 dataset, and IFS, a numerical model, also using the Era 5 dataset for its prediction. And you can see our skill scores look really good in the short range. Medium range, we still have some work to do, but it's still very good skill and similar skill, but at a fraction of the cost, as I mentioned earlier. To look at some of the comparisons on this resolution versus what's been done in the past, here's a series of papers going back to 2018. Dubin and Barrett at ECMWF developed really the first whole model looking at a data-driven approach, much like we're doing today. There were a few others that came later, Weatherbench, DLWP from Jonathan Lane and Dale Duran at UW. More recent on graph neural networks that was published this year, and then what NVIDIA has published for ForecastNet. And you can see the progressive improvement in resolution, increase in resolutions, but still we've got by far the largest available. And again, we're leveraging this opportunity to drive AI to very large scaling that has not been attempted before. And here's an example of that. We've done some strong scaling studies on some very large systems that exist in the community. These are all three in the top of the top 500: Jules Booster, the JSC in Germany, Perlmutter at NERSC, Lawrence Berkeley Lab, and then Selene, which is a internal NVIDIA system. And you can see that we're training out to 4,000 GPUs or so for these particular environments. But this is far more than we needed. We just wanted to demonstrate what was possible in training for the future as we get to much higher resolutions beyond ERA 5 towards the 1 kilometer global. But you can see some of the results that we were able to achieve on about 3,000 GPUs. We're getting the training time down from 24 hours to about 67 minutes. Now, once you have this model trained, you can then run it in this inference environment and see turnaround times, even for massive ensembles, in just a matter of seconds. I'm going to go quickly through a few other comparisons on skill. This is ForecastNet versus IFS ERA 5 on atmospheric rivers. Precipitation and surface winds, we saw very good agreement there as well. Hurricane paths and intensities. Here we're showing a few insets, ForecastNet versus the ground truth. We're able to capture the cone of uncertainty very well. For this particular Hurricane Michael forecast that was provided. And we did a study recently. I'm going to describe a couple of things we did to help go beyond and demonstrate beyond what's possible with the ERA 5 reanalysis and what we've been able to achieve so far with the current study. Here, what we did was increase the number of variables from 20 to 26. So a very nominal increase. I think ERA 5 has some 250 variables available. Here we went from an increase of 20 to 26 again. And you can see already how we've been able to improve the score from the red line here, which is the 20 variables, to the green, which is 26 variables. So we're starting to get further in range and closer to what's available with IFS, which again is the kind of gold standard in NWP for a medium range forecast. This was another variable, same idea, where we're able to improve quite substantially, just going from 20 to 26 variables towards meeting the skill scores of IFS. So we haven't really reached the limit yet on skill. We're now training on many more variables. I think we'll go to the full set since we can scale on these large systems and see what's possible at that level. Another interesting study we did was to compare what would happen with zero shot skill, so to speak, where we've trained this model on ERA 5 data. And then let's see what happens if we were to initialize it with a GFS forecast. Now, it hasn't seen any data yet from GFS. It's been trained entirely on ERA 5 based on the ECMWF model. And by doing this, though, we were able to find out that we could train or initialize with GFS data after being trained on ERA 5 and then do a really good job at predicting a GFS forecast. So this will move us closer to real-time forecasting once we get a capability for data assimilation. That's still some ways off, but in our roadmap. But you can see that we're able to get very good skill comparisons with GFS in this particular study. So some of the directions we're going with this model is, again, the massive ensembles. Here we could generate thousands of calibrated ensembles in minutes, which we think can aid in forecast uncertainty quantification. Local area model is in our roadmap, where we can start to develop a regional version that could be applied for weather prediction. And then I mentioned earlier the larger input vector, where we'll move from the current 26 to looking at the full 250 variables that are available. So I want to mention too that this is now open source, and I would encourage any of you in the research community to join us and see what you can learn and drive from data-driven weather prediction. We would really appreciate the collaboration. And a final comment on future work. As I mentioned, we're looking at the CMIP6 data, and we're going to look at that as far as the number of models available, or somewhere in the range of 30, but we can use that for initialization of our surrogate. We're working with the next GEMS project I mentioned, where we'll get to ICON 1 kilometer data that we can use for the tethering concept. We're moving forward on hardware that could be the first launch of the E2, which is our OVX hardware design, really geared towards large scale AI training, as I mentioned. Other areas of research going from 1 kilometer to 5 kilometer super resolution for subgrid emulation on certain physics parameterizations that we may want to emulate along with the dynamics available for a numerical model. And then looking at regional and fine tuning and downscaling. Sorry, this is the super resolution application, not the one I pointed to earlier. And then also looking at the collaboration and looking at some sort of AI technique for that that's new in the literature. I mean, that's really our overall focus here, to come up with methods that haven't been attempted in this community and see if we can help drive them further towards everyone's end objectives. Now, I didn't give a very scientific talk, but if you're interested in some of the more scientific details, I would encourage you to listen to talks recently provided by scientists working on the E2 project. One that happened at our GTC a couple of weeks ago, and then one that was just last week at this Easy Waste virtual workshop that's listed here. But you can get a lot more details about what we're doing at the technical level of the AI research, as well as how it will be combined with numerical models. All right, well, I really appreciate this opportunity again, Professor Ho, and didn't know if you were planning on a Q&A, but I'm certainly available to answer any questions that may come up. Thank you. Thanks for the opportunity.
Well, thanks so much, Stan. So as we been discussing and exchanging.
And I'll add that if someone is speaking, I cannot hear.
Can you hear me now, Stan?
Stan, can you hear us now?
Yes, and I noticed earlier that when Professor Ho was giving his introduction, it was muted.
Oh.
So I didn't hear him.
Okay, so this mic is not working. I'm okay. Okay, you can hear me now, right, Stan?
Yes,
Okay,
Professor Ho,
wonderful.
thank you.
Yeah. Okay, thank you. Well, thanks so much for this very exciting presentation. So we've been discussing this morning that fighting climate change and develop innovative climate solutions require a all-hands approach. Right? So we have people from academia, government, and industry. So and we're so happy that industry leaders like NVIDIA is investing using this innovation, the new technology, AI, machine learning, to help addressing the climate challenges. So I'm also very grateful for you, Stan, for making this great presentation. So at this point, I'd like to open the floor to see if our audience have any questions about the digital twin effort. Yes, Sandra.
Hello. So in looking at climate change scenarios, actually one of the biggest sources of uncertainty are essentially the economic models, which are what sort of fold into the various RCP scenarios. So I'm wondering, with sort of the ability of AI, if NVIDIA is thinking about sort of trying to reduce the uncertainty in the economic models that are sort of underpinning the various climate scenarios that are run with the physical models.
Well, thank you for that question. I have to first start with part of the uncertainty we see with these economic models is that they're not always publicly available. You know, can you get carbon emission data, reliable carbon emission data from China, for example? I mean, there's a number of examples we could cite. And so we haven't started working with those types of data sets yet, but have begun to think about how we might do so. We see they can apply at the global level, but probably more at the regional level. And our current focus has been strictly global for now because we're still in the development phase of this model. And you can see that we haven't quite gotten to anything that resembles a range that would be considered climate simulation. So we're still more or less in the weather scale, you know, with the medium range. Our next step will be S2S, or subseasonal to seasonal, before we actually get to the beyond that, to something representing climate prediction. Now, that didn't answer your question, I know. But I will say that I believe there's certainly NVIDIA research that can apply to the uncertainty that would exist with these models. But I'm going to go back to what I said earlier, is we're still questioning about how much of that data will actually be available in the public sector. That's still something that we're scratching our heads about. So we need to engage with people who understand that too. We haven't gotten to that point yet. It will come. And that's where I mentioned this open science and collaboration is going to be really important to our success. Thanks again for your question.
You okay? Okay. Interesting talk and very exciting opportunities. It seems, one technical question I have though is it seems that a critical part of this is the training data using the ERA5 reanalysis. So if you're planning to go down to kilometer scale, are you planning to develop with data assimilation sort of a kilometer scale reanalysis then that you can use in training your model?
We're just getting to the point where we're understanding the requirements of training at the very large scale. Well, let me back up even further. We're right now engaged in pure research, I'm going to call it, not really even applied research. And we're not certain this is going to work yet, because it hasn't been done. But right now, what we've seen has been very promising, and we've seen it applied to relatively coarse resolutions like the ERA5, the 30 kilometer. So what will be required to go to the 1 kilometer? I think we still have a lot to learn on the way there. Your question though, would we need some kind of a data assimilation capability? I haven't been in those kinds of discussions yet, so I can envision where that would help, and I know that we're doing research to try and implement that. But that would be more at the regional level, since we're hoping to spin off a regional forecast model. Since you look at the WMO today and they report the number of countries providing weather prediction services, some 90% of those are running regional models only, very few running global. So we're trying to affect that with this regional model approach, and that's where we'll apply this data assimilation research. So I guess the summary I would provide for your question is that there's too many uncertainties right now along the way to 1 kilometer global to know really what to expect. I hope that's a suitable answer. But I'll take that to the scientists and find out what I can gather exactly based on that question. Thank you.
Stan, one of the most interesting aspect is once the model, the AI machine learning model is well trained, then it takes only just a matter of seconds, right, to generate a simulation ensemble simulation results. So this is really interesting to start developing a large ensemble which can allow people to do a better uncertainty quantification. Now, the other aspect is when you have this large ensemble, we can start building better covariance functions which can feed back to data simulation efforts, right? So that's something has been a very challenging task for a long time because people don't really know how to build a realistic error information. So going back to Gary's point, the data simulation seems to be an important step. But along the way, the ensemble can help the more realistic and advanced data simulation.
Yeah, and people haven't really understood yet what massive ensembles could bring because people don't attempt them given the expense. You look today at the weather prediction community, ECMW has a 51-member ensemble. That's the largest that exist. I think NOAA is somewhere in the 20 range. But there was a study about 6 years ago done by Riken in Japan, where they took the NICAM model, and this was Professor Miyoshi. He did his PhD at UMD. Maybe you've read this work. But they ran a 10,000 plus member ensemble on, at that time, the K computer, which was the largest in the world. 10,000 member ensemble to help show what the benefits might be at such a large scale. Very interesting work. And we believe, based on that research, there's certainly advantages to a large ensemble. How that can then improve your uncertainty is research that we need to do. But we can generate these, as you mentioned, Professor Ho, we're generating a massive ensemble of, say, 1,000 members in a matter of seconds. You know, the advantage of that could be enormous. And that's really where we're driving. You know, these are, again, areas where we know they show benefit, but we haven't quantified that benefit. And that's a area where we think NVIDIA could contribute over what we see in the research community today.
So we have only 1 minute left. Any other last minute burning questions that we can ask Stan? All right, let's thank Stan again for this very inspirational talk. Thank you.
Thank you for the opportunity.
Great, thank you, Stan. And at this time, I'll ask our Climate Leaders Program students to gather on this side to my right, your left. For the next few minutes, I'm going to give you the opportunity as we lead into our poster session. I've only been at North Carolina State University for a year now, and I have to say I am highly impressed by the quality of students that are working here at the university, both at the undergraduate and graduate level. Working with the Climate Leaders Program, we have 10 wonderful students that have been my guinea pigs, and they've been wonderful in so many ways. We have one student who is actually participating in her internship in London right now. So her poster is here, but she is not. So 10 wonderful students. We cover 6 colleges from the university, so really working to be an interdisciplinary group. And we do have undergraduate and graduate students participating in our program. Tomorrow I'll give a little more information, but this is something you can participate in as a student, as a faculty mentor, and as a partner, either at the government level or private industry, nonprofit, working with our students. Our students work on communication, community engagement, leadership, and climate science through our one-year program, and then they serve a 3 to 6 month internship placement in a location and project of their choice. And so we're going to give them each 3 minutes, and they know I hold them to it, to highlight some of their work for you, just a brief snippet so you can talk to them, as well as the other wonderful 9 students that are here. Thank you with your posters as well. So as soon as they're done, we will flow right into our poster session here in this room. So without further ado, we have, Katie.
Sounds good. All right. Hello, everyone. My name is Katie Hollinger, and I'm a third-year PhD student in the Atmospheric Science program here at NC State. You heard a little bit from my advisor earlier explaining some of the work we do related to weather extremes and climate change. So the work I'm doing for my dissertation is supported by the Department of Transportation in North Carolina, and they want to know how much worse hurricane rainfall might be in the future. As we've heard from multiple of our talks this morning, hurricanes in North Carolina bring devastating rainfall, which can affect the streams as well as the transportation infrastructure and roadways. And so one of the ways that we kind of approach this problem is with these numerical model simulations that my advisor talked about a little bit earlier. So we simulate these hurricanes and see if we can replicate what they did in real time. Can we match the rainfall? Can we match the track? things like that. And then once we have a storm simulated, such as Florence, Matthew, or Floyd, we then can change the model environment to represent a future climate. And then we can simulate the same storm in a future environment. So we can see if Floyd happened again in the future, how much rainfall might it produce at that point in time. And we can get some understanding of what type of precipitation changes we can expect with climate change. But rainfall only gets at a piece of the problem. So knowing the rainfall doesn't necessarily translate to hazard information, to impacts-related information, and so that's where this program has really been beneficial to allow me to step into that space. My work this summer is with a hydrologist at UNC, Dr. Antonia Sebastian. So we're taking our rainfall data that we have from these storms and putting that into a hydrologic model to see if we can get at the impact side of the problem. Along with different rainfall data, we can also use these different land use parameterizations as well. So we can couple a future Floyd rainfall with a potential future Raleigh urban footprint. And we're really excited to be able to use this information to inform policymakers and decision makers about what kind of planning might be beneficial for the future to try to mitigate the amount of impacts we might see. The percentage of buildings impacted, the number of communities inundated, the number of roadways washed out. So we're really excited to translate this climate change information to a local and actionable level. So rather than take a regional scale like all of North Carolina might see a 50% increase of rainfall, we can say over Raleigh, that rainfall translates to this much inundation or this much impact. So if you want to know more, feel free to stop by my poster, but thank you very much.
Good afternoon. This is the home place of a North Carolinian displaced by climate change. 6 years ago this week, countless residents of Lenore County and other communities throughout eastern North Carolina were evacuating their homes, many of which stood in the floodplain of the rising Neuse River, swelling with rainfall left by Hurricane Matthew. 6 years on, North Carolina has a new challenge on its hands, determining a useful, community-oriented purpose for landscapes of climate retreat, like the one behind me. I'm Brian Vaughn. I'm a third-year Master of Landscape Architecture student in the College of Design. This summer, I had the privilege to work under the direction of Deputy Emergency Manager, Lenore County, Samuel Cornegi, and Dr. Gavin Smith. I set out to determine pathways and partnerships to address this challenge, which is one inherently concerned with land use, landscape design, community engagement, and partnership building. Now, a bit about how land where homes once stood become landscapes of climate retreat. FEMA's Hazard Mitigation Grant Program offers homeowners in flood-prone areas a voluntary buyout for the fair market value of their home. Restrictions stipulate that the land will be maintained in perpetuity as open space for maintained in perpetuity as open space for the conservation of natural floodplain functions. More frequent and intense storms justify the government's response to deliberately move people from harm's way. And in Lenore County alone, 1,485 acres of land have been acquired with this program and others like it. That's 50% more land than all of Centennial Campus. Yet at this time, no government provides dedicated resources to maintain the land as open space that can be used for community benefit. So herein lies the opportunity, that's a bit complicated, to create resilient outcomes and buyout lands. Land rendered available as collateral from climate disaster is envisioned as civic space, enabled by collaboration with community organizations and relevant expertise from officials in emergency management, the North Carolina Office of Recovery and Resiliency, and NC State, a land-grant institution with an extension mission. So consider this half-acre parcel behind me on Neuse Road, half a mile away from the river. The once owner of this homestead participated in the buyout program, and their home was demolished in 2018. Through meetings with a wide range of stakeholders, it became clear that we could develop a partnership with Lenore County agricultural education teachers to develop a number of open space options and parcels to realize them. And today, we're in the process of designing, budgeting, and securing a maintenance plan that's aligned with the needs of the future of Lenore County, students and their teachers. So a few questions that I invite this symposium to consider. What can we imagine for landscapes that have been sacrificed to climate retreat? How, in the face of climate change, might we transform these marginal lands into places intentionally stewarded by people and non-humans alike. And I invite you to engage in this conversation during the poster session. I'd like to invite Laura Gomez Rodriguez to speak next.
Thank you, Brian. Hi, everyone. My name is Laura Gomez, and I am a senior at NC State, majoring in biological engineering with a concentration in environmental engineering. And so with the Keats Climate Program, I wanted to focus on water quality issues. As we know, climate change is affecting how many communities are accessing clean and reliable water. And as an engineering student, I focus a lot on the science and engineering aspect of this. So with this program, I want to take the opportunity to look at more of the social aspects related to this. And so I had this past summer the wonderful opportunity to intern at RTI International in order to understand water quality perceptions in Latine populations, both here in the United States as well as in Latin America. And so I did this by conducting a literature review of various articles relating to water quality perceptions of specifically tap water or drinking water, as well as conducting interviews with participants of a previous RTI study in collaboration with La Universidad del Valle in Guatemala. And so one major thing that I learned is a general mistrust of tap water and those who manage it. And so one very interesting thing that I found was that mistrust of tap water in Latine populations here in the US is directly affected by mistrust in Latin America. And so the reason for this is because there's a cultural habit of just mistrusting tap water altogether. And as a personal Colombian immigrant myself, I can attest to the fact that me or my parents ever drink tap water, even when we think it's safe. And so another perception that I found is that of perpetual scarcity. And what this means is that when populations are faced with water insecurity or major pollution problems, the trauma from these experiences follows them even when they do have water security. And so one example was desalinization efforts in Peru and Chile. Now that the communities have access to water, they still refuse to drink this water, even when they're told it's safe. So one solution to this is education and community engagement. Many individuals said that they feared tap water due to not knowing how water systems work or where their water comes from. Additionally, community engagement, particularly community ownership, is incredibly important. A lot of communities don't like external federal or companies coming in to affect their water systems, so making sure that communities are involved in this is really important. And looking forward, I believe a lot more research should be done in this field, not only because it affects policymakers and community leaders, but also engineers and scientists, as we know that interdisciplinary studies help tackle the climate change challenges that are existing. Thank you so much, and I'll pass it on to Ishida.
Okay, hi everyone. My name is Ishita Kamboj, and I'm a fourth-year PhD candidate in Veronica Augustin's group, working with these lovely people that you see on the screen to my right. Today I'm here to give you a preview of my work away from the group, actually, where I was at Argonne National Lab with the support of the KITES program studying materials for lithium-ion batteries. So it's no secret that energy storage has been in high demand recently, but it's remarkable if you look on the chart to my right here that within only the next 8 years, we're supposed to over quadruple our demand. And if you break down this demand further, you notice that a large majority of that comes from electric vehicles and other transportation technology. It's estimated that one electric vehicle alone uses about 19,000 individual lithium-ion battery cells. And this is simply in order to meet the energy and power density demands to function a vehicle. And so you ask, why can't we just use one really big battery? Well, 3 minutes is not enough time to answer this question, so I'm going to ask you to come to my poster, but I'll give you a little hint that energy and power densities of overall technologies are largely governed by the active material that's participating in the chemical reaction with lithium ions during charge storage. And so during my time at Argonne, what I've been exploring is a class of materials called lithium and manganese-rich transition metal oxides. And these materials have gotten a lot of attention in the field recently for a couple of reasons. So first, manganese is about 37 times more abundant and 25 times cheaper than the material that we currently rely on in our lithium-ion batteries. So that's cobalt. And cobalt, I don't know if you guys have heard about it in the news recently, but it's typically mined in really tumultuous areas of the world politically and socioeconomically, and also it's been mined using notoriously unethical mining practices. And so it's in our best interest from a technological and also humane perspective to transition away from reliance on this material. But secondly, this class of materials also relies on excess lithium, which means that it can store more charge than a traditional lithium-ion battery that would be on the market today. The amount of lithium in the battery has a direct relationship typically to the amount of charge that can be stored. The difficulty comes in when you try to access this extra lithium that has kind of been squished in all these places in the structure, to say the least, is that we introduce some type of structural degradation. And so this can prevent upon rapid use, and especially when we try to access these ions faster and faster, so we try to demand faster charges and discharges from our batteries, this can introduce a lot of structural instability over time. And so at Argonne, my research is primarily focused on understanding how maybe small concentrations of cobalt can be used to affect the energy storage performance of these LMR materials. Specifically, cobalt is the main constituent in lithium-ion batteries because it can introduce high electronic conductivities as well as structural stabilities, and that's why it's everywhere we see. But I hypothesize that if we reduce the quantity significantly and include it in these lithium and manganese-rich batteries, we can still access the same benefits to allow us to charge and discharge larger quantities of this material at faster rates for an application like electric vehicles. And so if you'd like to learn what these graphs mean, I will resolve this thrilling cliffhanger for you at my poster. And now I'll turn it over to Kyle.
All right. So according to a 2022 study from the University of Washington, if we were to stop emissions today, as in right now, our likelihood of committing to reaching 1.5 degrees Celsius of a temperature rise is 42%. That likelihood only increases to 66% if moderate emissions continue through 2029. Now, this is not meant to scare you, but rather to emphasize the need for rapid emission reduction. And as a society, we are trending towards cleaner and more sustainable practices, but we're still heavily reliant on fossil fuels, and we likely will be for decades to come. So what this means is that going forward, the path to a net zero future in 2050 will require not only mitigation of greenhouse emissions, but also their direct capture from the atmosphere. And so while there are a number of ways that we can do this, direct air capture of CO2 in particular is a rather promising method for doing so. Direct air capture of CO2, or DAC, uses CO2 active molecules to trap carbon dioxide from ambient air in the atmosphere. This can then be released and injected into the ground for permanent storage. Now, doing this from an engineering perspective is relatively straightforward. It's been done before. However, the difficult part is doing this at low cost, and so that it can scale as a viable mitigation technique. And so Systera, the company that I've been interning with over the last several months, is looking to overcome some of these financial bottlenecks through a couple of ways. First, their CO2 active molecule, or their sorbent, is naturally abundant. It's comparable to baking soda, and it's much less expensive than designer molecules and much less corrosive than typical amine solutions. Second, from the energy standpoint, they have integrated heating in their systems that allows this trapped CO2 to release from their sorbent at much lower temperatures than typical. And third, from an implementation standpoint, their process equipment and their support for these sorbents have established supply chains, so they can take advantage of economies of scale very easily. And so combining these low-cost inputs with their modular design, Systera hopes to capture 500 million tons of CO2 by the year 2040. And so in summary, DAC represents a very powerful and important part of a climate solutions portfolio, and it instills hope for reaching this future where we are carbon neutral. And although this path to net zero by 2050 is daunting, it isn't insurmountable. And with companies like Systera quickly making waves, that future might be closer at hand than we think. And so if you'd like to learn more about what I've done through my internship and how I've contributed to Systera's goal, or how you might be able to, I encourage you to visit my poster after the session. Thank you so much.
Hello, everybody. My name is Jethro Singanzi, and I'm a third-year PhD student here at NC State in the Civil Construction and Environmental Engineering Department. and I work under Dr. Jeremiah Johnson. And a lot of what I'll be talking about today is focused on observing the synergistic effects of wind and solar resource blending on capacity credit and increasing regional grid penetration levels. So a lot of my work is focused on energy systems modeling, planning for the future as we try to decarbonize, because renewables have been proven to help us as we try to lower our carbon emissions in the future. So there's a general consensus in the energy professional space that proper capacity credit allocation can directly improve grid planning and resilience. And what capacity credit is a metric used to try to understand the benefit of various energy resources to the grid at any point in time. However, there is still debate about how to properly quantify that capacity credit for variable renewable energies, or VREs. So why is this important? Well, if VREs are given too little credit, their growth is disincentivized, which is not something that we want to have happen. And if they are given too much credit, there's also an increased risk of energy blackouts in the future. So I have been mainly focusing for the time at NC State that I've been working on this. I've been mainly focusing on understanding and trying to calculate the capacity credit for the open energy outlook regions of the United States. And what I've found so far is that when we try to calculate capacity credit for singular resources, their benefit to the grid is oftentimes not as great as if we account for them together or in different blends. And why is this important? This will help us as we provide information for utility planners and grid modelers in the future. And if you want to learn more about that, you can at my poster. And so far this semester, I've actually been at NREL, the National Renewable Energy Laboratory, trying to work on this more and understand, okay, how does my academic research relate to the more government research or industrial kind of research that they're doing? And I've been trying to compare my results from my own model to more robust models in the field. So thank you for your time, and if you'd like to learn more, you can come to my poster.
Hi. Hello, everybody. I don't know how to do this. I don't use apples. There we go. Hello, everybody. My name is John Barley. I spent this summer working at RTI. I'm actually still there, conducting a renewable natural gas modeling project. So what is renewable natural gas? Like it sounds like, it's very similar to conventional natural gas, except instead of pulling it out of the ground, we capture methane from a variety of sources. Those can be landfills, they can be hog lagoons, dairy lagoons, they can be from wastewater plants. So basically, we're turning trash into energy. You can also use gas to make a lot of other products that are very valuable. But why? Well, we can't keep burning things that come from the ground, but we can't necessarily stop burning things right away. So this is a really good stopgap. It's also a great way to improve the detrimental environmental effects of our waste stream. Just letting it sit out in the open and decompose and pump methane into the atmosphere is clearly causing problems, and we need to do something about it. Also, it makes a lot of other valuable products. It makes organic fertilizer. It can make a lot of other things too. I've spent a lot of time listening to other people, and I'd like to get back to them. One thing about renewable natural gas, though, is it's expensive. It's really cheap these days to pull it out of the ground, but the infrastructure that's required to capture it and upgrade it and turn it into something that we can then sell is not cheap. And without federal policies and other state policies, we wouldn't be doing it at all, because the people who do it wouldn't be able to make any money. So that's what my work over the summer was. How do those environmental commodities work? How do they get turned into money? And then how do they make it possible to protect our environment? If you have any more questions, I'd love to talk to you more at my poster, and we'll move on to Rihanna.
Hey everyone.
everyone. My name is Rihanna. I'm an undergraduate student here at NC State. I'm a sophomore, and I'm majoring in environmental science and plant biology, and I'm super excited to be here today. I've had so much fun, and I'm so glad y'all could make it. So my opportunity, I was fortunate enough to land an internship with the help of Dr. Marcelo Ardon at U.S. Fish and Wildlife Services with my supervisor, who's an ecologist at the Raleigh station in U.S. Fish and Wildlife. Her name is Michelle Mormon. And I had the wonderful opportunity to work with surface elevation tables. And what those are, they basically put surface elevation tables in wetland ecosystems to measure surface elevation, accretion rates, and how the soil rises and falls based on sea level rise. And there's this huge report of the entire southeast region at U.S. Fish and Wildlife Services, where they, his name's Zach, and he compiled an entire report showing the data of surface elevation tables throughout the entire southeast region. So there's like 53 refuges in the entire southeast region, and so he compiled that and put that in a report. But my project was, Michelle Mormon wanted me to subset this report so that it could be given to each refuge, and each refuge could have their own data on surface elevation tables, which are super important when looking at wetland ecosystems and looking at sea level rise. And so I did this in R, and I had not much experience in R going into this, and so it took a lot of discipline, a lot of learning experience, and 40 hours a week sitting and doing art is a lot. But I had I had a lot of fun, and I learned so much. And I was able to do that with the help of Emily Sy. She was an intern at U.S. Fish and Wildlife Services, and if you want to learn more about how to have an internship position at U.S. Fish and Wildlife, please come and see my poster. But I was able to make those reports for all the refuges that have wetland ecosystems and surface elevation tables. And it was super great, and I thank Dr. Ardon for all of his work and all of his amazing help. He's literally awesome. And Dr. Mormon, my supervisor, she's also awesome. And Emily Sy, who's in Antarctica right now, doing another internship as part of her master's program. Literally crazy. So yeah, thank you so much.
Hi everyone, I'm Allie Hayes. I'm a second-year master's student in the College of Natural Resources, and I'm going to talk about food and water insecurity issues. So the terms food and water insecurity are commonly conceptualized as periodic instances of supply-driven shortages that primarily affect developing nations. This isn't an incorrect assumption, but it is incomplete. Food and water insecurity manifest at the household and individual scales, regardless of the geopolitical region you're talking about. So as you can see from this image, we're looking at a global scale analysis of food insecurity, and we see nations that experience relatively high rates of food insecurity that are felt more or less ubiquitously across the national population, being highlighted in pink to identify them as highly food insecure. Meanwhile, we see higher income nations such as the US, much of Western Europe, and China showing near no food insecurity. However, spatially downscaled data tells us that this is not a complete story. In 2021, roughly 34 million individuals in the United States suffered from food insecurity, despite the near perfect score that we have received on this global analysis. And noticing this kind of divergence in the stories that we tell about food insecurity and where it is a problem based on the scale of analysis, I decided to spend my summer conducting a literature review looking at food and water insecurity studies across spatial scales in order to identify trade-offs between data that's presented at different scales, as well as identify gaps in the literature and some best practices. So in very brief, what I found was that studies that are conducted at the local and subnational scales provide some invaluable insight into distributional disparities between subpopulations within countries. Broadly speaking, they take a bottom-up approach, including stakeholder information and knowledge generation, and provide some very highly detailed data that is very accurate to the lived experiences of individuals suffering from food and water insecurity. However, global and national scale studies provide comprehensive data that informs policymakers on trends and interdependencies that are present in globalized food and water systems, which are very, very relevant to policymaking processes. Finally, I found that the topic of water insecurity is far less represented in the literature relative to food insecurity. And this has recently begun to change as crises such as Flint, Michigan, and the ongoing crisis in Jackson, Mississippi have received a lot of media coverage and shed light on how severe these issues are in countries like the US. However, the literature is still lagging behind food insecurity by about 20 years. So currently, food and water insecurity have increased over the pandemic, despite the projections of many economists and food and ag policy specialists. And I believe that we owe this in part to a lack of accurate and actionable data. And some of the studies that have successfully bridged this gap have used a mix of qualitative and quantitative analyses to provide actionable and accurate data. That's it.
Great, thank you. Ooh, that was close. We now welcome you to visit, along with these students, there are 9 other wonderful presentations that the students have put together. I got to do a preview as I put them all together. We know that we are cutting your poster time a little bit shorter because of earlier delays, but if you do not get to all of them or as in-depth as you would like, they are all available on the website now as well. But please talk to the students, engage them, share your knowledge with them, and learn from them as well as they're doing wonderful things. And we will gather back downstairs at 2:25. So enjoy. And students, please man your posters.
I got a thumbs up back there. I think we're good. All right, good afternoon, everybody. Thank you so much for attending this session. It's always a great sign when there's so much excitement at the poster session that we have to drag you back to the main session. Lots of great student research that we are very excited to share. So earlier today, we talked about climate science. We talked about ecosystem responses. If you're anything like me, I am thoroughly convinced we need to do something about this. And that is what this session is about. So we are going to have three speakers who are really well established, really impressive in this field of mitigation and solutions to some mitigation of carbon and carbon dioxide removal. So how do we solve this climate problem, particularly through this lens of science and technology? We have, the first talk up today is Dr. Wei Jun Tsai, who will be talking about ocean uptake of CO2 and carbon dioxide removal. Our second talk is Dr. Fanxing Li, who will talk about mitigation through redox active mixed metal oxides. And our final speaker is Dr. Veronica Augustin, who will do a deeper dive into materials for electrochemical and environmental applications. So for our first talk, if we could welcome Dr. Wei Jun Tsai. He is the Mary A.S. Lightheight Chair of Earth, Ocean, and Environment at the University of Delaware. He is a AAAS Fellow, an ASLO Fellow, an AGLU Fellow, and an expert on air-sea CO2 flux. Thank you. The floor is yours.
Thank you for the nice introduction, and thank you, Loy and Amanda, for inviting me. And I have to admit, my research probably is, furthest away compared with some others on the solution part, but I'll do my best to talk about the solution. So I want to talk about ocean uptake of anthropogenic CO2 and ocean-based carbon dioxide removal, and provide a coastal ocean perspective. Okay, interesting. So I have do a brief introduction first, and then talk about a CO2 cycle, CO2 flux and carbon cycle in coastal water, and then move into the ocean-based carbon dioxide removal. I will try to shorten the second part as much as I can, because I feel this morning's research already set up a stage for me. So, and you've seen this before, that, is there a point here, or? Oh, I'm not trying to see which one. Oh, here, okay. So this is the temperature, blue color, red color is CO2 over the, oh, okay. Over the last, few glacial, interglacial cycle, you can see with this interglacial, each time this CO2 is about 280 parts per million ppm, and during the glacial time, it decreased to 190 parts per million, and at the end of last glacial maximum and move to Holocene, we have this CO2 stabilized at 280 ppm for at least 1,000 years. And then we have that CO2 goes up really rapidly. And so when Dr. Keeling started the measurement at 1958 at Mauna Loa, and actually, so he nicely recorded this atmospheric increase. And in the fall of 1988, I took his class. This is from his original handout. And he came into the class, I remember, they say, okay, this last point was measured like 2 weeks ago. You feel that excitement of witness climate change. Of course, now, 2 to 3 decades later, and it was 1988 here, 350, and now 420 ppm. And human activity, it's been, scientific community consensus that the fossil fuel use and the land use are the main reason contributed to the atmospheric CO2 increase. And ocean has been playing a really important, or the only, sustained sink for atmospheric CO2 for the anthropogenic CO2, and then this is accumulation in the atmosphere, and some because the regrowth of forestry, right? So ocean plays a real important role, but on the other hand, because the take-up of CO2, ocean is acidified, so facing this challenge of ocean acidification with ecosystem and organism, particularly corals, for example, which will not really talk today. So traditional view, you have fossil fuel input, the land use, and ocean takes up a 2.3 gigaton carbon, 10 to the power 9 ton carbon, and then the rest is this so-called residual land sink. And that view kind of ignored the coastal ocean, and so this is more recent with the coastal. You don't look at the details. Basically, you can consider this from land ecosystem to the ocean through rivers, and it's a leaking pipe with CO2 going back to the atmosphere. And so that's basically my own research. I ask questions such as how much anthropogenic CO2 is accumulated in coastal waters, how do coastal waters hold anthropogenic CO2, and how do coastal ocean respond to CO2 addition. This is what my most recent 10 years research is on ocean acidification part, and which I will not talk today. And I will try to simplify these two on the next few minutes with ocean CO2 flux. And then adding a new question is really, what is the role of coastal ocean, how coastal ocean can be used to facilitate carbon dioxide removal. So let me first talk a little bit about carbon cycling and CO2 flux to build myself a little credibility, talk about this issue. So coastal ocean is really small, like particularly, so 7% for the, compared with the open ocean is the continental shelf, and then estuarine is really very small, 0.3%. However, the amount of CO2 released from estuarine is quite high in the, only not that far away from open ocean CO2 uptake, about minus 1.6 gigaton carbon. Now, what you read is a lot higher, like 2.5, for example. That is really anthropogenic part. So this is the contemporaneous, the total flux, and you have to add, because anthropogenic is compared with pre-industry. So that ocean was the source of CO2 of another 0.6, so give you 2.3, and now after 10 years, it's a larger number. So coastal ocean is really, an important link between land, ocean, and atmosphere. Now, I want to mention this, estuarine, we still has high uncertainty. So this number was what I did the most the last 20 years. We are pretty comfortable about 0.2 petagram, 0.25 petagram CO2 uptake or gigaton. And for the estuarine, there are large uncertainty, as you heard this morning from Chris' talk. But if we add vegetations, then there are even more greater uncertainty. But if we put that as a whole box, roughly it's actually a sink of CO2. Vegetation takes up CO2 from atmosphere, then release that to the water and go offshore in the way, to release in the estuarine like Pamlico Sound. But the offshore, the ocean, ocean continental shelf is a sink. So I'm going to just end this, of course, the carbon export to the ocean. So I started my career at the University of Georgia, actually, in 94, and I studied at Sapelo Island. So you see, CO2 was 3,500 ppm, and atmosphere was 360 at the time, so 10 times high. I'm taking sample, at the salt marsh, and then we move out to the South Atlantic Bight, starting, actually, I took Cape Hatteras, many cruise, drive to Beaufort and going down to to Florida, covering South Carolina, North Carolina, Georgia, and Florida. So we did a seasonal study, estimated CO2 flux in this region, and then also did a global synthesis. So one thing I did in 2006 is we put a CO2 mooring there and look at the CO2 increase. The blue color is the ocean, and this is the atmosphere. So the first few years, we saw this rapid increase of CO2, but when you build a longer time, it goes slower, and overall, it's still a little bit higher than the atmospheric increase. That is closely linked to the land output. So in the year of you have more land output carbon, you got a very rapid, the CO2 increase at the mooring. And this was 3 weeks ago. I was there and took a small boat to do ground truthing of the mooring. It was exciting, but I got a little bit seasick. And then we moved into Gulf of Mexico. I did the next 10 years of studying the Mississippi hypoxia area. And before I published a CO2 paper, we actually published a bottom water hypoxia acidification paper. So that is another story with my postdoc and students. So I'm going to skip this. And more recently, I focused more on this East Coast cruise. We call it ECOA, East Coast Ocean Acidification Cruise. Started with 2008, 2012, 15, 18, and we just finished the 2020 cruise. And so we have with students to do the CO2 and trend in this area, and then we now with the data we have allow us to look at a long-term trend. We can estimate very comfortably anthropogenic CO2 increase in the different water mass. And there are some interesting results. I need to move on quickly, and I'm going to skip this Chesapeake Bay and Delaware Bay study. Just to quickly mention, there are some, about Arctic work, and there are very large CO2 sink in the continental shelf area because the nutrient come in from Pacific through the Bering Strait, but the Arctic Ocean basin is really not a very large CO2 sink because that ice melt create a low salinity water mass there. It's not mixing down into the ocean to take up a CO2. So we just published an acidification rate paper on Science last week, Friday, so 10 days ago, in addition to some other paper about the CO2 part. So that pretty much my coastal ocean work, and now I'm more into the synthesis. I'm going to skip this part, and for the interest of time, move into this ocean-based carbon dioxide removal story. And to do this, I want to just point out that we will take the terminology, the units that the people doing the CO2 removal do. They don't use gigaton carbon or petagram carbon. They actually use CO2. So it's like a 3.6 difference of CO2 versus carbon. So all the unit here is really CO2. So just to mention that anthropogenic CO2 we produce as about 10 gigaton carbon, but 40 gigaton CO2, right? So currently there is ocean uptake about 9 to 10 gigaton CO2, and a land uptake about 12.5 gigaton CO2. I just want to point out one thing. We are talking about take ocean CO2 removal need to be at a gigaton scale to 10 gigaton. That has to be in addition to whatever it's naturally taken. So this should be an additional after CO2 uptake. So right now, according to this National Academy of Science, Engineering, and Medicine report, there are about 6-7 different methods proposed. Really, you can look at two different categories. One is to increase ocean's biological pump by fertilization, by artificial upwelling. That's also bring nutrient up there. But really, when you bring nutrient up there, you also bring high CO2 water up there. So I don't know how that will work. And then cultivating seaweeds, right? That's another approach. And so these are all increased ocean biological pump biological production. And then there are two other methods is really the physical chemical pump that is like this called ocean alkalinity enhancement. Basically, you add a base, you add a strong base or minerals to decrease sea surface CO2, and then let the ocean take up anthropogenic CO2. You basically enhance this physical chemical pump. And then there is this electrochemical engineering method, which is really break water to produce acid to dissolve or produce base, for that matter, and to dissolve minerals, basically enhance that alkalinity approach. So I'm going to skip the equations, but just to point out there are two really methods you can reduce sea surface CO2, either by add OH, hydroxide into surface water, or you can add carbonates. There are two different approaches, and in the next figure I did an analysis of how effective each could be. Basically, in this plot, we have the total amount of dissolved CO2, DIC, versus alkalinity, which is the base. So in this plot, you can see the equal iso PCO2 line, like PCO2 is 420 and 300 and 280, which is a pre-industrial CO2, and then 180, 190 is glacial time. So you really don't need to change seawater chemistry a lot. 1 to 2%, you will allow us to bring CO2 down to the 1980 level. That would be really enough to take a gigaton CO2 globally. What is difficult is how do you maintain that alkalinity, like you add hydroxide, which is very effective. But the challenge is when you add hydroxide, you could produce secondary mineral precipitation because you add immediately forming calcium carbonate precipitation. And another way people talk about add dolomite, calcite, that's not going to work because ocean is already super saturated with carbonated minerals. It's not going to give you the effect. Particle is going to drop to the seafloor. And silicated mineral, for the same reason, the rate of dissolution, like olivine, is 1,000 or multiple thousand years. So that's not going to work as well. So the hypothesis, the two questions is how realistic can you do that by adding, strong base or adding minerals? They are not going to work. So the proposal we did was to use coastal water, sewage and estuarine with low pH to dissolve minerals and to add base into that. So we hope that will allow us to, and then, once you add the base, because of low pH in estuarine or sewage water, then you can let ocean current, let river plume and ocean current to take it out. And particularly in the U.S. East Coast, for example, the city of Miami's sewage pipe that goes to Gulf Stream right away, and in the southeast, we have a lot of river estuarine with pH like 5, 6, very low, and with high organic matter in the sewage that could help to promote mineral dissolution. And unfortunately, we were not really funded. This is a cartoon in that paper we published just 2 months ago at that journal, The Innovation. It's like a 2-page idea to change this alkalinity to DIC ratio in the sewage because people already lime in sewage. What a sewage treatment does is convert organic carbon into inorganic carbon, and pH is too low, so they have to lime it. If you are already liming it, we could add more and then let the ocean current take it out, and you have to use the ocean water to vast area to take up CO2. So let me summarize and just this part. First, using high CO2, low pH, and low magnesium and calcium estuarine water and sewage water could allow strong acid base to dissolve without this inducing calcium carbonate precipitation and other issues. and you could allow minerals like calcium carbonate and olivine to dissolve. And there are other advantages. For example, we talk about having metal pollution once you spray into the ocean, but you could treat that in this nearshore facility. And we could actually have a co-benefit of reduced ocean acidification, because in coastal water you have this very serious hypoxia events with the ocean, with acidification. So another nice thing is the Gulf Stream. It goes into the deep Atlantic water and bury the carbon there for a long time. So that's pretty much what I'm going to present. Thank you. Oh, I'm sorry. This is ruins some preliminary work. We'll skip. Maybe someone have a question.
Excellent. Thank you so much. We're going to jump right into the next talk in the interest of time. So up next we have Dr. Fangxing Li, who is the Alcoa Professor and University Faculty Scholar here at NC State in the Department of Chemical and Biomolecular Engineering. His research focuses on catalyst and reagent particles with applications for green liquid fuel, CO2 capture, among other applications. Thank you.
Thank you, Jeremiah. Okay, so my talk would explain some of our recent work in terms of trying to reduce the CO2 emission from chemical manufacturing processes. Of course, you can address the CO2 problem by CO2 capture, which is highly important, whether you're capturing it from the air or in the ocean. The other aspect is how do we reduce it, and we produce less of them to begin with. So that's what this talk is going to be about. I broke it apart into 4 sections. A lot of these applications are based on so-called chemical looping strategy. We're going to exemplify how to use that for potentially clean chemical manufacturing and why should we care about it. And the second aspect is showing examples of how to tailor mixed metal oxide material to have the right redox thermodynamics. And third aspect, we need to modify the surface to make it catalytically active so that it can perform the function as both a catalyst as well as a oxygen separation agent so that we can couple multiple unit operation together to make the process more efficient. And then lastly, showing some new applications. So why should we care? In fact, the manufacturing sector accounts for about 30% of the primary energy consumption in the US. And within the manufacturing sector, chemical production is the highest in terms of the energy consumption and CO2 emissions. So if we look at these commodity chemicals, we produce a lot of them, and we also consume a lot of energy, and the energy typically comes from natural gas or other fossil fuels. As a result, you emit a lot of CO2. I'm going to highlight a few molecules that we have been looking at, and why should we care about them? If you look at the numbers, we have very large production capacity. I pick a few molecules that has different capacities, but generally they are in tens of million tons of levels. And also they emit generally about a ton of products of a ton of CO2, and sometimes it's 2 tons of CO2 per ton of product. How can we, the first question we ask is why, we are emitting so much CO2 and consuming so much energy. One commonality of how these chemicals are produced is they are equilibrium limited dehydrogenation or cracking process. And as a result, each pass you're making a lot of byproducts. You're not fully converting the feedstock, and the separation tend to be very energy intensive. In fact, the CO2 emission from the separation step could be very comparable to the production step. How can we integrate the two of them together, or somehow change this endothermicity into exothermicity to eliminate equilibrium limitation? That would be nice. So the catalysis community have been looking at this for a long time. Over the past few decades, people were designing catalysts for oxidative dehydrogenation of hydrocarbons. if you put oxygen molecule in there and burn the hydrogen byproducts, you would have a process where it becomes exothermic instead of endothermic, and in theory, you can get 100% conversion. Of course, that's when you have a perfect catalyst. And if we look at this picture, for all these different products, if we have a perfect catalyst to burn all the hydrogen byproducts, they go from very endothermic to exothermic. If we further calculate if we can ideally consume all that energy for CO2 splitting to make carbon monoxide, which is an important commodity chemical, we can actually convert them from a CO2 emitting process to a net CO2 utilization process. So the potential is there. The problem is the catalyst doesn't meet our requirement. It's not 100% selective. It doesn't give you 100% product yield. So looking at the limitation for existing oxide catalysts is there's a very well-established mechanism called Marshall equivalent. If you have metal oxide, oftentimes the oxidative dehydrogenation process occurs this way. You have a gas molecule coming in and react with active oxygen species to form the chemicals, but the replenishment of this oxygen vacancy occurs at a different site. So it's spatially separated even though you have a same catalyst particle. Now, there are two aspects. One is you don't have this perfect process because when you have oxygen and hydrocarbons together, it tends to have non-selective reactions because some of the sites are naturally unselective. And second is to produce that oxygen itself is very energy intensive. In fact, from a second law standpoint, you're only 25% efficient in making oxygen, and itself is emitting a lot of CO2 and very costly. So what we thought about in our group was to look at mixed metal oxides that we decouple this process spatially into two reaction steps. We could use a packed bed reactor and do the gas switching, or we could use a circulating fluidized bed reactor. But bottom line is we use the mixed metal oxides that would release its lattice oxygen and react with hydrocarbons to make chemicals. And after it gets depleted, generating a lot of oxygen vacancy, we move it to a different reaction step where we contact this reduced metal oxide with air. As such, the oxygen in the air would be pick up and filling up these oxygen vacancies, and you integrate the air separation step with the chemical production step. So you do two things at the same time, potentially avoiding this energy consumption, as well as potentially get much higher product selectivity as well, because the oxygen gas never gets in contact with the hydrocarbons. Now, we tend to focus on mixed metal oxide, for example, perovskite oxides, and with the B side containing at least one of these elements. But then we have a lot of choices in terms of putting A side and B side metals into this structure. So the question comes, how do we select the right material? So here's an example of our recent study where we use computations to help us to design the metal oxides. We use strontium ferrite as a backbone structure, and then we replace the A side and B side with different elements. And we specifically look at two different applications. One with high oxygen chemical potential where we can do air separation. So basically, if you put steam or vacuum on the metal oxide, the oxygen would release out. And then if you contact it with air, the vacancy would be filled up. And the other one is we use a reducing agent to create the oxygen vacancy, and then the metal and oxygen bonding is so strong that it's going to split CO2 into carbon monoxide. So we can easily figure out what is the desirable oxygen chemical potential range we will be looking at just by Gibbs free energy minimization. For example, for CO2 splitting, we need 10 to the negative 20 in terms of atmospheric pressure, equilibrium oxygen chemical partial pressure. For air separation, it's very high. And then we perform some high throughput DFT calculation, and that gives us 2,000 different materials, and then use that to train a machine learning model to figure out 5 cation materials. That's about 200,000 different materials. And first we look at literature. After screening them, we got about 200 out of the 2,000 material for each case. And then we look at literature. A lot of the already reported material fits in our prediction, and prepared some new materials for both applications, air separation and CO2 splitting. And about half of them, or more than half of them, work better than our base case material, indicating that the model works pretty well for material design, even though we took a lot of simplified assumptions in order to be able to simulate the results very quickly. So here's one of the applications for chemical looping air separation. This is the high oxygen partial pressure material working with an industrial collaborator, tested the material for 10,000 cycles with over 90% oxygen purity. In fact, it can be much higher if it's a bigger system because of the downstream, we have some dead volume. And then I would talk about how to apply them for chemical production besides oxygen. So these are all the possible chemicals that we can make out of simple feedstocks like methane or ethane or propane that's abundantly available. It looks like producing a lot of these chemical products appears to be energetically favorable, but the problem is CO2 and water sitting in the small dynamic well, and if you use any of these mixed oxide I mentioned about, you generally would get CO2 and water. If it's low partial pressure, you get some CO and hydrogen, but you don't get the chemical products you want. So that requires us to modify the surface to kinetically control it, to have active sites to catalyze these reactions. So I'll give 3 strategies that we have used to produce a few different chemicals. So our thinking process is simple. This is a more generalized strategy. Of course, there are other ways you can do it, but our thinking is if you have a metal oxide that's non-selective, what if we just cover it completely? And then you can avoid all the non-selective sites, and then we'll see whether this outside layer maybe can be catalytically active. So we have 3 different strategies I will illustrate. The first one, we call it an inert molten salt. So in this case, we use a molten salt such as sodium tungstate or sodium molybdate and so forth. And what happens is they have low melting points, about 700 C. If you mix them up, the melting point would be much lower. At high temperature, they tend to have very low surface tension, so they spread on these metal oxide particles and fully cover it. What happens is once it's covering the surface, it blocks the activity for CH bond activation, which is kind of counterintuitive because when we try to make chemicals, we need to activate the CH bond. But in this case, we can use them in tandem with a heterogeneous catalyst, or we can simply rely on thermal cracking to generate our chemical products like light olefins. So here's what we did in this case was actually a model catalyst of magnesium manganese oxide. This is not a perovskite, but it tends to have the right small dynamics and very minimal interaction with the salt. And a lot of perovskite also works. As you can see here, we form a core shell structure, also indicated from low energy ion scattering. The reaction mechanism really is a 2 parallel pathway. In the gas phase, you have thermal cracking of ethene to make hydrogen and ethylene. And then the oxide itself is very selective for hydrogen combustion. As a result, you get a net oxidative dehydrogenation reaction through a surface that's completely being inert for CH bond activation. So we test these material for over 1,000 cycles in a fluidized bed reactor, look at other improved promoters that can potentially fully inhibit CO2 formation. As you can see here, potentially you can get very high yields. Industrial processes in the order of 55 to 60% single pass yield. And also, if we do a process simulation, we find that depending on the assumption we use, basically where the fuel comes from, the CO2 emission compared to traditional cracking to make 1 ton of ethylene gets reduced anywhere between 64% to 87%. So that's a pretty good improvement, in our opinion, just by making the process more efficient. We also were involved in some scale-up activities. For this process, we plan to use a circulating fluidized bed reactor for ethylene production at large scale. And the next approach, again, coming back to the molten salt, but in this case, we want the molten salt to be active so that it can activate CH bonds and it can perform the operation without using another catalyst or can be operated at low temperature. So in this case, we look at lanthanum strontium ferrite type of material with lithium carbonate promoter on the surface. And what happens is we found that iron 4+ to 3+ transition give us the oxygen species that's very active, like peroxide oxygen species that can go through the lithium carbonate layer and activate the CH bond. For example, ethene would become ethyl radical and then gets released to the gas phase to perform the reaction. As a result, you can see here, there's very little cracking reaction, but we get very high yield, indicating pretty good catalytic activity. And this is one of the results that we did long-term cycles in a packed bed reactor. And the context of this application is right now we have a lot of rejection in terms of the ethane being produced because a lot of shale gas wells are producing ethane at very high concentration, but the gas line can only accept up to 10% ethane in methane. So we thought, if we have a packed bed reactor system at small scale, then we can convert the ethane to ethylene. And ethylene can be further oligomerized into liquid fuels with known chemistry. For example, nickel-based silica alumina type of catalyst. And as a result, you can do a distributed liquid fuel production so that it's more transportable. And the third aspect is if we can use the molten salt to cover it, potentially we can use also a traditional solid catalyst shell. And in this application, we are looking at styrene production. So we use a calcium manganate-based material as the core to store and release the lattice oxygen. And we use a potassium fluoride-based shell, which is basically the commercial dehydrogenation catalyst to perform the catalytic dehydrogenation reaction. So unlike the traditional process, which give you a yield about, again, 62%, I think, single pass, we were able to show that under optimal operating conditions, we were able to get over about 91% single pass yield for styrene. And then this can be applied for other alkyl benzene dehydrogenation, oxidative dehydrogenation applications. And last slide, I just show a few ongoing work that we are looking at besides ethene and ethene molecule. We look at propene to propylene, butene to butadiene. We look at combined CO2 capture and utilization for capturing CO2, and then utilize that CO2 for ethylene and carbon monoxide production, enhancing naphtha cracking, sorbent-enhanced biomass gasification for hydrogen production, as well as some other applications like NOx synthesis to trying to reduce the emission as well. So this just summarized the work. There's still a lot of things that we don't know, even though some of them, it looks very exciting. Here are the group members that contributed to this work. And also I acknowledge the funding agencies, particularly Keynote Institute for, a lot of our technology have benefited from Keynote support. With that, I would be happy to answer questions later.
Thank you so much, Dr. Lee. Jump right into our third and final presenter for this session. Dr. Veronica Augustin is the Jake and Jane Hooks Distinguished Scholar and a university faculty scholar here at NC State in material science and engineering. Her work focuses on synthesis and characterization of materials with very important applications for electrochemical energy and environmental technologies. Thank you. One more. Are these extras? These aren't yours, are they?
No.
Okay. Would you like to present those or no?
That would be a problem, right? Thanks. Hi, everybody. Good afternoon. It's really my pleasure to be here, and I really appreciate the invitation to speak today. I think this is a really fantastic symposium. As you can see, in engineering and science, we often talk about, bridging across length scales, and it really feels like we're doing that on so many levels. We started with satellite images this morning, and this afternoon we're looking at electron microscopy images. So we're really taking you down, and it's kind of nice to be at, starting from top to bottom, because that's where my group does the engineering and the science that we do. It's pretty daunting to be in the session titled Climate Solutions. People are looking at you for answers. The work in my research group, we really try to, first off, understand processes, and second off, we focus on electrochemistry. And so when it comes to climate solutions, I know we're supposed to have a YouTube presence, so we were talking about, capturing things we may say. The thing that I would want everyone to remember from my session, you don't have to remember the details of my slides, but climate solutions includes electrochemistry, okay? Electrochemistry is a really important component of climate solutions, and this is where my group does their work. incidentally. First, I want to acknowledge another part of climate solutions, which is training graduate students, undergraduate students, and postdocs in our group, because I think ultimately they are the ones that will hopefully save us all from all these significant climate issues. And we have quite a few of them from my group here in the audience today. Hopefully you all had a chance to meet each other, including Ishita Kamboj, who is the student who is part of this climate leadership cohort. And she's really, I think, embodies that whole component of being a climate leader. And she's at an internship at Argonne National Lab this semester working on lithium-ion batteries, and it has been a really fantastic complement to the work that she's doing in our group. So the work I'll share with you today is done with these graduate students and postdocs, as well as a number of collaborators, and supported through various funding agencies. So what I'll talk about today is our work on electrochemical ion insertion. And the first thing when you think about electrochemical ion insertion may be your lithium-ion battery, right? We all have lithium-ion batteries on us, perhaps more than one, at any given point in time right now. And this effort was recognized 3 years ago with the Nobel Prize in Chemistry. We just have the Nobel Prize announcements the past couple of weeks. And the technology was really to figure out a way that solid-state hosts can insert lithium ions reversibly, changing the way that we interact with electronics, and now changing the way that we will interact with our vehicles, right? And hopefully, perhaps ultimately, how we will interact with grid storage as well. So electrochemical ion insertion, kind of the bread and butter of the field, if you will, is working on lithium-ion batteries. And that's what Ishita has been doing at Argonne National Lab, is developing new lithium-ion battery cathode materials and architectures. This is a tremendous technology that's going to have increased manufacturing demand coming in this decade, primarily from the need to electrify our vehicles. So the question comes, how do we do this sustainably? How does the United States fit into this picture, given that global manufacturing in the US is only 10% of the capacity? And so that brings an opportunity for new chemistries, and that's where research labs at universities, I think, play a particularly special role in being able to investigate what are those new chemistries going to be. Sodium ions, protons, beyond lithium-ion mechanisms, lithium metal, solid state. There's a playground of chemistries available to us, and it's anybody's guess what the next holy grail will be, but this age of rechargeable batteries is here, and it's here to stay for some time. Other processes that we can do with electrochemical ion insertion and have impacts on how we utilize energy or energy efficiency include things like smart windows or energy efficient windows, because electrochemical ion insertion into a solid state host can modulate the optical properties of a material. So they can change color in the visible spectrum, but also, for example, in the infrared. We can use these mechanisms for what's called ion-based electronics, or electronics that operate a little bit more like brains, like biological systems that could perhaps be more efficient at large scale than current computing technologies. We can use these materials for ion separation, for things like removal of sodium ions or chloride ions for desalination using electrochemical processes, and even for more complex reactions involving proton or cation coupled electron transfer processes that might be used in electrocatalytic type behavior. So in our group, the way that we look at engineering across different scales is from the material all the way to the electrode length scale. So I wanted to orient you from a typical battery cell that might look like this, and then if you were to peer inside of it, that's layers of electrode materials and electrolyte sandwiched together. But if you look in even closer, we have this little schematic, we're zooming in, and ultimately there's these pictures that look like this. This is the crystal structure of the materials that are being used to reversibly shuttle ions in and out of their structure. This is an example of a sodium ion insertion material that we were studying for low-cost aqueous battery applications. So this mechanism is pretty important, could play a large role in different energy and environmental technologies. And the way that it functions is we have this very fascinating interface between our material, which may or may not be crystalline, and an electrolyte, which could be liquid or as well as solid. And what we're interested in our group is understanding exactly how these processes take place, what time scales, how to make them faster, how to make them more selective, and then use that understanding to design better materials. So these electrochemical processes can lead to changes in the host materials, electronic, optical, chemical, structural, mechanical, and so on. And so that gives us a lot of responses to play with when we study the electrochemical signal associated with these materials. One thing you might ask is, well, why did lithium-ion batteries become such a dominant energy storage technology, rechargeable energy storage technology, when there are many other mechanisms that can be used, even electrochemically, to store charge, including ones that actually can store more energy? It turns out that insertion processes kind of have this Goldilocks scenario, where they really optimize the kinetics and the number of electrons that can be stored inside of a solid-state host, so that you have that nice balance of not only what's the capacity of the material, but also how quickly you can access it, and related to that, how long it will cycle for. So that's why these technologies ultimately have become so dominant in energy storage. And then electrochemistry, like I said, that's the key word I want to have from my presentation. Why electrochemistry? It turns out for many of us, this is the golden age of electrochemistry. There's really never been a better time to study this field. I think a key reason is the reason we're all interested here today. It's this ability to convert between chemical and electrical energy is really, I think, fundamental to the search for global and sustainable energy. So we're talking about CO2, the chemistry of CO2, how to utilize energy more efficiently, and being able to go between chemical and electrical forms of energy efficiently is really what electrochemistry is all about. The other reasons that I have listed here is why now, right? This is not necessarily, electrochemistry is not a new science, but why now? We have this ability now to have experimental and data science tools to observe electrochemical processes at atomic scale. And I'll share with you a couple of examples from our research where we come close to that. We also have better synthetic capabilities than ever before to control molecule and material composition, shape, and size. And then we have these computational tools to bridge experiment with theory. So it's a very exciting time. But don't just take my word for it. According to the New York Times, it's a great time to have a degree in electrochemistry. Okay. So one of the fundamental questions that our group is asked, like I was asking, like I said, we work at this kind of smallest of length scales, thinking about how atoms and molecules interact together, is a question about where does the electrochemical interface end and intercalation begin. So in particular, we're working with these layered materials, these porous materials that confine water molecules and cations. And there was a question about how this mechanism takes place when the interlayer of these materials contains not just a cation that's inserting, but also structural water or other types of solvent molecules. And so to approach this question, we took a look at a material called bernesite, which is a mineral form of manganese oxide. It forms this layered structure. This is what a unit of that crystal structure looks like. These are manganese ions here in the blue. The red atoms are oxygens, and they're separated through this interlayer that contains water molecules as well as potassium or other kinds of alkali cations. It turns out that this material is of interest not just for high power energy storage or what we call electrochemical capacitors, but also for things like desalination and catalysis, like electrocatalysis reactions. This material, when we synthesize it in the lab, it has this kind of morphology. You can see the scale bar here, 500 nanometers, very different from the Google Maps images this morning. And this is an X-ray diffraction pattern showing the crystalline arrangement of that material. And so here's that connection between what we do in the lab, which is characterization of the structure, showing, for example, flexing of the interlayer, and what our collaborators can do computationally, where we're able to bridge from theory to experiment that's so powerful in material science and engineering these days. We were able to show experimentally that this material, it has these layers that flex as cations move in and out, and we apply a potential. Our collaborators at UC Riverside modeled this process on their computers, showing the same exact thing. And exactly the more detailed reason for that they were able to obtain from their simulations is that this process required basically counter movement of potassium cations and water molecules for the reaction to take place. And then another type of simulation result are these reactive force field grand canonical Monte Carlo simulations that are showing exactly what that interlayer is doing and gave us clues as to why the electrochemical response of the material is so fast. It has to do with these water molecules basically acting a little bit like pillars, exchanging places with potassium cations, and keeping the structure intact so that it can cycle for many, many, many cycles without undergoing deterioration, and also doing that very quickly. Okay. The next thing we ask, we want to understand these fundamental interactions of the electrode materials and the electrolyte, is how do we assemble these materials to make an actual electrode, right? I showed you before that a battery cell looks like this. It's composed of sheets of electrode materials, and those electrode materials, the way that they're packed together is usually something like this. And there's many, many things that influence exactly how these particles pack together. And ultimately, what we want is to have an electrode architecture that maximizes the materials that we have inside, particularly when we use more costly materials than the manganese oxide I was showing on the previous slide. It turns out that we oftentimes don't maximize the kinetics inside of these porous materials. This is a beautiful paper that comes from one of our collaborators, as a contributor, Professor Partha Mukherjee at Purdue, that shows that in these porous electrode architectures, you oftentimes have concentration gradients that develop across the thickness of the material. And this was a simulation done on vanadium oxide particles that was complemented by what are called operando X-ray diffraction results done at a synchrotron facility. The idea here is that the outcome of the study is that these porous electrodes do not charge and discharge uniformly. We are not packing them as efficiently as we could to maximize the power capability. And so even though this kind of slurry electrode architecture where we mix powders of materials and cast them as a sheet is the mainstay of the electrode of the battery industry, the process the outcome of that technique is not ideal. It's a little bit more of an art than a complete science because we don't have complete control over where each component is placed. And particularly if we start to incorporate materials that are non-spherical or nanoscale, that electrode architecture will start to really deviate from what we want ideally. What's also illustrated in these pictures is that these electrodes are composites that incorporate not just what's called the active material, which is where the ion insertion takes place, but also things like binders to stick the particles together and conductive additives to increase the electronic conductivity, as well as porosity for that liquid electrolyte to permeate through. So what we're doing in our group is we're thinking about ways to move beyond slurry electrodes. That's a collaboration between our group, the group of Philip Bradford here at Textile Engineering at NC State, and Partha Mukherjee's group at Purdue University to think about how do we have a more deterministic or more controlled electrode architecture. And this is part of the work that Ishita Kamboj is doing here at NC State. So we came up with this process where we take carbon nanotube foams developed in Philip's group at NC State. We use electrodeposition as a room temperature aqueous process to deposit our metal oxide onto the surface. We can get this nice homogeneous coating, and then with these electrode architectures now, we can nicely control mass loading and areal capacity through the electrodeposition process. And I mentioned that our collaborator here is Partha's group from Purdue, and the idea is that we're going to be combining this process that I showed you on the previous slide, where we have more control over the placement of each component, with the phase field modeling that is done in his group to basically digitize the electrode architecture. So how do we build up these electrodes such that we actually know exactly what is going to be the electrochemical performance from these materials? So finally, just want to say thank you again to all of you for your attention, the research group and our sponsors, and you can reach me here if you have any questions or comments, and I'm happy to take questions during the panel.
Thank you so much, Dr. Augustin. Amanda, how much time will we have? We started a little bit late? 15 minutes. Great. Okay, thank you. Sure thing. Jethro, do we have any? Oh, okay. So if there's any questions, please come up. I have a couple big picture questions. We were really into the science, and I'm going to take a step back and try to think about how we can deploy some of these options, some of these technologies, as they relate to big scale mitigation. And so, Dr. Augustine, I'm going to start with you. And it seems like right now the dominant chemistry for lithium-ion batteries are cobalt-related batteries, and 2/3 of cobalt is produced in the Democratic Republic of Congo. There are supply chain issues that are related to this. Do you think it will be easier for us to clean up our supply chain, to fix some of these issues that carry with them their own negatives, or to change our battery chemistries?
Right. So right now, the automakers are very aware of the issue with cobalt, and they're moving rapidly away from cobalt in the cathode material. So lithium cobalt oxide was the first chemistry that was commercialized in 1991, but since that time, there's been significant drops in the cobalt content of the cathode, such that I think the next generation, for example, Tesla batteries will be using lithium iron phosphate as the cathode material. So there are other chemistries available that are still insertion chemistries, lithium ion insertion chemistry. So that's definitely taking place. From a solid state chemistry standpoint, it turned out that cobalt did have, certain beneficial things from the periodic table that it just was so good at what it was doing in the structure. And that's actually part of the work that Ishita is doing, where she's sitting right there, at Argonne, is exactly addressing that question of, how do we do that? But it is a kind of a balance. And so in the near term, the lithium-ion battery chemistry is exquisitely detailed in terms of exactly, it's like a pinch of this, a pinch of that, a pinch of this. It's very beautiful. But in the long term, it does become a question of, what can we have multiple battery chemistries, for example, for different applications? That kind of is the ideal, would be like, oh, I have this application, maybe I can use a different chemistry. But there's market forces and economic forces at play too. And those can become really important. So even though lithium-ion batteries may be overkill in some applications, because they are manufactured at a lower cost than some of these newer technologies, they may end up becoming the dominant even in those other sections, is what I'm trying to say. But we do have a lot of options to play with.
That's great. Thank you so much. Okay. Yes, please.
Hi, thank you all for your talk. My question is specifically directed towards the ocean alkalization, so I think Professor Kai's talk. So this concept of raising the pH of the ocean sounds really difficult to do, in the sense that you probably need like a lot of base in order to accomplish this. And I was wondering what the consequences of this could be. Well, first, how much do you need to raise the pH in order to notice the benefits in being a carbon sink? And what kind of effect, how do we know what kind of effect it will have on things like glaciers or the aquatic life and marine ecosystems that we honestly, it seems like we don't know much about the ocean in general. So I wonder where this research field is getting a lot of its information from, if it's models or empirical evidence or et cetera.
You're definitely right. We don't really know much, and thank you for the question. Actually, it's interesting that the real challenge is not in increase the pH or how much base we need to add. It actually doesn't need a lot. As I did a calculation in that DIC to alkalinity surface, if we want to bring PCO2 down from 420, which will be in the next couple of years, to like a 1990 level, like 390, 370, that create a 50 ppm SiCO2 gradient. If we can do that on a global scale, that will give you 10 gigaton CO2 uptake. So it's not how much we can, reduce the CO2 or increase alkalinity. That actually is not that hard, although it's still hard. What is really challenging is the ocean is not a stationary system. When you add alkalinity to that and then quickly take CO2 into the system, so DIC also increase, then that reduce the gradient of CO2 across SC. That's one issue, so that reduce the efficiency. Secondly is really ocean mixing. So it actually alkalinity will mix into the deep ocean, lost the efficiency. And if you're going to increase the whole ocean, then it's really not going to be practical. So Loy, actually, his group did a simulation for the Gulf Stream system, and they did beautifully. I didn't show this last slide to show a promotion of CO2 uptake. However, it's like only less than half of what I would predict initially with that capacity. It's because you're going to lose that alkalinity to somewhere else, and and other people did some global simulation. It takes like 80 years to achieve a significant part. Even that, it's not like to 10 gigaton. It's a few, gigaton CO2. So, and also the other factor is, with the metal pollution and ecosystem impact, they all need studies. So it's a massive challenge. Thank you.
Just to really hammer home this being a solutions panel, one of the things that I wanted to ask you, it's sort of a three-part question, is for each of your respective fields and your proposed solutions, what do you see as the current bottlenecks or restrictions preventing your solution from being sort of the mainstream or at scale? How do you think we would overcome these, or what needs to be done? And do you have any estimations on how long it would take to overcome these problems?
So bottlenecks, solutions, and timescales. Dr. Lee, do you want to start?
Is it okay? I think the bottleneck in applying new technology for commodity chemical production in the chemical industry is really, the capital, the large capital that's required. So if you talk with any chemical company, they already have their plant invested tons or decades ago, and the billions of dollars has already been fully write off. They would very much like to operate the plant as such, as opposed to building a new plant. But over the past few, I think year or so, I think things are changing because they are more serious about reducing the emission. A lot of major chemical companies announcing that they will get net zero by 2050. A lot of them 2050, some of them more aggressive. So talking with some of their technical people, even though CEOs, they promise that, but they don't really know how to do that. It's easy to get 20-30% reduction just by some optimization or buying renewable electricity and stuff like that, but reducing it to net zero is really hard. So now they have the push to adopt new technology potentially, but still we are talking about billions of dollars of new investment for example, an ethylene plant. So that's gonna take skill up and stuff like that. In terms of putting a timeline, I don't think I'm able to say that, because if you look at a lot of DOE, Department of Energy projections, they oftentimes, they are off by decades. So.
Scale up is a challenge. A few years ago, I was at an event that was sponsored by BASF and VW, and it was in batteries, and it was really clear to me that the automakers, they're like, we've made this space for the car battery, we have this supplier that has to make this much material. So if you're coming in with something totally new that will have a different form factor, or you don't have it at the scale they need, they're not that interested in your technology. So that's always a challenge, but at the same time, it's also realized that with for example, lithium-ion batteries, the global supply chain is really concentrated in one part of the world, and that becomes a national security issue as well as an energy issue. So new chemistries is one way to overcome that problem, because otherwise, how do you gain control of a supply chain? Well, it's probably a question for the next panel. It may not have a pretty outcome, right? So I think that's where new chemistries, new technologies, we always have to keep pushing that and investigating new things, because you never know. And we also don't know whether the chemistry and the things that we're working on today, what the impact will have in 10 years, 20 years, and so on. So in defense of fundamental science, what we're studying today, we think we're looking for the next lithium-ion battery, but we might be looking for the next battery that changes the landscape like lithium-ion.
Great. From my point of view, I feel this lack of willpower. We technologically, I feel there's still mountain challenge like ocean alkalinity enhancement, for example, but at least in principle, it's not that far away. We can move forward, but how you could call that this consensus willpower, or economically with a sufficient incentive. But we need that, but recent development seems very encouraging, like the private industry actually moved before the federal government to come up with money to support, like this additional venture project. We unfortunately didn't get funded, but at least we were selected for the first round with competing ideas. What we lack, the reviewers, they really like our idea of coastal, sewage, these low pH water, but they were disappointed that we don't have a real field test, and that was partly, I also mentioned this barrier, like I contact the city of Miami's sewage treatment plant and maybe Philadelphia, it was just not moving anywhere, and so I was kind of discouraged in that part, but I think maybe I should do a smaller step, like with a local county level sewage, smaller, like to demonstrate something first, and also if it's still right, we need a really international collaboration to move forward. For example, it's not a good idea seem to collaborating with China now, but I see they have a very strong, this willing to move forward with a lot of these carbon dioxide removal technology to try that, and so I guess we should try different method approaches, because we are really running out of time. As you mentioned, even without releasing any CO2 into the atmosphere, we're not going to get to that 1.5 degree. So we need to remove some. This, only a few years ago, geoengineering seems like a little dirty name. Right now, people come back and like it. They start to.
Thanks, everybody. So I'm going to start with something Veronica said, but maybe ping back to the rest of you, which you said that you told us we had to all learn electrochemistry, but then you switched modes partway through and said that slurries are an art. Fabrication using slurries was an art, and that there's a significant challenge there that's just geometry, right? And so I guess I'd like to have a sense, and this might be for Fanxing as well, and possibly Wei Jun, but like to what extent are we not using morphology? Is there untapped territory using morphology as an engineering space for some of these same things for which we have the chemistry? Is there space there left to explore that you hinted at? Oh, no.
Yeah, it must be out because there's nothing on here. But there are different ways to use morphology, at length scales and battery materials. But certainly, one can envision that having a well-architected electrode, which would obviously involve the use of geometry and understanding how lithium ions move inside of the material, how lithium ions will move inside of the liquid electrolyte pore space. Building that together would let us really harness that technology better. And that's important because we would like to be operating with the maximum utilization of our material. And we're not doing that right now, particularly from the power standpoint. So if you want to have high power applications of lithium-ion batteries, then having this perfectly architected electrode is the goal. And so there's a lot to do, I think, in that space.
Thank you for the excellent question. From thermal catalysis standpoint, the morphology is relatively less important if you think about it. So you need porosity, pore size, the right pore size distribution. But on the other hand, you do care about the particle size and hydrodynamic diameter. If you're looking at fluidizing the particle, transporting them, how strong they are. But on the other hand, if we go to atomistic scale, then there's a lot of very exciting work in terms of looking at active sites and potentially perform tandem reactions. And even in that case, like when you put two different sites at different distances, you can get very different results. So I would say, if you look at traditional plants, they probably care about catalyst, diameter and, pressure drop and stuff like that. But there's certainly room about, your question.
We are almost out of time. I was, if I could take the liberty of asking a question for our students. So the students who want to get into climate solutions, we recognize that we need interdisciplinary solutions. What is the right point in one's career and in one's research to really engage in this? Do you need to focus on disciplinary expertise in graduate school and then broaden out, or do you need to start immediately and engage with other scholars?
That's a challenging question for every professor, I guess, right? There's advantage or disadvantage of either way. I think, this is the right time, so you should.
Well, so definitely study electrochemistry. That's for sure. Even if you don't want to study it in depth, you will see that electrochemical technologies will come up as solutions, and it will be good to understand, what someone's proposing in that with these schemes. But I would say, I kind of think that graduate school, it's a time that you can delve deeply into your passion as a scientist and engineer. And for some students, that will involve going into policy. For some students, that will include going into entrepreneurship. And for others, it might be deeply focusing on your discipline. And I think we need all of these characters, and the main thing I would ask is that you find what is going to be your superpower that you gain from being in grad school. And I think one of the nice things at a place like NC State, and we were just talking about that earlier, right, is that there's classes that you can take as a grad student. You can take my class on electrochemistry of materials. You can take Professor Johnson's class on energy systems and sustainable energy. And you can kind of go in between those worlds. You can do NSF I-Core for entrepreneurship. And the key is to try to find out what's your passion, because that's what's going to be sustaining you when you leave. And I think we just need people who are passionate about whatever it is that they're doing. That would be the perfect solution. We don't need everyone to do the same.
What a nice note to end on. Thank you so much. Can we please join me in thanking our panelists? What great presentations. We will let you know how long the break is very soon. And the answer might be 0, so don't go too far. Okay.
So while we're transitioning, maybe you need to stand up for a minute. It's going to take a minute for the speakers to come on down, shake it out, move around for a second, and we're going to get going in just 1 minute. Day before the reception, so you know what this panel stands between you and is some more refreshments, perhaps some more standing and socializing. But thank you for sticking around. My name is Erin Seecamp. I'm currently the director of the Coastal Resilience and Sustainability Initiative. If you don't know about it, tomorrow you can learn more. In 5 minutes, you'll hear all about it. But I've been asked today to moderate this panel on socioeconomic and policy solutions. And one of the interesting things that I come to this with is actually hearing from the last panel, particularly Dr. Augustin talking about market and policy forces that really are going to shape our future. And so our conversations today are with, we have Amanda Martin, who received her PhD at the UNC Chapel Hill. She's the Chief Resilience Officer with the state of North Carolina, and is working with the NCORP program. And then we've got, she's formerly the principal planner with the state of Rhode Island. And next we'll have a talk from Gavin Smith. Dr. Gavin Smith is in urban and regional planning from Texas A&M. He is currently a professor here in the Department of Landscape Architecture and Environmental Planning. He serves as an advisor to 4 governors on issues tied to disaster recovery and hazard risk reduction. And then for a unique twist to your afternoon is Dr. Jonathan Casper, who received his PhD from the University of Northern Colorado. He's an associate professor here at NC State in the Department of Parks, Recreation, and Tourism Management, and he's a founding member of the Sport Ecology Group. And so for each of them, you can see the different topics of their presentations here. I did try to ask them to weave in 2 questions into their presentations. The first one is really focusing on a key area of innovation. And then the second one is really focusing on recommendations to students. And with that, and our limited time today, I will turn it over first to Amanda, and welcome to NC State. Although I'm certain you've visited our campus.
All right. Does this distance work from me to the mic? Can you guys hear me? All right, well, thank you for having me. My name is Amanda Martin. I'm the state's Chief Resilience Officer. I work at the North Carolina Office of Recovery and Resiliency, which is in the Department of Public Safety. But a lot of the work that we do is to coordinate and try to ensure that all the different actors in North Carolina are working together in a strategic way. And so a lot of what you'll hear about today is just about the big picture of state policy and climate adaptation. So to introduce my office, it's a relatively new office. We were created in 2018 by the legislature, got started in 2019 to administer disaster recovery funds from Hurricanes Matthew and Florence. At the same time, the governor decided that he would like the state to have a chief resilience officer. This is a new occupation, a new job title. It was sort of created by the Rockefeller Foundation, which placed chief resilience officers in cities around the world for a period of, I think, 5 years. They were supported. And it kind of generated this idea that there should be staff dedicated to the issue of resilience. And these staff should not just be experts in resilience, but should be experts in convening and collaborating with other kinds of departments that have an important role to play in adapting to climate change. So that's what I try my best to do. So let me paint a big picture here. When we talk about climate adaptation, often the first place we start is in understanding our climate vulnerabilities. And there's a lot of different ways that we can go about doing this. You can do it with a very technical lens. You can do it with a very personal and social lens. I'm going to touch on some of the big themes of climate vulnerability in North Carolina. So the big starting point is just the kinds of vulnerabilities that we have, the kinds of climate hazards that we're vulnerable to in North Carolina are many, and that's just by our physical location. So we talk a lot about flooding in North Carolina, and we have multiple sources of flooding. We have flooding that comes from rainfall in our rivers. We have stormwater flooding in our cities, and we have coastal flooding. So that might come from a coastal storm or from sea level rise or even a high tide. We also have other climate hazards that it's critical for us not to ignore, even though flooding often takes center stage. So those are hazards like high heat. There's a different profile of the kinds of impacts that high heat has on the people that are vulnerable to it. We have risk of drought in the state. We've had an unusually dry summer here. That increases risk of wildfire. So there are many climate impacts that we want to, climate hazards that we want to be thinking about when we talk about building resilience to climate change in North Carolina. We also have a very quickly growing population around here. It's no surprise. You'll see it in other parts of the state as well. And in many respects, that's a good thing. It's a sign of the vitality of our economy, quality of life that we can offer. But it's also complicated because it brings more people and more infrastructure into zones of risk for climate hazards. And it adds, as we develop more impervious surfaces, can make runoff problems that can contribute to flooding problems as well. And then on the other side, you have rural populations that have a shrinking population base. They're maybe economically depressed, and they don't have their own resources to adapt to climate change or to build up their resilience. So there's kind of challenges on either end of that population and economic growth spectrum. We have a history of development in the floodplain that's common across the United States. There are many historic and current reasons that we see development in the floodplain, and it is continued nearly unabated in North Carolina. We have a really bad problem about continuing to build in dangerous places. And then I want to say we also have a problem of inadequate affordable housing where people don't have good options necessarily if they're low and moderate income about where to live, so they may need to choose to live in a place that floods frequently, and persistent poverty that kind of on the other side of the equation continues to keep those families from having income to be able to put towards housing options or other kinds of things that can make us as individual households and families more resilient. So what's at stake? I think I've mentioned a lot of different things that are at stake. I just want to highlight that it's everything from wildfire to public health to ecological concerns. So it's very vast and it can be very overwhelming. So we try to take that strategic, smart approach to the impact that we want to have. The final thing I want to say about the kind of what's at stake piece is that this is our future generation. And the investments that we make today really tie our future, the next generation, into the physical built environment that we create. Okay, so if we know that our climate is changing and we do not alter the way that we put infrastructure into the ground, we're hemming future generations into having to pay for that decision. So that's kind of my ultimate message about the impact, is that we really need to think about what we do today and how it will affect North Carolina 20, 50, or 100 years in the future. All right, so what is resilience? When we talk about climate resilience, people use a lot of different definitions, and partly because it's a really great word. We don't have another word like it in the English language. There are two analogies that we like to use when talking about resilience. The first is a swinging door, and this is kind of an analogy. So say you've come here today, you're in the auditorium, we take a break, and you go out into the hall and you're chatting up your friend you haven't seen in a while, but you're standing right next to those heavy auditorium doors, and someone comes out, the next person comes out, and accidentally that door swings open and it bumps into you. And so, hopefully nothing bad happens. Maybe you sort of like fall over, hope you don't fall over. But you might stumble or take a step over. And at the point where you recollect yourself and your friend is still there, what do? You take a step away from that swinging door. You learn from the past, from your experience, that standing next to that door is not a good place to stand. And that's what we mean when we talk about resilience. It's not just about building back to where we were before, but what's the best that we can build to be, given what we've learned from hard things that have happened. The other model that I like to use comes from the pandemic, actually. It's called the Swiss cheese model. You may have heard about it. And it posits that there are, you have this person who's on the left, and you have germs, or let's just say a bad thing like climate change happening on the right. Okay? And there are all these layers of protection that we want to put up between the person and the bad thing. And what we know is that, so in the pandemic example, you have things like washing your hands, wearing a mask, avoiding gatherings. This is from an earlier point in the pandemic. I should have started out by saying that. But there are all these measures that we can take, and we know that none of them are 100% effective. And that's why it's so important that we use multiple layers of defense. So when we talk about resilience, we want to be thinking not just about our hard infrastructure, the things that are made out of cement. We want to be thinking about ecosystem services and the way that nature protects us. We want to be thinking about community cohesion and the way that we look out for our neighbors. We want to think about political leadership. So there's all these different elements, and we don't want to rely on any one element. Instead, it's that compilation of all these protective elements that are important to resilience. These are some of the elements that we think about when we think about resilient communities. We think about land use. So I'm a planner, and so land use is always at the heart of where I start understanding what a community is all about and their history. Land use is really at the heart of especially our flooding problems. It's that we haven't figured out how to create a place for water. We just think about getting water off of, get it off of my property, get it out of my community. But we haven't thought enough about where water is going for us to be able to live well with the amount of water that we have and that we will have in North Carolina. We, of course, have infrastructure that helps us be resilient to climate change. There's that social and economic capacity, connectivity piece that's important. And as a Department of Public Safety employee, I'm contractually obligated to talk to you about emergency preparedness. It's a very important part of resilience as well. All right, but there are challenges in North Carolina. What are some of the things that make it hard from a policy and planning perspective to achieve that kind of resilience? Well, the magnitude of the problem is hard to comprehend. I don't think I need to tell all of you that, but when we communicate with elected officials or with the general public, it can be hard to say how extremely precarious a situation we are in, and especially how to say that without making people feel like totally defeated or just sort of not being able to work with the message that you're bringing. There's another policy challenge is expectations about popular solutions. A lot of people think that we can just engineer this problem away. And what we have to say is, no, we need many layers. We can't just take a mass engineering approach to trying to, especially for flooding, trying to like shoot all the water out of the state somehow. That's not a promising direction for us. Surprisingly popular idea, though. And then on the other hand, the expense of those proactive solutions. So something like preventing development in the floodplain is very expensive, both because floodplain development in some areas is very high value, like along the ocean, and that can be a really important part of a local government's tax roll. It is generally very politically difficult to oppose development in the state. And there are many of our affordable housing options, unfortunately, are located in the floodplain. So there's kind of like all these ways that the proactive thing that we should be doing, which is building outside of the floodplain, is expensive in many regards. It is difficult to coordinate across multiple branches of government. We got to build in transportation. We need to build in natural and cultural resources. We need to build in health and human services. And these are large institutions that can be difficult to actually create the coordination that's needed. And then we have limited local capacity, and so this is especially speaking to our more rural communities, although we see it at every scale of government, that we may have a government where you have a local jurisdiction where one person is the fire chief and also the town clerk and also the town historian, and they also are an elementary school teacher. So these people, our local officials, wear so many hats, they do not have the extra bandwidth to kind of do this future-oriented thinking when they're just trying to get day-to-day to make sure their community is still functioning. And we don't have a good source of funding for that. It's much more attractive for both private and public funders to fund stuff you can see, like bridges. It's just less exciting to fund a person at a local government, but that's what we really, really need. So I'll talk to you about some of the important pieces of policy that we've put together in recent years. There's been really great leadership both from the governor and from the General Assembly. The governor issued Executive Order 80 in 2018, which was North Carolina's commitment to address climate change. In it, it called for North Carolina to develop a comprehensive science report on climate impacts, as well as develop a plan for the state to become more resilient. For the General Assembly's part, they have been, the General Assembly holds the purse strings, and in the 2021 biennial budget, so basically the one we're still operating under, they put $300 million towards flood mitigation efforts. So they are starting to lay down some serious money in recognition of the need for funding flood mitigation. So a few exciting things that are happening more specifically. Do we have our state climatologist here? I know, I saw her earlier. She may have had to step out. A lot of, this is partly to her credit. We are updating our rainfall frequencies. So the rainfall data that we're using to base engineering decisions on is woefully out of date. It does not include things like Hurricane Matthew or Hurricane Florence. And so even just to bring our engineering standards to current day, we need to update that data. And then we're working with our state climatologist, Dr. Kathy Dello, on incorporating climate change to pilot some more future-looking engineering standards so that when we plan a piece of infrastructure that's supposed to last 100 years, we've incorporated the idea that it's going to rain more frequently in 100 years from now. So let me skip through. Let's see, we're retrofitting to better standards. DOT is actually leading the way in some really, that's Department of Transportation, some really exciting ways here. They're using nature-based solutions. They are among the agencies that are sort of most cutting edge in how they are projecting things like sea level rise and taking that into account when they are laying out money on large pieces of infrastructure. We have a lot of effort around heat health. I know I've been talking a lot about flooding. Heat health is a major social equity, social justice issue. Our folks who are most vulnerable to heat are outdoor workers, senior citizens, people who don't necessarily have the greatest advocacy voice. And so it's really exciting to see our state and local public health leaders be looking at heat health issues. There's a number of state resilience planning initiatives completed or that we are going to work on. One exciting one is this flood resilience blueprint, which will take a watershed approach to addressing flooding in North Carolina. It's what's really needed because our watershed, the way that water moves through our state doesn't necessarily respond to jurisdictional boundaries, and that can be a big obstacle. So we're really looking, that one's not underway yet, but we're looking forward to having that develop. And we're supporting local communities in identifying their own resilience needs and resilience priorities and helping close some of that capacity gap that I talked about. So just to recap where we've been, there's a lot at stake in North Carolina when it comes to dealing with the impacts of climate change. And we want to make today's decision in light of their a generational impact of the decisions that we're making. Number two, state leaders are prioritizing resilience in some really promising ways. We have a very long way to go, but it's good to see that kind of action and commitment. And that's to address both those kind of physical vulnerabilities and the socioeconomic context that make us so vulnerable to climate change. And then finally, there's a tremendous diversity of initiatives underway in the state. There are things I learn about every single day that are happening in different pockets of the state. It's really exciting. What we need is sustained funding and capacity to institutionalize those practices, bring them to scale to really get us into the 21st century, prepare us to prosper in a changing climate. So that's it.
Thank you, Dr. Martin. I learned at breakfast that the next speaker was actually your major advisor during your doctoral work. This is really a nice, close-knit connection. Welcome back to North Carolina. So next up is Dr. Gavin Smith.
Actually, you stole my thunder, but just to be honest, I wasn't her major advisor. I was on her committee, but nevertheless, I'm still really proud of her. Where did she? I was going to say, don't let her leave, because the students, all of you in the room, this is someone to aspire to. So you ought to grab her and talk to her about, some of the things that she did that allowed her to take on this this great position. So I'm going to talk about a lot of stuff. I'm going to do it fairly fast. I'm going to talk about a textbook that a colleague and I wrote. I'm going to skim through some of that. I'm going to talk focusing on buyouts or the acquisition of hazard-prone housing, which is a really important risk reduction and climate change adaptation technique. I'm going to talk a little bit about the National Academy of Science study that I'm part of, looking at managed retreat on the Gulf Coast, which I think has some really interesting insights. And then I'm going to wrap up with a new $1.5 million grant we received 2 days ago. To talk about how we can collaborate with people like Amanda. So what I'm going to do is the textbook that I showed, shameless plug, I guess, is there is the text. The intent of that textbook was to take lessons from natural hazards and disaster management and apply them to climate change adaptation and vice versa. And this is something that I've been working on for some time. And we did case studies all over the world, and we looked at those lessons and asked each of the authors to tell us about those lessons. And so what we did is we distilled 254 lessons into 4 imperatives. So I'm going to quickly go through those, and I also would encourage you to think about how everything I talk about is going to be also linked back to the acquisition of hazard-prone housing, which I'll explain in just a moment. You can see the slides are a bit dated. This is when Mitt Romney wanted to cut FEMA just prior to Sandy. And our former president basically arguing that climate change wasn't happening. So the slides are dated. The book was written in 2014, but people like Amanda and others, there's been a fundamental change, at least in my opinion, in what's happened in our country just from 2014. And so but I do think these imperatives are still important. And in fact, they link, I think, nicely with what Amanda talked about and some of our other speakers have talked about. This one is a governance imperative. How do we get different levels of government to collaborate? How do we use different levels of government to deal with conflict? Climate change is inherently contentious. Disaster management is inherently contentious. How do we develop the issue to deal with flexibility, things like the issues of uncertainty and non-stationarity? Also, we distilled these, some of these recommendations into what we call a capability imperative. Again, Amanda talked about this. This is one of the greatest challenges, I would argue, in climate change adaptation, is how do we help local governments, states and the federal government build the capacity to deal with climate change adaptation. I think, to me, this is one of the most fundamental questions of the overall challenge. So how do we build an extended network of people that can offer assistance? And I'm going to talk about that large grant. It involves land-grant universities. How do we draw and harness the capacity of land-grant universities, for example, to deal with these issues? How do we develop knowledge and policies through dialogue as opposed to basically telling local governments what the answer is? All of these issues are really important. A planning imperative. I have a background in land use planning as well, as does Amanda and many others. Thinking about how we do a better job of land use planning, not only where and how we build in relation to hazards, but how do we think through future investments that might have a 100-year life cycle if it's big infrastructure like Amanda was talking about. The issue of planning for this future and planning for uncertainty. And how do we think through innovative strategies? This was actually prior to Aaron asking the question. This is one of the things that a lot of people around the world were talking about. And these are concepts and ideas, but how do we, for all of you, I mean, this is a life's work. Each one of these slides is a life's work, but how do you operationalize some of these big questions? And then finally, something that I would suggest maybe we haven't talked about enough in this session is a real moral imperative. Amanda talked about it relative to social vulnerability, but there is a moral imperative for us to do something. You know, you talk about the next generation, but all of the people, think about the elderly folks that were in Florida, or think about others that are perhaps not as wealthy or don't have the resources. The image on the upper right is a photo I took in Manila. It may not look like much, but there is about a 30-foot wall right behind that development. That is on the inside of a concrete revetment. Every year those houses wash away, and every year they're built back. You could make the argument that they're resilient, but that's the only place they have to live. I'm not saying it's resilient. I'm saying that this is basically their alternative. This is Shishmaref, another photo that we took, and basically the community of the Native American village is falling into the sea. And so how do we develop these processes that are deliberative, that give voice to people that historically have not been given a voice, but also are disproportionately feeling the impacts of climate change? So to shift gears a bit and to think about this issue that I'm talking about today is this background on buyouts. The word buyout is, if you lived in Eastern North Carolina, everyone knows what the buyout is. This is in essence monies that are provided to local governments to acquire hazard-prone housing, typically in the floodplain, buying them out. They give them money, they take the money, they move elsewhere, we tear the house down, and that land is turned into open space forever. But some of the big issues that drive some of this, and again, for those of you in different disciplines, you know, perhaps take a look at some of these slides and how they apply to you. One is if you're in economics, we typically use benefit cost analysis to determine eligibility. Maybe that's not the right method to do it. If you're poor and your house, we bought out a house in a former life working in state government for $10,000. That was a stick-built house, $10,000. What are you going to do with $10,000? So my point is the cost effective, if you have a really expensive house, it's more cost effective to buy it out. If you're looking at thinking through, we typically pay pre-disaster fair market value. Again, low-income people disproportionately are hampered by this. The program is voluntary, and I use quotations around that because this program typically happens in the post-disaster environment. If you're poor, you may have few alternatives, and so you take the buyout as a way to recover, not necessarily as a way to reduce risk. And so all of these issues are important contextually because and I'm linking this back to climate change adaptation, because buyouts, in fact, I led a program in a former life working in the same agency that Amanda did, where we acquired 5,000 homes in Eastern North Carolina. That's good, in theory, but most of them were low-income housing, and there was already a lack of available affordable housing, so we reduced risk but exacerbated affordable housing issues. We didn't build back replacement housing, as we should have, to incentivize the people to stay in these communities. So these are big issues that directly relate to the issue that everyone's talking about now, which is managed retreat. These buyouts have been going on. There's over 50-some-odd thousand buyouts that have happened in the U.S., but we're often not talking about these issues. I'll talk about the New Zealand example in just a moment. These are some of the challenges that I've talked about to some extent, but if you're a small community and you do a buyout of a fair number of houses in your community, you can lose your tax base if you don't build replacement housing. We often don't think about pre and post disaster planning, including building new replacement housing. The level of participation, people that choose to participate, it may not be contiguous. So you may have what we call checkerboarding. Every third house is bought out. So you're tearing apart the social fabric of the community. You're buying down risk to some extent, but a lot of people are still staying in these areas. And so we still have to go out and rescue them, or we have to help them recover in the next disaster. This is just an example, a slide shot. You may not, you say, what in the heck is that? So that is I did some advisory work in Hawaii after the Kilauea eruption. And it goes to me, it's a really powerful example. Don't worry too much about it. It's basically showing the lava flow into Leilani Estates. And what's interesting is that some of these places were under about 20 to 30 feet of lava. Most of the people didn't want to take the buyout. They wanted to move back and build back on top of this still smoldering lava flows. They had to wait, of course. But my point is there's deep place attachment in many places, not just in the coast. The people wanted to come back to what they knew. And they're still, this was a program that 2+ years later, they're still working through who's going to participate in these buyouts. So I want to, again, kind of shift a little bit and talk about a study that we did looking at a comparative study of buyouts in the US and New Zealand. And they're very different. And I said 50,000. There's actually 65,000 homes when this slide was created, buyouts that have happened in the US. We know that it's one of the most effective ways to get people out of the floodplain. I mean, ideally, we wouldn't build there in the first place, but there's all kinds of reasons that Amanda alluded to. The land is less expensive, so people may have limited options, and so they choose to live there. But it's a very effective technique to reduce flood hazard risk, and it's really a key part of what we would call managed retreat. There's a lot that we can learn from other countries, but this is, I think, I would argue in the US, it's our own hubris. We're very good at sending money to communities. Let me back up. We have a lot of money to send. Actually, I think we perhaps don't send it as well as we could because the capacity to administer it is tough. But we're not drawing from international lessons like New Zealand. And so the timing of this is actually quite good. We're starting a new project where now that we're developing a national managed retreat strategy in the US, New Zealand's a bit farther along than us. And so our offices, our White House and the New Zealand equivalent are going to be working together on this effort. So I'm really excited about that. More to follow there. These are some of the findings. So some of the big issues. These programs are really bureaucratic. They're difficult to administer. They take a lot of time. Some buyouts take 3, 4, 5+ years to be bought out. If you don't have an alternative to live in, you live in that house that's full of mold and in bad condition. We don't have enough capacity at the local level, but we also don't invest enough money to help local governments administer this program. Samuel Cornegi, I think, is in the room still from Lenore County. I mean, he can tell you about the challenges of administering this program. It's very, very complicated. This money typically flows post-disaster. Imagine trying to administer a complex program in the throes of a disaster. So all of these issues are challenging for us to think through, including how do we better manage the open space in the US. New Zealand's very different, although they're very similar. If you look at the image on the upper right, that is actually pronounced the Whakatane District Council. That was an image I took. They was told not to get out of the car. This is a person's home. Basically, I'm not being bought out. Don't tell me what to do. And before you know it, you're next. It's going to be the grand scheme to take all of your land and so forth, which we've heard some of that before in the US. But what's interesting about the New Zealand case is that they don't have these highly bureaucratic programs. They create them in the aftermath of a disaster, and they run them through their existing federal programs. So they actually create federal buyout programs based on the disaster at hand. The challenge with that is they haven't developed a program, and so they've got to develop the actual program, and they do it over and over. But for example, in Christchurch, New Zealand, they did this. And they didn't actually adhere to clear voluntary programs. So they bought out almost 8,000 contiguous parcels in Christchurch. Imagine that. You know, I talked about the checkerboarding issue. They bought out, for the most part, 8,000 contiguous parcels. And I'm telling you, I've got 2 minutes, so I'm going to have to go through this very quickly. All right, so here is just some examples of the open space management that they've done. These are some shots that I have of the red zone landscape. One thing I will point out is we are working on and finalizing an open space management guide for the use of buyout properties, soon to be hot off the press, I'm hoping in about a month. A couple other slides. If you give me 1 extra minute, I'll get you a coffee at the break. I was going to say beer, but we don't have no beer, I don't think. Anyway, so shifting again to this National Academy study very quickly is we actually met in Houston and Tampa and as well as Ile-de-Jean-Charles. These are some of the preliminary findings. I'm not going to read through them in great detail, but what's really fascinating from the local government perspective is almost everyone in the community said, managed retreat, there's no such thing, it's an oxymoron. It's not being managed, it's ill-planned, it's ad hoc, and it's highly problematic. I would strongly encourage, if you're interested, especially look at Chief Dardar from Ile-de-Jean-Charles talking about this. It's incredibly powerful just if you take a look at these slides. I'm going to quickly run through. These are some images from Ile-de-Jean-Charles. Excuse the images because this is taken from a moving van. But this is us driving into Ile-de-Jean-Charles. Interestingly enough, they're building $100,000 boat strips adjacent to Ile-de-Jean-Charles that they're buying out and moving them away. To me, I thought that was an interesting issue of the bad governance going on. These are, again, houses that remain. Many people are choosing to stay. That's actually stretched quite a bit, but nevertheless, this is an adaptation measure. The person that's looking to stay, you can see the elevator. This is actually a person that he allowed us to stop and take this photograph. It's clear that he doesn't like climate change, but he also recognizes it's happening, and he does. But at the same time, he also doesn't want to move. This is the typical kind of prototypical design or layout of these communities in Ile-de-Jean-Charles. This is where they're moving to. So it's tens of millions of dollars moving Ile-de-Jean-Charles to this community in Homa, about 30 miles inland. A lot of the people that we talk to don't like it. We've spent tens of millions of dollars doing this. They felt like they weren't fully engaged in the process. And so this is a real problem. Very quickly is to just say that there are tons and there are tens of millions of dollars, hundreds of millions of dollars that are coming through these different programs. I'm not going to talk about them, but rather these are things that I would encourage all of you to think about. This is my last slide, is to tell you about a project that we were just awarded. It's an idea that I had proposed to FEMA. In essence, how do we as land-grant university at NC State and land-grant universities around the U.S. build the capacity of under-resourced communities to develop and implement large risk reduction grants. We are working on this. We're actually just getting started. We're going to be interviewing and doing national surveys of faculty and engagement experts around the country, including at minority serving institutions, to find out those that are interested, technically proficient, and committed to do this work, because it does involve a long time commitment to do it right. And so we're working on this. I'm hoping, and this is going to be part of our large-scale report that we'll develop at the end of the year, which is I would love to get students involved at NC State and all over the country, but also thinking about perhaps the central node being here at NC State. And these are, instead of doing it at the front, these are just some of the papers that we've created through our most recent research. Okay, great, thank you.
Thank you, Dr. Smith. Next up is Dr. Casper, who's going to be talking to us about how sport can be a platform for climate change, something you may have never considered.
All right, I might be the most different presentation of the day, but I'm the final presentation, I believe, of the day. So, all right, we're going to practice something here. So if you're in this area here, these little seats here, or these little seats over here, and myself, right? I'm going to scream climate, okay? And then if you're in the middle here, you're going to scream change, okay?
What about adaptation?
Okay, let's do adaptation. Better idea. Adaptation. All right, ready? So, actually, it's not coming off. I'll do it for you. All right, so the far seats on these sides, this side's climate. Ready? 1, 2, 3. Louder. 1, 2, 3. All right, and then in the middle, let's do change. It's easier. All right, climate, change. All right, ready? Climate, change. Climate, change. Climate, change. Go climate change and adaptation. All right, no, just joking. All right, so I just had to kind of warm you up. I had to get into the sport experience of this, but I don't know if it was very effective, but I tried. So I'm going to talk a little bit about sport and try and be more specific to climate change and how sport relates to it. I think I got it there. So I'm going to start with this. So first of all, we know that sport itself, as we start to look at sport itself, is impacted by the environment, but also impacts the environment. And so there's a lot of different examples as we start to look at this. First, if you're thinking about sport, if you're thinking about professional sport, or if you're thinking about even collegiate sports, we have huge facilities that command a lot, both on the environmental side of it, but also deal with the fans that come to and from these events. So the environment is affected in many ways. And so with that, we know that sport organizations need to be accountable for their environmental sustainability and start to take some actions specific to that. Lanny probably knows this little picture over here, but this is the tailgating area here at NC State, kind of demonstrating some of the trash that's accumulated just in the grounds here at NC State. But there's a lot more than that. We've done some research on air pollution and how much air pollution is associated with hosting a college football game, both from the amount of emissions that come taking the people to the game, but what happens during the game, including the charcoal and the idling and everything else that goes along with that. So we've demonstrated, and there's a lot of scientific research showing that sport needs to do a better job of accounting for their environmental sustainability. As our past speaker just spoke, we also know that the climate is changing, and that's affecting how sports are being offered or if they can be offered. And so we see a lot of examples, for example, even with the most recent hurricane, how major sporting events had to either cancel, delay, or move their events. We saw, for example, in California during the forest fires, where the San Francisco Giants couldn't play their games because the pollution was so bad that it was bad not only for the athletes, but for the fans that were actually there. So sport is starting to wake up a little bit to the fact that, hey, not only do we need to account for our environmental footprint, think about climate, and we also need to be thinking about climate change and climate adaptation. So that there is that as well. Another thing that's really important is that, especially because our older people are getting older and our younger people are becoming more into the managerial roles, especially within sport, but we're starting to see that not only sport managers, but sport fans wanting actual change when it comes to sustainability and recognizing that climate change might be a problem. So we're starting to see society as a whole start being a lot more receptive to environmental efforts, climate change marketing or communication. And as a matter of fact, a lot of my research here, specifically mostly to college sports, finds that about 68% of the people that go to sporting events actually want to see and learn about environmental actions and sustainability. So we see that there's an audience, a captive audience, that's part of it. I'll talk about that a little bit more later. Also, we know that what we're starting to see is that as we start to accommodate for sustainability, you start to see that there are people that are affected, whether it's the athletes, whether it's the fans, but we're also starting to see an economic aspect to this as well. And I don't want to take a lot of time on this, but we start to see where there's opportunities for sustainability related sponsors. For the past 8 years, I've worked as a consultant for the University of Colorado. They have something that's called Ralphie's Green Stampede, and they basically look at how to not only incorporate environmental sustainability at their events, but also how do they change their fans' lives? How do they change behavior outside the event? And they do that based on the money that they get from sponsors that help fund their program. And they fund initiatives that are based on trying to change behavior. So you see that there's a whole bunch of things happening. It's good for me. 12 years ago when I did this, there was very few of me doing this research. I just came back from a conference where there were 14 or 15 people doing what I was doing, and then there's about 300 practitioners implementing a lot of the things that we do. So there's a lot of momentum going as it comes to this. Aaron asked me to see how does this all link together? Well, the big thing is that we see sport being this platform for awareness and ultimately change. Change is hard, but awareness is a little bit easier when it comes to what we're doing. So we learned that, first of all, the sport's an important enabler for sustainable development. And if you go to the UN and you Google UN and sport, they'll basically have the UN Sport for Climate, and they have all the different ways that sport can help contribute to all of the different sustainable goals. So much that at COP, they actually spend a lot of time with sport being a major platform for what they do. So we're starting to see international movement going to this. Also with sport, and this is where you get into this kind of non-traditional educational platform. So we know, for example, how do you get kids to change their behavior? You get them young. So we have a lot of sustainable education that goes into middle schools or even elementary schools. But what about adults, right? What about adults that have kind of stuck in their ways, okay? Well, sometimes sport can be this educational platform or this non-traditional platform to hopefully encourage sustainability behavior, raise awareness of climate change, and actually be an example of it in many ways. Lastly, and this is Lanny in the back, we used to be part of this, is that we have something called demonstration effect. And this is kind of like a see and do, in the fact that if I don't even know what composting is, if I go to a game at Carter Finley Stadium, I pretty much have to compost. So I actually have to do it. And I see my friends that go to the game do it. I see the educational programming that goes along with it. So there's actually the demonstration effect that helps with changing social norms, which is an important part of what we do. How am I doing on time? Okay, I'm gonna go quicker. All right, so one of the key areas for innovation is something called the Sport for Climate Action. And this is a UN initiative. This is where sports can actually sign up to commit to some of the UN sustainability goals. And this, it's hard to see, but it's in blue. These are some of the different ones that they have. So it's about cutting emissions. A big part of what they do is that it's not just related to the organizations itself, but it's looking at the fans and looking at the external stakeholders of that organization. And so, as I say here, sport is a unifying tool to create the solidarity among global citizens. This is a way where sport can take a lead, okay? And I've learned a lot from my research that it takes someone that really cares to actually do anything about it. And so if you have these major sport organizations signing up, committing, and even competing to beat each other, change can happen, and hopefully in a good way. So some of the research that I do focuses mostly on fans and decision-making of fans and understanding, do some of the things that happen. And my big area here now is looking at climate change. We know that climate change is polarizing. We know that there's many people that will just close their ears and eyes, and like the man who was about to get evicted might recognize it, but is not going to pay attention to it, right? And so within sport, we have that. As a matter of fact, if you look overall at sport fans, about 60% of them identify as conservative, and so you have a captured fan base that ordinarily it could be very hard to get to. And so with sport, we're trying to provide this neutral platform where in a non-political way, and that's a big thing, in a non-political way, be able to change awareness, change how they think about climate change, how they think about sustainable in a certain way. So we can start at the lowest level, right? We can start at something, for example, at Clemson University. They're the Tigers, okay? They did a climate change sustainability initiative that was about the tiger habitat and how it's being affected by climate change, and how can tiger fans do something about it. It was an extremely successful initiative, okay, but not political, okay, not political. But if you care about the tigers and you're a Clemson Tiger, then you need to care about this, okay? We can do the same thing here at NC State. The American red wolf is being affected by climate change, okay? So we can do things like this where we can hopefully have this be something that's effective. Last thing, and then I'll get to it, is that I've started to find that for example, Republicans, in this case I compared Republicans and Democrats, Republicans were very aware of the initiatives that were happening by sport organizations. As a matter of fact, they could recognize the sponsor, they could recognize the purpose, and they could recognize the behavior of what we were trying to communicate to them just as much as we could Democrats. So we're learning that we're not preaching to the choir when we do this, and that can be a real important thing. So I'll leave it on that, and then I can answer any questions as we go.
If I can ask the speakers to join me on stage, that would be great.
This one, nope. Oh, there it goes. Okay, it's working.
Talk there, put a bow on this session and the day, because we really do need to think about how to change individual behaviors if we're going to make some kind of change to our climate dilemma. And so some of the things that I heard in this session was really about what is at stake, right? How decisions today impact the future, and how we need to be thinking and incorporating climate science in solutions into those types of initiatives when we're conducting land use planning, when we're changing infrastructure, and that capacity is needed, and not just in terms of our capabilities, but also capacity in terms of awareness of the public and in creating a moral imperative to move this forward, so that justice is also a key concern and a key issue that's addressed. And so I'm hoping that our panelists could just take one moment to comment a little bit further on how you think our students in the audience and online can consider integrating justice into their work.
Sure, what a great question. I think that there is a role to consider equity and justice in whatever setting you work in. If you work in a lab, if you work in a local government, if you work in a community-based organization, there are so many scales of action that we can take to be considering justice. And I guess I want to make a plug for something that I've been learning a lot about recently, which is inclusion for people with disabilities as a justice issue. Particularly, it's very important for climate resilience work, because people with disabilities are affected by climate hazards differently. And yet we don't always account for the diversity of disabilities that can be present in a room, those that we can see and those that we can't see. And so it's really important that we make not just our government programs more inclusive and diverse, but also our student communities and our group work groups, and all those smaller pieces that build up to the community that we actually live in. So that would be my thought.
Yeah, it seems to me one of the issues for all of you as students is to think about, you don't have to have a background in the social sciences, or if you're an engineer, for example, at least I think a good engineer will look at issues of equity. And by that I mean, for example, I mentioned benefit cost analysis as a way to determine where we are placing investments. I talked about buying out hazard-prone housing, but benefit cost analysis is used to measure the efficacy of protective measures. And you could make the argument that that's problematic because it disproportionately encourages people to build protective measures to protect the wealthy. And you can see that outside of New Orleans, the levee tails off in some of these poorer communities, the rural communities that don't have access. So if you're an engineer, there's a role for you to play in this. If you're in political science, issues and understanding roles of power and power imbalances, all of those things are really important. Another thing I would suggest, and in fact Aaron and I were talking about this, I think, during breakfast, is one of the most important classes I ever took in graduate school was environmental dispute resolution. The ability to understand these issues that deal with resource management, they're inherently contentious. Dispute resolution teaches techniques to empower people, It also teaches techniques to engage people over long time scales. I know, in fact, Erin, I think, teaches a class in that, so maybe a plug for Erin's class. But I think that's incredibly important, you know, again, whether you're an engineer or not. I guess the other thing I would say is this notion of interdisciplinarity was talked about quite a bit. I think that's important. And again, I feel like I'm just a salesperson. I'm plugging another thing. But I would plug a graduate certificate that I teach in disaster resilient policy, engineering, and design. So we have students that are engineers, public administration, landscape architects, and so forth, working on big issues. In fact, last year, we conceptually looked at how are we going to resettle the Outer Banks. I'm not suggesting that we should do it. I'm just saying that we actually challenge students to think about how that might occur. So those are just a couple thoughts.
Yeah, I'll be quick, but I think if you're looking at sport through this lens, I think it's looking at where there's injustice and how can that be communicated through sport. And so, and I think that's like, for example, climate injustice is part of Climate Pledge Arena's big. This is in Seattle, this is a new arena that they had, the Seattle Kraken play there, and they were looking at climate injustice specifically with people that are being moved out because our arena is being built, right, and forced into different areas. So I think it's just looking for those areas where at least sport can be a sounding board or amplify a cause. It's not sport with justice in sport is is used a lot.
So the first question I have is from online, and it's pretty specific. I think it's for you, Amanda. Someone was curious about when North Carolina was going to release their updated IDF intensity, duration, frequency curves for rainfall. Can you respond to that?
Sure. The answer is not tomorrow, unfortunately. We're just working on getting that project rolling. An exciting part of it is that we're hopefully going to be able to fund a platform so that it'll be more publicly accessible. But I would say we're probably looking at least like 1.5 to 2 years before that comes out.
And I have my own question. So, and I feel like all of you have touched on this. You specifically mentioned it, Amanda, but you're talking about path dependency, which is really important in this world. Can any of you discuss sort of what you consider to be best practices to create new, more sustainable paths? And beyond just infrastructure, I mean, we've talked about political path dependency, social networks, collaborations. What do you think we should do to, start going down a better path?
Let's see. So I guess I guess I'll go next. So, and whether this addresses your question directly or not, I'll give it a shot. Is one of the things we talk a lot about in my classes is this notion of resilience. It has roots in both ecology and engineering and other principles, and the social sciences as well. And to think about the issue that there is not a one size, there's not one answer. The idea that just the New Orleans levee is going to protect New Orleans, that's not true. And actually they're altering those techniques where they have, as Amanda alluded to, these multiple lines of defense is another way to think about it. Not just a levee, but selective acquisition of some hazard-prone housing, elevating others, protecting critical infrastructure, and so forth. So I think that's something to think about, and that again spans all disciplines. It spans public administration and engineering and the social sciences, nature-based solutions as another alternative. I mean, thinking about all of those issues working in tandem, I think, is really important. And thinking about the root, a healthy ecology is one that's inherently diverse, generally speaking. And so all of those issues, I don't know that I'm getting at your answer, as clearly as perhaps I should, but those are just a couple thoughts. Yeah.
I can say a few words about that as well. I think something that that a lot of the sort of unsustainable paths that we've been on have in common is that they seem to really make sense for one reason. Often it's an economic growth argument, like we really needed to do this because we need to grow our economy. And I think shifting our language, if it's the language we use in our community spaces, in media, in public relations, to think about multi-benefit solutions, so solutions that have, maybe they have something good for the environment and something good for the economy, and maybe they have something good for people in them as well. It's kind of an idea that's been around with sustainable development for a few decades, but it's getting some new life breathed into it by things like nature-based solutions, which can offer protection against climate hazards while also being good for the environment, as well as it can create recreation space. It can be an economic amenity for a community. And so normalizing the idea that our investments should have benefits that fall into multiple sectors, I think is a big shift that we could make at a high level, theoretical level, that would help us identify those paths that we're not going to regret in 50 years or 100 years.
Thank you very much for three great talks. I'm a newbie at this area, so forgive the question. I've been very impressed by the one shining example of Ian, of Babcock Ranch. All the houses were built to withstand 150 mile-an-hour winds. They didn't put up telephone poles, solar panels, which, thank goodness, are low to the ground where the velocity of the wind is zero. Very smart. They were 25 feet above sea level. I'm not sure if that was just by chance or they actually filled in. And they also built special spaces to capture water from the rain for very large events like this one. It worked perfectly. Are we better off spending money helping people to get there instead of buying them out, moving it, and then not putting in solar panels? I mean, I'm all for playgrounds, but if you have flat area, maybe we should be building solar panels instead and put the lines on the ground, and then when the problem comes, you're ready. Just a question.
Absolutely. I think that Gavin spoke a little bit about pre-event planning, which is one way to look at that is when we say pre-event, we mean before the disaster. And when we think about planning, it can be, I'm a planner, so I think about, well, how does a community like that get developed? What regulations have to be in place? What kind of an investor will support the development, the upfront costs of financing? And then how do we get people into a community like that? So absolutely, so there was a study recently done by researchers at UNC and NC State, a variety of other North Carolina institutions. It was at the General Assembly that the legislature asked for it to address flooding challenges in North Carolina. And one of these studies found that for every property that we have taken out of the floodplain, we are building something like 8 more. So for every property that Gavin's program worked to build, to remove from the floodplain, we've built 8 times that number of houses in the intervening time. So that's obviously not a sustainable practice, not something we want to see. So, I mean, absolutely, I think we want to be putting the money in up front to build the communities that will last.
Yeah, Ruben, I think it's a really good question. I would suggest we need to do both. There's and this is the challenge, and this is actually, that was my concern. I started to try to think through, what is the aggregate risk in North Carolina? Are we buying it down through 5,000 buyouts or not? It sounds like we're not, because we're adding more. And so my point is, we need to think about people and property that is in harm's way now, and we need to deal with that in some form or fashion, retrofitting them, elevating them, moving them to higher ground. But at the same time, we also need to come up with powerful incentives and disincentives for people to continue to build in these hazardous areas. And I would suggest it goes back to this notion of resilience, that, buyouts, some level of protection, some level of not building there in the first place, choosing not to place infrastructure there. The second part, and actually both are fraught with political challenges, is to tell a community that you can't use all developable land in your community. You can build in the floodplain, and that's never been against the law. You have to follow certain standards, but in an era of climate change, what's that standard? We're still trying to figure all this out.
Are there public monies that can be used to take existing homes and build
They can be, and it depends. So you can elevate houses in place. However, most infrastructure investments, most housing investments are built and designed to the 100-year flood event. And now in an era of climate change, that's wrong. We spent $14 billion repairing the New Orleans levee largely to the 100-year event. It's out of date. It's already out of date. But what's the right design standard? Do we design like the Dutch to the 500 or 5,000 year return event? And who pays for it? So, I mean, all these issues are intertwined, and they're fraught with real political challenges. It's also harder to ask a local government official to limit development in certain areas, especially if they have friends that own that land. But then on the other hand, in the post-disaster environment, sometimes people are willing to move because they've had enough. But sometimes they're also very reticent to do so, so they stay. So I would suggest we need to do all of those things. And that's again, one of the fundamental challenges for students and all of us, is how to come up with a thoughtful strategy to do it that has funding and political support to do this over long timescales.
I just received the 2-minute warning, so yes, one more question will be welcomed.
A question that may fuse the three folks on the stage's expertise. I'm excited for this. So, Dr. Casper, the Winston-Salem Dashes, the Durham Bulls, the Down East Wood Ducks. My question for the panel is, how might we devolve some of the sustainable development goals and their relationship to sport in a distributed statewide way in smaller communities? So I'm imagining something like a resilient North Carolina night at Granger Stadium in Kinston or the Durham Bulls Athletic Park. Would love to hear your experience or familiarity with kind of the smaller communities and their experience with sport, and some feedback on that idea. Thanks.
I love it. So within sport, and especially the most effective activations or campaigns are specific to the community needs. So if you can find, as scientists, areas where there's something that can be communicated to a population or a local community, talking about the minor league baseball scope and who goes to these games, it can be an effective way if it's done right. Greenwashing is a big thing within our realm, and if you have a green game, well, does that really matter, right? If you're not doing it all the other games. So if it's something where the science or the need for community action or the need for community awareness can be specific enough at that community level, I think not only will it be unique, but people will be more receptive to it. So as you see with minor league baseball teams, you see all these crazy names, but a lot of them are because it's reflective of the community, right? And so having the initiatives be reflective also can be important as well.
Excellent. Would you like to respond?
I don't know. Brian, thanks. Brian's my student. Brian, come on. I'm speechless.
I think there are people like Dr. Casper who have figured out how to make a career out of something that the rest of us just do for recreation. So I read here that you are a professional sports fan. It's like people who research tourism and go be tourists. Anyway, I really admire that. I love the idea of a resilience connection to local sports, because then it could be part of my job to be a sports fan as well. Yes, there you go. No, but I do think that Brian is drawing a metaphor here that's really important, which is that we have some really standout examples of places that have been built to very high standards, or communities that have attained some kind of, there was after Hurricane Michael in the Gulf on the coast of Florida, we kept seeing this image of an entire community that had been like decimated, and there was like sticks and rubble everywhere, and there was one house at the shore that had been built to a higher standard that was just standing there. Really stark demonstration of what higher standards can do. So it's important to have these great examples, but I think part of what Brian is saying is that we need to figure out how to make those examples accessible to smaller communities, to more modest communities, more modest homeowners, so that they can be distributed across the state and across, the communities where we live. So thanks.
Well, great. Thank you all for sticking around this afternoon. Amanda, would you like to give a little update on what's next?
Thank you again to our speakers and panelists. If you guys will join me in a round of applause for all of our speakers today. I thank all of you and would like for you to give yourselves a pat on the back. That's also a little extra stretch for sticking with us for this very long day, but I'm hoping you're finding it as rewarding as I am with this diverse perspective. We have worked you hard, your brains hard, your behinds hard. So now we hope to give you some relaxation and truly a time to connect and talk. Gavin, we do have wine and beer for those of legal age. So you're gonna have to treat Aaron to a wine or a beer. So we do, upstairs on the back of your name tags, our list of folks who are presenting at our innovation showcase and reception this evening. So you can find those. We did have one last minute step out, so we apologize for that. But yeah, so there are light refreshments with the beverages now, and then at 6 we'll have our folks who are representing their businesses and groups at their tables until 6, and then we'll all join together kind of as a dinner time as well, and that's all buffet style, so feel free to mix and mingle, and a large number of the students left their posters, so if you haven't had a chance to look at those yet, do that as well. So if you have any other questions, tomorrow morning we'll be back starting our first talk will actually be up with breakfast in the morning. We have a representative from Eastman Chemical at that time, and then we will come down here to hear from, I believe it's 13 of our different programs here at NC State and all the wonderful things that they are doing around climate challenges and solutions as well. So a great opportunity to build some collaborations with the university. And then just prior to lunch, we have James McMahon from S&P Global, which is, and he is the CEO from the Climate Service. And then at lunch, we have a couple of folks from Avangrid that will be presenting as well. So we look forward to seeing you again tomorrow, but for the rest of the evening, please join us upstairs for just some good relaxation.